morning to everyone. Please take seat. So we will start the first session in the morning, which has a very promising title of, let's see, this is Big Science Questions to be Answered by Infrared Astrometry. And first of all, I would like to make an announcement. We have a meeting room available for those of you who needs to do a telecom or a meeting for a short time, please. This is in the first floor, following the corridor, the last room to the right, to the left. And before going there, you should pass to the concierge and tell him that you are going to go upstairs to use the meeting room, okay? So, as I said, we will start now, and the first talk of this morning is very interesting. It is about the challenge that Gaia NIR, the opportunities and challenge that Gaia NIR will have to explore the galactic center. And the speaker is Francisco Noguera Lara. You have 15 minutes.
Okay, thank you. Hello, everyone. Good morning. First of all, I would like to thank the organizers for inviting me to give this talk on the Galactic Center, my favorite topic. So I'm going to be talking a bit about what Gaia NIR can do at the Galactic Center and some challenges that we will have there. So let's start with a brief introduction on the Galactic Center itself. So this is a spitzer view of the central region of the galaxy, and the first thing that you notice is that we have here something very bright, and this is basically the structure that is outlining the galactic center. So it's what we call the nuclear stellar disk, and this is a flat structure with a scale length of around 100 parsecs and a scale height of around 40 to 50 parsecs, and it contains more than 10 to the 9 solar masses of stars. So it's really, really massive and dense, and it's also different from the surrounding area, which is basically the galactic bar. If we zoom in and we go towards the innermost regions of the nuclear stellar disk, what we find is another stellar structure, and this is going to be the densest cluster in our galaxy. It's what we call the nuclear star cluster. So it has an effective radius of around 5 parsecs, and it contains more than 10 to the 7 solar masses of stars. So it's even denser than the nuclear stellar disk. And then, of course, if we continue and we go inwards, we will find the supermassive black hole at the center of the galaxy, Sagittarius A star. So now that we know more or less the galactic center, let's talk a bit about the observational challenges that we find when we try to observe this amazing region. So the first thing is that the galactic center is relatively far away, so it's at 8 kiloparsecs from the Earth, and we are within the Milky Way, which is nice, but it's also a problem because to observe the galactic center we need to go all the way through 4 spiral arms, and then also we need to go through the galactic bar, and finally we will reach the galactic center. So it means that we will have a lot of contamination from foreground population. And it's not going to be only the foreground population, but it's also the stars that we have there. If you remember, I said before that we will have more than 10 to the 9 solar masses of stars for the nuclear stellar disk. So it means that even if we go to regions in which we don't have any particular structure, we are going to have too many stars. So this is just a random region there, and you can see that there are stars everywhere, and this is only 10 arcseconds. And the situation gets worse and worse if we go to the quintuplet cluster or Arches cluster or whatever known structure that you have there. So even with high angular resolution observations of around 0.2 arcseconds, we are going to be limited and we will be able to observe just the giant stars. So particularly for Gaia, the problem is not going to be the sensitivity, it's going to be the crowding. And then my favorite problem there is the extreme extinction. So believe me, this is exactly the same region. This is visible, and behind what you have is near infrared. So yeah, if we go to the near infrared, you see that we have many, many stars there, but almost nothing in the visible. So this means that, unfortunately, Gaia is totally blind, so we couldn't use Gaia at all, which is a pity. But now the situation will change with Gaia NIR, hopefully, if this happens in the end. So now let's discuss a bit the key points that we need to take into account for Gaia NIR in order to observe the galactic center. So let's start with bad news first. So parallaxes, at least star by star, are not going to be useful because the galactic center is too far. So my dream at the very beginning, when I first learned about Gaia NIR, was to try to do something similar as what some people have done for the California cloud or other nearby clouds. And it's basically to determine the 3D structure, as you are seeing here. So it's really, really great, but you need good parallaxes for this. And the key point here is that this cloud, the California one, is at only 400 parsecs from the Earth. At the galactic center, we also have plenty of gas and dust in what we call the central molecular zone. So this is a very dense accumulation of gas and dust with more than 10 to the 7 solar masses of dense and cold gas there. And the thing is that we don't know the structure. So having good parallaxes there would have been really, really useful, but the problem is that the distance is 20 times larger, and then the individual uncertainties that we expect for distances there, even having amazing parallaxes, like 8% uncertainty, it's going to be 600 parsecs. So remember that this structure is relatively small, so the radius would be like 150 parsecs, so we cannot really say anything meaningful, which is a pity. Then another thing that we need to consider is this crowding problem that I mentioned before, and then for this we need to pay attention to the angular resolution that we expect for Gaia NIR. So the thing is that the angular resolution will get worse if we go towards longer wavelengths. And particularly, we are going to be interested in this regime here because the effective wavelength for the stars there at the galactic center will be quite red because we have a lot of extinction, as I mentioned before. So the thing is that if we are not too optimistic, because the mirror that I'm considering here is something around 1.5 meters, we will get an angular resolution of around 0.20 something arcseconds, which is relatively good and it's decent, and we can do many things as you will be seeing. So then another thing that we need to take into account is the pixel scale, and this was actually the question that I asked yesterday. This pixel scale will be more or less 0.1 arcseconds, so then we need to be careful with undersampling here. So this is just to illustrate what happens when we have a telescope with a mirror of 1.45 meters, like Gaia now, and then an effective wavelength for this broadband filter that we will have for the proper motions of around 1.7 microns. So if we have two stars separated 0.3 arcseconds, we will be able to resolve them. So no problem, and I think that the proper motions will be really, really good. But then if we decrease a bit the distance between the stars, we will get some problems because here you can see that they will be a bit mixed, and yeah, that's problematic for the uncertainties. So what I have done now is to go to the central region of the nuclear stellar disk, and I have used the state-of-the-art catalog for this region. It's a photometric catalog, galactic nucleus, and we are pretty complete there, up to KS 16, more or less. And what I have done is to take into account a luminosity function with all the stars in gray, and then all the isolated stars, and by isolated here, what I mean is that they don't have any close neighbors at a distance of 0.3 arcseconds. And this is the completeness that we can get with that. So we are really, really complete here, almost 100%, and then we are going to be always above the 80% completeness limit, which is really good. So we can really trace many stars in the nuclear stellar disk with this angular resolution that is a bit pessimistic because it's a relatively small mirror, and it can be even better in the future. The only problems, my only concern maybe is when we go towards the innermost regions, particularly the nuclear star cluster. So this is the effective radius of the nuclear star cluster, and here with all the stars in galactic nucleus, you can see that we have some structure here. But then those are the isolated stars, and this is the same color scale. So we are missing some structure maybe, and this is even clearer when we go to the subtraction between all the stars and the isolated stars, and you can see how this is the residual. So we will miss something, but this is not critical, and this region is really, really bad. And then again, the angular resolution that I consider here is a bit conservative. So the situation will be probably much better. Another interesting problem is the potential chromatic shift, because the thing is that we will be using a broadband filter for Gaia NIR, and then it means that the effective wavelength of the stars will be changing depending on the extinction. And as you can see here, when we go to J-band, we are not seeing too many stars because the extinction is really important there. It's going to be affecting J-band. But then as long as we continue and we go to H and K, we are increasing a lot the number of stars. So many of the stars there will have different effective wavelengths, and this is something that we need to take into account for this chromatic shift. If we have something with low extinction, the centroid will be a bit shifted in comparison to something with a higher extinction there. So that's why it's really fundamental to have, if possible, simultaneous near-infrared band observations here to know exactly the color term there and being able to correct this potential effect. This can be also done with spectra and also, of course, with previous catalog, but the thing, having simultaneous near-infrared band observations will be really useful because we also have a lot of variability here due to the extinction and the clouds that we have, and also intrinsically to the stars. So what we have estimated is that more than 50% of the stars at the galactic center can be variable stars, and that's why it's also important to have these simultaneous observations. And now that we know a bit more about Gaia, let's try to find out the questions, the main science questions that we could solve with this, but taking into account that the main role of Gaia in the galactic center will be the high precision proper motions. And just to give you an idea about how good these proper motions will be, I wanted to compare them with the best proper motion surveys that we have now. So this one is an HST survey. The only problem of this survey is that the region is quite small, the coverage, but the uncertainties are quite decent. So here you can see the error in one dimension for the proper motions. And then this is something that we are working on now. So it's a follow-up of the galactic nucleus survey. And with this, we will get high resolution proper motions. And this is just for a test field that we have already reduced and tested. And we will have the whole central region of the nuclear stellar disk. And the uncertainties are also pretty good. But this is what happens when we go to Gaia NIR. So don't try to find the line because it's basically 0. So this is the best case scenario with uncertainties around 0.010 milliards per year. And this is, if we are a bit more conservative, 0.050 milliards per year, which is really much, much better than whatever we have now. And we will be able to get this for almost all the stars up to KS 17. So this is really mind-blowing, and it will make a huge difference. And then the questions that we can try to tackle with this, so this is of course an incomplete list, but they are related to what I'm doing now, so that's why I chose them. So they are basically to understand a bit better the relationship between the galactic bar, the nuclear stellar disk, and the nuclear star cluster, which are the structures that we have at the galactic center. Then we can also say a lot of things on the formation scenario of these structures, which is really not well understood now. And then we can also try to find young stars and dissolve clusters and associations. So I will briefly describe more or less how to tackle these questions with proper motions. So the first thing here is that we need to take into account, to distinguish between the galactic bar and the nuclear stellar disk, we need to know that the bar is basically a hot kinematic structure. So this is an example of what we find with stars from the bar there at the galactic center. So they will have a large scatter, so the velocity dispersion will be relatively large. And then when we go to the nuclear stellar disk, it's going to be the opposite scenario. We are going to have something cold, and then with proper motions, we will be able to constrain memberships, at least giving probabilities to a given star to be part of the nuclear stellar disk or the galactic bar, and this will be really useful in order to trace and distinguish what's happening with these two different components. Then another thing that we can do, and we have already done this, but with relatively bad proper motions, they are not bad, but we are limited by what we have now, it's to determine orbits there. So for this, we have used a spectroscopic survey. So we have radial velocities here. We have the proper motions from Virac 2. And we imposed a constraint of 0.6 milliards per year for the proper motions. And this gets rid of many, many stars there. So we just have like 1,000 stars to be able to compute orbits for them. So this is a limiting factor that will be much better with Gaia NIR. And then, of course, we need to assume a gravitational potential. But this is the limiting uncertainty now. Well, of course, we have different orbits. We have fish orbits, bananas, pretzels, and the X2 parented orbits are dominating because we are going to be dominated by the nuclear stellar disk in this region, and those are the orbits that matters. But the thing with Gaia NIR, the uncertainties will be much better, and actually they are even better than the uncertainties that we will get for the radial velocities, which are much better constrained. But with Gaia NIR, proper motions will be the dominant factor, and the uncertainties of the orbits will be much better, and also we will be able to determine orbits for many, many stars. So as I mentioned before, tube orbits are going to be dominated, so they are related with X2 orbits. And if we create this density plot, we see how we have many, many stars following these kind of orbits at the central part of the nuclear stellar disk. And if we go towards the edge, we will have less stars with these orbits, because we are going to be dominated not by the nuclear stellar disk, but by the galactic bar. And the opposite situation happens when we go to chaotic orbits. So we don't have too many at the center, but we will have many more at the edges. So just with orbits, we can also get a way of distinguishing between the galactic bar and the nuclear stellar disk. And on top of that, another thing that we can do is to combine everything with metallicities, given different surveys that we have, and particularly a KMOS public survey that we just got approved. It's called BBPX GALSEN. And with this, we will get spectra of more than 40,000 stars at the galactic center. So we can combine everything and really get the distribution of metallicities for the different orbits and relate them with what we are getting for the nuclear stellar disk and the galactic bar. So combining kinematics plus chemical analysis, we will get metallicity distribution, we will get information about the formation scenario, and we will get to know more about the relation with the galactic bar. And then the last question that I wanted to discuss a bit is how to identify young stars there. So we have a key problem at the Galactic Center, and it's what we call the missing clusters problem. So we have indirect measurements, and we know that we have many, many young stars at the Galactic Center, but we don't know where they are. We don't know who they are, actually. The only things that we have is two massive clusters, arches and quintuplet, here and there, another young stellar cluster at the nuclear star cluster, and some tens of stars here and there of young stars, but not too many, and this is not enough to account for the number of young stars that we know that we have there. So using proper motions, we have tested and published a method in order to get co-moving groups of stars that are going to be tracing this young star population, because all these young star associations will be sharing a common proper motion in the end. And the thing is that now we have this restricted to small areas in which we have good proper motions, and with Gaia NIR we could apply this technique to the whole thing, so that will be a step forward there. And finally, the last thing that I want to say is that spectra are also very important to detect young stars. So this is an example of what you can get with KMOS. And the thing is, just with a K-band spectrum, what you can do is to use the CO band head absorption to distinguish between an early type star and a late type star. Because here with the late type star, you will see this CO band head absorption. So that's why spectra, also in Gaia NIR, at least low resolution spectroscopy, will be really fundamental, because we can get also information star by star, and we can have good candidates to be young stars there at the Galactic Center, which is really fundamental to understand how star formation happens in this extreme environment. And with this, I would like to conclude. So my take-home message is Gaia NIR will provide really high proper motions for the Galactic Center, and this is key. We will have nice synergies with previous surveys that we are developing now. And then the main thing is, if it works for the Galactic Center, it will work everywhere else, because it's really the most challenging environment in the galaxy. So it's a good template to be taken into account to prepare the whole mission. So with this, thank you very much, and I'm happy to take some questions.
Very well.
Thank you.
On time. We have time for 2 questions. Go ahead, Alessandro. Okay.
Sorry. Thanks for a very nice talk. This is very interesting, and actually with the white paper that we're working on at the moment, we're just starting to look at now the crowding issue in the Galactic Center. So maybe if you could send me an email afterwards, we involve you in reviewing and contributing to that part of the paper. It would be quite useful to get your input there.
Thank you.
Thank you.
Thank you very much.
I'll try to be quick. On one hand, clearly the very last point is crucial, right? If you want to define a survey, you start from the worst case scenario, and this is perhaps...
Welcome to the Galactic Center.
Yes. And so the other question, bear with me if I try to play devil's advocate. What about using JWST? Because it's naively, one will assume 6-meter telescope. You can observe the Galactic Center for 10 years, 15 years. Would that be competitive? I don't know.
There are 2 things here. So the first thing is that we have submitted a community proposal for JWST. It's a large program for the Galactic Center. We have many different goals for that, young stars, extinction, whatever, but proper motions are really crucial here, because we can use JWST, the angular resolution is really good, and the only problem is a bit of undersampling here and there, but still, so it's something that we can do. Maybe the main problem in comparison to Gaia NIR would be the reference frame, because here with JWST you can really get very nice relative proper motions. You will be constrained by the number of epochs, which is also important to be taken into account. But then the thing is that you will need, if you want to get absolute proper motions, you will need to rely on Gaia, probably. And that's the approach that we are taking now with the Galactic Nucleus Survey that Rainer is leading, and he will say something probably now. But yeah, the thing is that we are using Gaia, and we are limited because we have just tens of stars there. And with Gaia NIR, you will have an absolute proper motion for whatever star you like. So that's really game-changing.
If I may say something rapidly to JWST, there is a white paper out there about a JWST survey of the Galactic Center. and it's a community effort. So we try to get this as a treasury program. Anyone is welcome to join at any time. I'm happy you say that. We hope that the JWST TAC would see it also as way, because we all think it's obvious to use the JWST in the Galactic Center, but we have asked for 140 hours. It's a minimum we need, and we don't cover everything that we want, because it's very inefficient, JWST, it's a problem. And of course the TAC always wants high redshift and everything. So if any of you sits on the TAC, please.
Please.
And is not on the proposal, please help us. It's been already 4 times we put this in. It's always highly ranked, but of course, I mean, if you have an oversubscription of a factor 10, it's very hard to get this. Other point is things like binaries with black holes, and so that would be a very strong case for Gaia NIR infrared, because you just get a much better sampling. James Webb, if we're lucky, we get 2 epochs. Thanks.
Okay, let's go ahead. Thank you, our speaker. Okay, our next speaker is Marcin Samsuk, who will talk about kinematic fractionation of the Milky Way birds.
Okay, thank you very much for the introduction and for organizing such an interesting meeting. I will talk about some of the work I did on the Milky Way boxy peanut bulge a few years ago, but I think it's still relevant in the context of what Gaia NIR can help us understand. So, first of all, when talking about the Milky Way bulge, it's interesting to think of the context, because for different authors, the bulge means completely something else. So in the observational perspective, in the survey perspective, it's quite simple. It's just this inner field of the disk that is thick and has a lot of stars and a lot of dust. But from a physical point of view, I think it's a bit more complicated, and there are several galactic stellar structures overlapping there that are also obscured by dust, so we know only some partial things about them. So first of all, the biggest structure is the galactic bar. I think now this is a fact, it's a consensus that Milky Way has a bar. As you can see here on the right, as in extragalactic, the bars, they have this associated vertical boxy peanut structure, so you can see it in infrared. But I will talk a bit more on that later. Inside the bar is the nuclear stellar disk that Francisco already nicely covered, so I'll not go too much into that. And recently there have been these new claims that besides the bar and boxy peanut bulge, there is some kind of classical bulge in the Milky Way. So they found, several groups, they found this very metal poor, non-rotating stars. They have the extent of 1 to 2 to 3 kiloparsecs. So conceptually, this is something that would be called the classical bulge. On top of that, there have been claims on the other extreme of the metallicity. So the structure that is called metal-rich knot. So this is very metal-rich stars, also extending on the kiloparsecs scale on very hot orbits. So as we have some ideas how the classical bulges are formed, this is very new and very interesting. There is not much on the theory side how this forms. All of this is obscured by dust, so we don't have like the full picture. We only see some field of view here, some fraction of stars there. So we definitely need Gaia NIR to fully understand how this all works. So going to the biggest part, to the bar and the boxy peanut bulge, external galaxies that have bars and in the Milky Way-sized galaxies, majority of them have this boxy peanut bulges. So this is pretty common. It's not surprising that the Milky Way would have it. So it was first seen in the COBE imaging in near-infrared, and here you can see. Did someone say something? No. Yeah, so here is a nice plot from WISE that you can see the boxy peanut bulge. But this is only the face-on view, the edge-on. So to add the third dimension in red clump stars, in the reddened magnitudes, you can see the split that depends on the height above and below the disk, as the models of boxy peanut bulges predict. And besides only just the density distribution, in the VVV data cross-match with Gaia of red clump stars, if you correlate the proper motions L and B, then they also have this X-shaped structure that's also orientated with the bar. So there's also kinematic signature of the boxy peanut bulge. If we go to the simulations of boxy peanut bulges, every simulation that I know of that have boxy peanut bulges and star formation shows that the boxy peanut bulge can look very differently in different stellar ages. So here you can see from the oldest to the youngest, there's a continuous change in morphology. So the oldest stars, they have this boxy shape in the outer parts and the small linear peanut, and going to the younger and youngest, then the outer X dominates and the inner part is more round. Again, this is very common in simulations. I think it would be very weird to have a simulation with star formation and boxy peanut bulge looking exactly the same in every population. So this is, and this is what this difficult term in the title of my talk, the kinematic fractionation, that was first used by Victor in this paper. So in this video from my simulation, you can see how this happens. So in the top, you have the oldest stars face on and edge on, and lower is one being younger and younger with 1 gigayear. So when the simulation starts, the disk forms the bar, and associated boxy peanut bulge arises in vertical direction. And then with time, the younger populations, they follow the same evolution, but the oldest one heats up, and the initial peanut becomes boxy, and then the same thing happens for the younger populations, just offset with 1 gigayears later, so they have less time to heat up. In the inner parts, this inner peanut remains the same, and later when the bar forms, the star formation is limited here, so there's not enough stars to probe these orbits. So there is just the nuclear star disk there left, and we don't see this inner peanut in the inner parts. So this is how it looks at the end. One way to quantify this is to look somewhere above or below the galactic plane and make a cut and measure the distance between these two overdensities of the peanut, and with age, from old to young, they spread out, the size increases. It's different at different heights. If I make a slice at y equals 0, then you can see it clearly that going from red to blue, from old to young, this continuously increases the separation of the peanut, measured that way, which was already somehow seen in the Milky Way before the simulations. So going back to the red clump stars, in this work of Melissa Ness and her colleagues, they looked at the split in different metallicity bins, and they found that the most metal poor in their sample, they don't have the split, and the two metal-rich bins, it looks a bit different. So this is not exactly the same picture from simulations, because there are projection effects and other observational stuff, but there are some hints that this is happening in the Milky Way. So I had a look at this using variable stars. So the first set of variable stars that I used were Lyra. Yesterday we had a nice talk introducing Lyra by Giuliano. In the individual star evolution, the consensus was that they are mostly old. Giuliano said that in binary evolution they can be a bit younger, but we don't know really how often which one happens. So especially in the bulge, I would think that most of them are very old. When looking at the bulge in Lyra stars, there is a bit of a debate whether they've outlined the bar or this spheroid, this classical bulge. So there are papers claiming that sometimes using the same data set that they see the bar that's elongated and inclined, or that they see the spheroid. I think last year there was a very nice paper by Prudil et al. That shed a bit of light on that. So while making this kind of maps of a Lyra in the bar region, the distance errors of this of stars here, they are of the order of 0.6, 0.7 kiloparsecs, so 1/3 of this plot. And the major component that contributes to these errors is the extinction. So in this paper from last year, Prudil et al. They adopted different extinction laws to the same sample of error Lyra, and they found that depending on the extinction laws, they were showing the oriented bar with the bar angle similar to what we see in the red clump stars and other populations, or in other extinctions map they would see something that's aligned with the line of sight and more symmetrical. In this paper they say that, okay, using their favorite extinction map, that is the best, and splitting it into metallicity, they still see that the metal-rich error Lyra, they have a spherical shape, and the metal poor, the metal poor, they still have the spherical shape, and the metal rich still have the oriented bar with the bar angle. However, going a bit deeper than just density distribution, the strongest evidence that the error follow the bar comes from proper motion. So this is independent of the extinction maps. In proper motions, you see that there is a rotation, and in the spheroidal component there wouldn't be in the VL. Also splitting in metallicity, there is some gradient in how much of this rotation is. So maybe this metal poor component is contaminated by the non-rotating part. So knowing all of this, in 2022, these issues with the extinction, I had a look at just the on-sky distribution of error Lyra. So I chose from Ogle survey like a rectangle that doesn't have a footprints of the survey. So it's a complete sample of error Lyra, and I found that they do have a boxy peanut shape in this on-sky projection, just as predicted from the simulation. So there's a minimum that's statistically significant. However, projecting this into the linear size, it is a few times smaller than known from red clump stars and infrared, which agrees with the predictions of the simulations that the oldest stars, they have very small peanut, and going to the younger and younger, that will be traced by red clumps, it grows with size. Later I used Myras from Ogle. So Myras have this nice dependence that binning in period can give different populations in age. They have age-period relation. Taking the whole sample of Myras, they found that the 3D model with the X-shaped bulge fits better. So the whole sample of Myra have an X shape. Now going to the predictions of simulations into this rectangle below the galactic plane, using Auriga simulation this time, I see here that if I add some cuts in the galactic longitude, then the oldest peanut, that's this very small concentrated part, will be fully covered by this rectangle. But going to the younger and younger, as the separation grows, the inner lump will be cut by the limit. So on sky, the outer part will be dominating more and more the on-sky distribution. So you can see this here. There is just gradual shift predicted with ages from old to young. And looking into Myras, there is also such a shift. So the oldest Myras, they are concentrated around 0, and going to younger and younger, there is a shift with periods to the right, as predicted with this age morphology dependence of the boxy peanut bulges from the simulations. Right, so to summarize this talk, the bulge is very complicated. There are several stellar structures overlapping there. They are different in terms of kinematics and chemistry. The biggest structure that is known for us, the bar, itself, it looks very different. It can look very different in different populations, as simulations show, and as I shown here in Lyra and Myras, in comparison also to the red clump stars. Yeah, we need Gaia NIR to have more data there, better data to see what's there, and also until Gaia NIR, we need to make some theoretical efforts to understand the galaxy evolution, how quantitatively all of this depends on the growth of the disk and the evolution of the bar. So that's it. Thank you.
Okay, so we have time for questions. Go ahead.
Thank you, Marcin, for the nice talk. So in your talk of 2022 with Terra Lyra, did you check if there is any trend with metallicity?
Yes, they look differently, but splitting in metallicity, it reduces the number of stars, so it's hard to claim that it's statistically significant, the difference.
But the difference is in the direction, like being younger?
So with the distances,
Yeah.
so if I do this plot with the distances, okay, the metal poor, they have something similar to the simulations if I would add some smearing to the simulations, and the metal rich, they have something that doesn't show signatures of the peanut, but again, using distances is a bit complicated because the errors here are significant. Yeah.
Thank you.
More questions? Okay, so let's thank our speaker again. And now we have a talk by Giuseppina Battaglia that will tell us about how Gaia NIR will help us to understand the local group of 12 galaxies. Thank you.
Yes. How do I start the presentation? I think it was one of the PDFs.
Espera. Compartiendo en Zoom. Voy. Ahora sí. Vale. Ahora sí.
Vale, gracias. So, good morning. So what I would like to discuss today is how Gaia NIR infrared can impact our understanding of galaxies in the local group, drawing first from our current experience. So just quickly, even though Guillaume Thomas introduced them today, just a brief reminder of the kind of systems I will be discussing. So this is a picture of different types of local group galaxies, dwarf galaxies that are in the local group. A characteristic is that they cover a range of stellar masses that is quite wide. We are discussing systems with the stellar masses below 10 to the 8 solar masses down to something as small as 1,000 or even smaller. And then another defining characteristic is that of the about 100 dwarf galaxies that we have nearby, within 1 megaparsec, the great majority of them are distributed around the Milky Way on M31, so are satellites of a much larger host system. So why do we need accurate and precise proper motions? So I see it a little bit in two different parts, and this is also how the talk will be divided. So first of all, we have a clear need of deriving systemic proper motions to have the ability of having or knowing the 3D velocity of these galaxies, and therefore being able to turn this into an orbit around the host system. Because given their vicinity to the host, it's obvious that pericentric passages can affect their gas content, structure, internal kinematics, star formation histories, and so on and so forth. And then, of course, another concern, or potential concern, is whether tidal disturbances are somewhat altering the inferences that we make of the dark matter content and distribution of these galaxies. Then there are also some other aspects that one can explore with 3D systemic velocities related to other near-field cosmology questions, like, for example, whether some of these dwarf galaxies came in together as a group, and especially whether actually some of them were former satellites of the Large Magellanic Cloud and not of the Milky Way, or also explore the stability of features that we see around the Milky Way and M31. There is this plane of satellites, which are quite difficult to reproduce in lambda CDM. And then the other aspect is actually the need for accurate and precise 3D velocities of individual stars, not only to study the internal kinematic properties of the systems, but especially, at least from my perspective, the interest is to be able to make the best inferences that we can of the dark matter halo density profile of these galaxies and learn about the nature of dark matter. So concerning the first part, already the current data releases of Gaia have really implied a leap forward in our ability of recovering the 3D motions of these systems. So before Gaia NIR2, these kind of estimates were available for 11 dwarf galaxies in the local group. And now, with the Gaia NIR3, essentially, we have provided these estimates for 73 dwarf galaxies out to a distance of 1.3 megaparsec. Of course, for full transparency, when you turn these systemic velocity measurements into, these systemic proper motions into tangential velocities, the kind of uncertainties that one obtains is widely different depending on the distance of the galaxy, but also its luminosity, because this essentially impacts the number of stars bright enough to be above the Gaia detection limit. So for this sample, where we are covering almost 2 orders of magnitudes of distances, then we have systemic tangential velocities accurate to about 1 or 2 kilometers per second for the nearby systems, out to several hundreds. So this is clearly, for the moment, just a proof of concept for these systems, and those for which we can derive orbital measurements, orbits around the Milky Way, are indeed those within 400 kiloparsecs around. Before I move to the actual result, one realization of the past years has been that when you want to derive orbits of the systems around the Milky Way, it's very important to take into account the perturbation that the Large Magellanic Cloud is introducing, because nowadays we think that the dark matter halo of the Large Magellanic Cloud can be up to 1/10 or 1/5 of the one of the Milky Way. So it's really a strong perturbation. And so here there are some examples of orbits for 3 satellites derived, not including in orange, including in light blue, these perturbation self-consistently. And it is obvious that including it has a large effect. For example, the orbits can in some cases become more external, in other cases can become more internal, and in other cases can really make the difference between having been a long-term satellite of the Milky Way or having been just recently accreted. One of the aspects that we and other teams have explored with this kind of information has been, for example, whether some of these systems belong to the Large Magellanic Cloud instead than being satellites of the Milky Way. And so this, for example, we did it analyzing the orbits of these galaxies around the LMC, comparing their 3D velocities with the escape velocity from the LMC as a function of time. And so what we found is, for example, that there was one system, GROS2, that apparently was recently captured by the LMC, and then other 6 systems, of which I'm showing here 2 as an example, which are very likely to have been former satellites of the LMC, and then other 3 which possibly were also former satellites of the LMC. So of the counts of galaxies that we see around the Milky Way, possibly about 10 of them actually came from the LMC. Then once we have assessed which of these dwarf galaxies are not part of the count of Milky Way satellites, so we take them out. Then with the information gathered, we have a complete picture of the orbital properties of the rest of the galaxies around the Milky Way. This is a BC plot, it's just a summary of the pericentric distance for all these dwarf galaxies. derived with the 3 gravitational potentials that we are exploring in this study. But so what I want to say with this transparency is that now we are in the conditions of actually assessing in a very detailed and comprehensive way and systematically what is the impact of tidal disturbances on the systems and assessing how much they alter our inferences of the dark matter halo density distribution. Because what we can do is to run n-body simulations of systems, placing them on observationally motivated orbits, study the remnant and compare it to detailed observations that we have, like, for example, the 3D distance, the 3D velocity of the system, the stellar surface number density profile, the velocity dispersion profile, okay? And then apply the dynamical modeling to these simulated objects as we would do on the data, and then understanding what our biases are. And so together also with Giuliano, we performed this kind of analysis for 2 of these galaxies, Sculptor and Fornax, and actually we found that on observationally motivated orbits, our inferences of the dark matter halo density profile are quite robust, okay? This will not be the case for all these galaxies, obviously. Each of them needed to be treated separately, but we have the ability to make this kind of assessment. And then finally, another outcome of this type of analysis that we can assign a probability of membership to individual stars. Sorry, Mina, did I have 5 minutes more? Okay, thank you. So probability of membership, so what people have done is to explore the existence of extended features around these galaxies and found that there are probable members out to sometimes 10 or 12 half-life radii, which is unexpected, even for galaxies for which the orbits don't tell us that they are tidally disrupted. And so this raises another interesting possibility that perhaps these extended features are actually stellar halos, okay, seen on the scale of dwarf galaxies, so the results of hierarchical accretion. So this is something exciting. So what could the Gaia NIR infrared do for improving further the picture? So this is the current situation for the precision in systemic transverse velocities, and this line just guides the eye towards 10 kilometers per second. This is what the Gaia DR4 can do for us, and then this is what our estimates would be for Gaia NIR infrared. So this would be absolutely amazing. It would imply putting the further away local group galaxies at 1 megaparsec to the same level of precision that we have now for the most nearby Milky Way satellites. And then very quickly, I'll move to the second part of the talk. I will try to be as short as possible. One very interesting feature of dwarf galaxies is that they have enormous dynamical mass-to-light ratios. They range between 10 to several thousands, okay? So these are the most dark matter-dominated galaxies we know of. And this kind of inferences of their dark matter content is practically completely derived from the line-of-sight velocity distribution of the stellar component, because these galaxies are essentially devoid of gas, so we cannot rely on the gaseous component. They are mostly non-rotating, okay, so we need to quantify the random motions. And these random motions are just of a few kilometers per second, so this is precision work. So people have, of course, tried to determine the dark matter halo density distribution of these systems, and here are the 3 best-studied Milky Way satellites, ordered for increasing luminosity. And the bands give results from different studies. So some trends are emerging in the sense that the faintest systems seem to live in steeper dark matter density profiles than the brighter ones, which could be compatible with lambda CDM plus the impact of baryonic effects. However, it's also very clear that there are discrepancies between different studies, and essentially results of applying dynamical models to mock data sets, which would be, for example, this plot, make us understand that this is to some extent due to the way the different dynamical modeling techniques, here depicted in the different colors, are coping with the fact that we only have line of sight velocities, okay? Even though we have samples of 1,000 line of sight velocities. And the holy grail would be to have proper motions accurate enough to be able to have tangential velocities of a similar accuracy. So this, you see how the situation would change when you add 1,000 tangential velocities of precision of 2 kilometers per second. Then all the techniques, or most of the techniques, yield essentially the same results, and they are spot on the right answer. The situation now is the Gaia, the precision with Gaia data is not sufficient to be able to have these accurate tangential velocities. So people have combined, for example, Gaia data with HST, or HST data with different, very different time baselines. However, of course, we are limited to the field of view of HST, which is very small with respect to the full extent of the galaxy. So, and even though I'm skipping some of the details, I just wanted you to have this last slide on what is the outlook. For example, if we take the same galaxy, Draco, shown in the previous slide, for a Gaia DR4, we expect to have of the order of 8 stars with a tangential velocity precision of less than 10 kilometers per second, and none with less than 5. With the Gaia DR5, this would become several hundreds with precision less than 10 kilometers per second, and just about 20 with less than 5 kilometers per second. The velocity dispersion of this system is around 8 kilometers per second. However, with Gaia NIR infrared, then we will be having more than 1,000 stars with velocity precision less than 5 kilometers per second. So we were really having our ideal data set for dark matter inferences. And for systems like Fornax, we would be in this unprecedented situation of having really an overwhelming number of stars with very large precision. So to conclude, I think Gaia NIR infrared would be really transformational for this kind of studies of local group of galaxies. Thank you.
Thank you very much, Josefina. So we have now time for questions. Any question? Go ahead, Jose.
This is a question from an absolutely non-expert. When you make your simulations and you have the orbits around the Milky Way or LMC, are you able to compute the eccentricities, the orbital eccentricities of the satellite galaxies?
Yes, yeah, of course. I mean, of the system itself, you mean? Yeah, of course.
What is the range of eccentricities?
Well, I mean, these are somewhat imposed, right? Because, I mean, we already placed them on... Fornax is rather circular, I think, for the most likely values of the 3D velocity. Then you have other systems in which you can have an eccentricity of 0.5, 0.3, so it's really dependent on the type of system.
I am asking about these individual proper motions for individual stars inside Fornax. The precision on proper motions without radial velocities, imagine, a lot of proper motions in Gaia NIR, but not as much radial velocities. Do you have some simulations, I am thinking now in Harkonnen, do you have some simulations saying that even in this case, with only proper motions, can you distinguish between cold, warm, fuzzy dark matter? Is able to distinguish? Thinking in the science case, can we think in a science case, because you have 99% of dark matter, let's say, thinking on the dark matter you need for the dynamical analysis?
Sure. I'm not aware, but I might be mistaken of a simulation done only in the case. I think the power is really having the 3D information. But the spectroscopic part is not an issue because already for these galaxies we have several hundreds or 1,000 or 2,000 in some cases velocities with this kind of precision. And with the weave, foremost, etc., we will gather even further. So what is really missing is really just the tangential velocities from the proper motions.
Okay, so let's thank our speaker again. Our last talk of this session is about kinematics of the Magellanic Clouds by Oscar Jiménez Arranz. Yeah. Let's see, okay. Do you know how?
Stop here.
Sure, okay. Here we are.
Sí, sí, ya está. Sí, sí, ya se ha hecho. Sí, sí, ya está conectado. Sí, sí, ya está compartido, Empieza así. ¿No?
Ah, que
¿No es
empieza
eso?
en negro.
Sí, sí, empieza en negro.
No lo pones fácil. Vale, ahí está.
Sí, sí, está bien. Gracias. Okay, so let me start by telling you a story. Back in the day, I used to be a first row student, not because I was super interested in the lectures, but because I was not able to see very well what was written on the blackboard. Even though it was long time ago, I perfectly remember the first day I went to class with my brand new glasses, and all these blurry shapes became like very sharp lines, no? So this is somewhat similar to what happens to the internal kinematics of the Magellanic Clouds thanks to the launch of the Gaia data. So you can imagine my excitement about the future, the launch of the Gaia NIR mission when this happens, to see improved kinematics. So in this talk, I'm going to address how we see the Magellanic Clouds with high-resolution glasses, or more specifically, how Gaia NIR is going to improve on the internal kinematics of the clouds. So first of all, I'm going to start by introducing the two main characters of this presentation. We have seen this image plenty of times today. However, today I'm not going to focus on the Milky Way disk, but in these two overdensity of stars, that is the LMC and the SMC. And if we make a zoom in comparison, in order to see like how good Gaia data is with respect to other external galaxies, this is how Andromeda Galaxy would look in Gaia data. So we can see that the LMC and the SMC, those are like very bright and big satellites of the Milky Way. If we make a zoom-in version of these images, and let's introduce one of these characters one by one, about the LMC, what I would emphasize is that it's a dwarf galaxy with a total mass of 10% with respect of the Milky Way. Secondly, it is a disk galaxy, and it's not face-on with respect to us. It has an inclination of around 30 degrees, more or less. Secondly, there are some clear signs of disequilibrium. First of all would be like the one single unbroken spiral arm, and the secondly will be like an off-center and out-of-plane bar. We change now the focus, and we go into the small sibling of this couple, the SMC. I would say that this was another dwarf galaxy of 1% total mass with respect of the Milky Way. However, it is a dwarf irregular galaxy, so the stars do not line in a plane. So this means that when you check on the line of sight, it has a distorted shape. I think it's something that we have addressed during these days. And secondly, there is some clear signs of interaction. For example, this Magellanic Bridge, which is some flow of stars from the SMC towards the LMC. So now, if we see this system as a whole, I would like to emphasize two main things and why we should care about the LMC and the SMC. First of all, again, those are the closest galaxies of the Milky Way. So this means that thanks to Gaia, we have availability of astrometric information for tens of millions of stars. And secondly, on top of that is that we can see stars across the whole disk. No? In the Milky Way, we live inside the Milky Way, so we only see like this 1% of stars, which is a biased sample of the whole disk. However, here we can see the disk as a whole. And secondly, and as I was saying before, those are in strong interaction, so this means that we are taking into account the LMC and the SMC to be the perfect laboratory for testing methodologies and models designed for the study of external and interacting galaxies. So now I would like to address, first of all, what we have learned with Gaia, and then I will address what we want to learn with Gaia NIR. So in here I would like to emphasize three different scientific cases going from the inner part of the LMC towards the outer regions of the LMC. First of all, the story begins, I would say, with maybe Gaia NIR 2, where here is how we can see the internal kinematics and parallax of the LMC. Here on the left we have parallaxes, and on top and right proper motions, and in here we were able to see some imprints of the scanning law of Gaia. No? This, however, improved with Gaia NIR 3, and we were able to see how this sawtooth pattern slightly disappears, and Klaus showed how for the Gaia NIR 4 the parallaxes will improve even more and erasing this kind of patterns. So this was published as a part of one of the PVPs of Gaia NIR 3 by Gaia Collaboration and Xavi et al. 2021. And again, here I would like to emphasize that in parallax we get lost this sawtooth pattern, and kind of similar happens for the proper motions. So by taking all this into account, we're able to make clean LMC samples, so removing Milky Way foreground contaminations, and get clean samples of LMC stars only, no Milky Way contaminations, or very few Milky Way contamination, of the order of 12 million LMC stars. So yeah, we have like an excellent data set in order to study this sample. So what have we learned? No? First of all, again, I'm going to go like very deep into the inner regions of the LMC. So I'm going to study how the frame rate. We are going to study how the bar rotates. So this is related to what we saw, yeah, exactly, yesterday with Santi Rocafabrega's talk. No? We were able to get this kind of kinematic maps to of the LMC. And we are able to apply this Denem method, Sensum method, et al. In order to infer the LMC pattern speed. So when we mask and go into the LMC bar region, what we recover is a pattern speed of -1 plus minus 0.5 kilometers per second per kiloparsec, compatible with a non-rotating bar. No? This is something that we address later with simulations and see that this is possible due to the interaction between the LMC and the SMC. So this is one of the first results we have learned with Gaia data. Secondly, if we go slightly more into the outer disk, or the outer region of the LMC, we're going to study how the disk is shaped. No? So thanks to Gaia data and SDSS5 data, we are able to infer which is the 3D structure of the LMC and the SMC. So here what I'm showing is like how the inclination and the line of nodes changes for different parts of the disk. And here what we can see is kind of this quadrupolar pattern, no? So blue, red, and similar for this pink, green, pink, green. So here what we are seeing is like the warp of the LMC disk. So by taking by this and then like making some three-dimensional models, we are able to fit and to make a representation of the LMC disk. So with this, what we learn is that the LMC is a disk warp. So again, we can take all this data and we can try to make these 3D models. And again, since this in the end is a model of the LMC disk, we're able to make a rotation and to see like how this looks like in reality. So here we can emphasize two things: that the inner region is slightly inclined with the rest of the disk. So this is like a warp bar, as we were saying before, and also the warp disk at the outermost regions. And lastly, I would like to go into the outskirts of even more into the outskirts of the LMC. So there have been like suggested few streams associated to Magallanes clouds, named 2S1 to S4. And here in this last paper, published at the end of last year, what we wanted to do is to take this sample of a star, candidate sample, this S3 stream, done and studied before Gaia NIR 2, like using only spectroscopic information. And what we wanted to do is like, okay, let's try to see first if those is really a stream, so check on the Gaia kinematics. And secondly, try to infer if there are like more stars candidate to this stream. So this is what we did. We'll train a neural network classifier, and we were able to go from this small sample of star candidates for this stream into this whole dataset. Later, we performed this analysis in order to see if this is really an LMC stream or a distant Milky Way stream. By performing orbital analysis, we saw that, in fact, this is a Milky Way stream. So yeah, still the hunt continues, but yeah, all this is information that we can learn thanks to Gaia. So now with this, I go into what we can learn with Gaia NIR. So first of all, regarding the bar, what I would like to say is that yeah, we can access off-curve regions. So again, here with Gaia, we're facing the problem that some parts are being obscured, so we don't have the image of the whole bar. So it's something that we can improve thanks to Gaia NIR and have better astrometry for that. Secondly is like across the whole disk, not only the bar, we can improve on the astrometry. There is some first work done by Marie already trying to quantify this using the Kratos suite of simulations. So in this work, what we did is to use this simulation set, simulate that we have a red clam stars at LMC distances, so 50 kiloparsecs, and to see how Gaia DR4, DR5 compares with different Gaia NIR missions. No? So again, here in this plot, what I'm going to show is like a function of the G magnitude, how the proper motion uncertainty changes, being shown as a solid line in mu alpha, and in dash lines as mu delta. No? So this is what we get for Gaia. So this will be Gaia DR4 and DR5 when we have errors of the order of 0.1 mass per year or 0.03 for Gaia DR5. However, if we go to Gaia NIR, depending if we have this M5 of L10 that David was explaining yesterday, we can drop like this uncertainty into much lower values. So thirdly, what I would like to say is that we can make an improvement on the LMC 3D structure, so by having better kinematics, more proper motions, more line side velocities. Also, again, time span is going to be longer, so we'll have like more variable stars, so we can able to infer the 3D structure in a different way. Fourthly, they will have a better characterization of streams at LMC distances. Either they are Milky Way or LMC streams. We will have like more proper motions, more line side velocity, so a better orbital analysis, and many more topics. So with this, I go into the conclusions. So again, first of all, I would like to emphasize that the LMC and the SMC are the perfect laboratory for testing methodologies and models designed for the study of external galaxies. Secondly, that Gaia DR3 is already providing more than 10 million LMC stars with proper motion information, some of them also with line of sight. The LMC in the inner region may host a non-rotating bar, and this is something that, as Santi said, we want to further address with hydrodynamical simulations. That the LMC disk is warped. And thirdly, that Gaia NIR can shed like light in more of these XMC feeders. So yes, with this I finish, and I will take the questions.
So go ahead with the questions.
Thank you, Oscar. Very impressive work. I was curious about this stellar stream that you mentioned that could be coming from the, from the accretion of the LMC system in general. But then you show us that it's not a stream, it's a bunch of stars. So I was wondering, had you thought about that maybe you have found the stellar counterpart to the stream, the gas stream of the LMC and the SMC system?
It's something that we would like to address in future works. Yeah, like to be honest, now we were like more focusing because again, no, this is a bunch of from S1 to S4 stream. So we started with S3, which was like the more clear one. So yeah, no, it's something that we have not looked very much in that. Yeah, we can talk about it later. Yeah, yeah.
Okay.
Thank you.
Well, to stay on the stream, do you have the distances of the streams that you discovered?
For the training set, it was like these 10 stars more or less by Camila Navarrete's sample, yes. However, they rely on the classification, whether they are BHB or BS, and those distances suggest that they are from 45 to 70 kiloparsecs away, so that's why they were considered an LMC stream. However, for the others, like we provided 1.5 more thousand stars that we don't have individual distances. Now we are proposing to have like more spectroscopic follow-up of this sample in order to get better distances. But no, for the new sample that we provided, we don't have any distance estimate. Yeah, we tried to check on the RLIRA catalog from Gaia, and there were only 2 stars, so it was not something.
Okay. Yeah, because there is a lot of streams that cross around the LMC at some point also with different inclination, different orbits. So yeah.
Thank you.
Okay, so if there is no more questions, we will finish, and we have now the coffee break. We should, let's say, Oscar, we should be back at, let's see, at about 10:50. 11:20, sorry, okay? 11:20, yeah, half an hour, more or less.
tú. No, pregunto. Ah. No, ya está. Creo que ya está. Sí. Sí, está activo. Perdón.
Que va a haber un cambio en el
Ah, vale.
Hello. I'm Ignacio Negruela. I'm going to be chairing this session. And first thing I have to tell you is that there's going to be a change in the schedule because Miriam is going to be postponed and probably she's going to be interchanged with Sarah or maybe with the last speaker, Manuel Perger, if we can get hold of him. This second session, we're going to continue hearing science cases for Gaia NIR, and the first speaker is going to be Gabriel Rodriguez Morris, and he's going to talk about relativistic modeling of astrometry. Please.
So thank you very much. Good morning, everybody. My name is Gabriel. I'm a PhD candidate at the Lorman Observatory in the Technical University of Dresden. So during the next few minutes, I will be talking about relativity and astrometry, and more particularly, like why or how relativity is involved in modern astrometric missions. And then also at the end of the talk, I will give some brief comments regarding the celestial reference frame and how it can be upgraded thanks to Gaia NIR. So to begin with, and just to give some context, it's important to know how relativity is involved in astrometry and why it became necessary. So with the advent of the Hipparcos and Gaia missions, achieving accuracies of milli and microseconds respectively, it became necessary to include subtle effects, for example, relativistic effects in the astrometric models that allow for the data processing. And so what's the typical scenario in astrometry? Basically, we have a moving observer in some reference system. So our satellite, for example, in the barycentric celestial reference system. And so it's receiving light rays from the sources we observe. So the two main relativistic effects that we have there, first of all, the first one is the motion of the observer itself. And this is related to aberration. So there's a Newtonian version of aberration, but the more exact one or precise one requires relativity. And then the second effect is given by the gravitational light deflection so according to the theory of general relativity, the light rays that come from the sources, so find some objects on their way to the observer, so planets, stars, asteroids, and the light is bent, basically, when one of the light rays, of these light rays passes close to some of these objects. So, yeah, this is the general scheme in modern astrometric missions. We have, so the relativistic effects are part of an astrometric model. This astrometric model is combined with other instrumental models, so for example, for attitude or calibrations. And these are used to process the data that we receive from satellite observations, and when we put all of these together, we get the astrometric catalog. So this means the astrometric parameters, light ascensions, parallaxes, and proper motions of each source. We also get attitude parameters, etc., but we are focused on the relativistic effects and how it affects the astrometric parameters. So the thing is that if we include or skip a relativistic effect in the astrometric model, it will imply a change in the astrometric parameters that we receive in the final astrometric catalogs. For example, we know that the light deflection by the sun it was one of the first known effects in general relativity, and it's important for most of the sources at the Gaia accuracies. So if we skip relativistic effects, so gravitational light deflection from the sun, we will get different astrometric parameters in the end, and this will come with some errors, because we are skipping something that we need to include to achieve the accuracies we would like to have. So currently, the model that is being used in Gaia is called, so in the astrometric model, is called the Gaia relativity model, or GRAM. And so it's based on the theory of relativistic reference systems. The foundations can be found in this 2003 paper by Clioner. So it's called Particular Relativistic Model for Microsecond Astrometry in Space. So it aims at accounting for relativistic effects that are necessary in every individual observation of every source at the 1 microsecond accuracy. And notice that this is actually 10 times better than expected for Gaia, because, well, this is necessary to avoid error propagation when we average out over all observations. So in this model, the 5 astrometric parameters, the positions and proper motions, so 5 astrometric parameters and radial velocity, the 3 parameters for position and 3 for proper motions, are defined in a rigorous relativistic framework, and this allows to account for this phenomenon of aberration that I mentioned before, that is related to the motion of the observer, and also includes light deflection effects in every observation by the following, so by the solar system, major solar system bodies, so to say, which are the Sun, Moon, and 8 planets. And well known here, so these are well-known bodies in the sense that we know their physical and positional parameters to enough accuracy to account for 1 microsecond, so effects that are relevant for 1 microsecond in the final astrometric parameters. Yeah, so we want to focus on gravitational light deflection because it's the most subtle and relevant effects for our concerns. And so the positional shift, when we observe a source, it has a positional shift. If the light ray that we observe passes close to some of the solar system deflecting bodies, and this shift is given by this formula. It depends on the mass of the deflector. The larger the mass, the larger the shift, of course. Depends also on the distance between the observer and the satellite, and also most important on the angular distance between the source and the deflector as the satellite sees it. So just to give an example, imagine that we have one observer in the L2 Lagrange point, so like Gaia basically, approximately, and then it observes a light ray coming from a source, and this light ray is passing very close, so through the limb of Jupiter. Then this shift that so the satellite will observe amounts to 17 milliarcseconds for Jupiter in this extreme case, and this is well above the accuracies that we have in Gaia and that we want for Gaia NIR. The thing is that so this formula is highly time dependent, and if we, as we see in the right plot, we show the path on the sky of a source. First, when no light deflection effects by Jupiter are included in the model, so this is a continuous black curve, and then we also include the same path when light deflection effects by Jupiter are included. So first of all, we notice this zoomed area, and in the zoomed area we see indeed that the difference between the two paths is large, so it amounts to some milliarcseconds. But then for other times, so in that region the sources are very close to Jupiter at some moment. But then it goes away because Jupiter is moving, the satellite is moving, and so the shift becomes much smaller. So okay, the shift is important in some of the observations, but what about the others? In the others, it looks like it's much smaller, right? So how does this translate into the astrometric catalog? Because one astrometric catalog is constructed based on many observations. So when we average out over all the observations, do these particular observations in which the shift is large actually have like important impact on the final astrometric parameters? So this is what we studied recently, and for this we used a simulation tool called AegisLab, and what we did was consider 1 million of real Gaia sources. And first, we obtain the astrometric parameters when we use the full GREM, the full relativity model in the data processing scheme. And then we obtain the astrometric parameters again, but when we skip some relativistic effects, for example, light deflection by the solar system giant planets. And then, so we have two sets of astrometric parameters. When we compute the difference, we get our astrometric error. So the errors that we will have if we skipped some of these effects in the relativistic model. So here we just show some results that we are putting in our upcoming publication. And first of all, what we notice is that when we show the percentage of sources that would have astrometric errors larger than 1 microsecond or microsecond per year in the case of proper motions, if we skip gravitational light deflection effects due to the giant planets of the solar system in the model. So for Jupiter, we see that, yeah, approximately 1/4 of all the sources will have astrometric errors larger than 1 microsecond or microsecond per year. But then the situation dramatically changes for Saturn because it's already less than 1%, and it's even better or less noticeable for the ice giants, so Uranus and Neptune. And of course, these numbers will also become much smaller when we consider the percentage of sources that have errors larger than, say, 3 or 10 or 30 microsecond or microsecond per year. Then, so these numbers will be given in this upcoming publication. Then we were also able to evaluate the so to compute the sky map error distributions on the sky. And so we put an example here. We have the right ascension errors that would result if we missed gravitational light deflection effects by Jupiter. So the numbers there are given by median in each hill peaks. And we notice that there are some regions that are most affected by light deflection effects by Jupiter. And these regions correspond to a subset or to some subregions of the ecliptic plane, and this actually makes sense because the sources that are most affected are those that were observed close to Jupiter, at least at one moment of time during the live mission. By the way, we used 5 years of mission lifetime in our simulations. And so why are the largest errors near the ecliptic plane? So this is simple because Jupiter, so Gaia is orbiting the Sun in the L2 Lagrange point, and Jupiter is orbiting the Sun also in a plane whose inclination with respect to the ecliptic plane is small. So the sources that will be most affected will be those with small ecliptic latitudes. And that's the reason why those are the most affected regions when Jupiter is skipped from the gravitational deflection by Jupiter is skipped from the model. So, okay, we'll also give, from this 1 million sample, we give, the astrometric errors of the most affected sources, so it amounts to some, 100 and something microsecond or microsecond per year in the case of proper motions. So, Jupiter, we can see that it has some noticeable effect for many sources, but then the situation gets much better for the other giant planets, and I didn't even put the rocky planets because it's even smaller. For some of them, it's even 0 at the 1 microsecond level. So, okay, Graham describes adequately, these well-known relativistic effects. By well-known, we mean, so of this we know the positional and physical parameters adequately. And, but are these all the relativistic effects that play a role in astrometry? And the answer is no, and this is connected to one question that was raised yesterday by the audience after David's talk. And the thing is that, so apart from planets, that we know well their parameters, we also have stars. So the light rays that come from the stars, from an observed star, find other stars. And there are macrolensing events shifting also the position. But there's a problem because we cannot model every single deflector or deflecting body in a precise way. Because, we don't have control over every single star or every single asteroid in the asteroid belt. So this could be a problem because actually, since we cannot model these bodies independently, this could give rise to a so-called astrometric noise. And this is basically a limiting accuracy beyond which we cannot go because we simply don't know all the bodies that are having an impact on the positions of the stars. And this is particularly relevant for Gaia NIR, as I show here. So imagine that we observe a star, and then we want to achieve, let's say, 1 nanosecond accuracy in the astrometric parameters of this star. So we have to consider a region given by an angular radius around this star, and inside that region we will have many other stars that will act as lenses. So they will prevent us from achieving the accuracy we want to reach because we don't have control over all of them, so they will be modifying the positions. So this is what we actually have to study. This has not been done before, and this is what we're doing now. It will be particularly relevant for Gaia NIR because it will observe very close to the galactic center, and there we have very huge stellar density. So, just make a rough example to expose the influence of microlensing. So the shift that the source suffers due to microlensing event is in this case given by this formula. It's given in terms of the distance to the lens and the distance to the source. Equivalently can be written in terms of parallaxes, of course. And the thing is that, so if we consider Alpha Centauri system as a lens, and then we consider sources that are angularly separated an angle of 1 degree or less seen by Gaia or Earth, or observing the Earth, we find that the errors that we will have in the positions amount to some microsecond, few microsecond, and in the proper motions and parallax amount to few nanosecond per year and nanosecond, respectively. But in any case, proper study of the errors has to be done not individually, with some particular systems like AlphaCent. This only to give an example. We should actually propose some realistic model of the galaxy, for example, the Besançon galaxy model. So for stellar populations to actually study this using some more rigorous simulations that would give the astrometric errors throughout all the sky. And now to finish, just change topic, basically be a brief comment about the celestial reference frame. So as we know, QSOs, quasars are the most natural objects, astronomical objects to build celestial reference frame because they have very small, almost zero parallaxes and proper motions. So they act as fixed stars so that we can use to calibrate our instruments, etc. And so here in the year 3, we were given like a reliable sample of QSOs of about 1.9 million sources. And so this is like reliable sample. Then we also have some other samples containing more candidates, but these are not as reliable because they are also like, they have some spurious effects like star contaminations. So it's more difficult to extract like the important QSO candidates or the most reliable QSO candidates in those samples. But also we have, so my PhD colleague in Dresden is also studying this, these stellar contaminations and doing a proper study of astrometric quality and purity of these samples to improve the QSO samples that we get, reliable QSO samples. And also final comment, we see that in this left plot again, we don't have basically QSOs in the galactic plane. This is because of the large galactic extinction, so Gaia cannot observe QSOs in that region, and this will be hopefully improved with Gaia NIR, so this will allow to get like more homogeneous map of QSOs in the sky. And also, in general, the number of QSOs that Gaia NIR will observe will be much larger than Gaia, and this is great for many, so to help answer many big science questions, for example, in the field of cosmology, because we know that QSOs are very far away, so they suffer from cosmological redshift, and this, so having a large sample is important, for example, to study the early stages of our universe. So the messages first, we have the modeling of relativistic effects that we have in Gaia is also, so it's describes the relativistic effects well also for Gaia NIR, so effects that are important to 1 microsecond or 1 microsecond per year accuracies. But we have to pay attention to these microlensing events that have not been considered because they will impose a astrometric noise limit, yeah, this limiting accuracy beyond which we will never be able to go because our lack of knowledge of all the individual deflecting bodies. And finally, yeah, that the observations in the near the ecliptic plane will be, so provided by Gaia NIR, will help us get more homogeneous distribution of QSOs. So that's all from my side. Thank you.
Thanks for finishing almost in time. And questions?
Nice talk, thank you. So what could be the impact on the determination of binary orbits?
Yeah, so binary orbits, yeah, that I'm not sure because binary orbits are modeled differently in the astrometric model. So these effects that are considered in the Gaia relativity model, it's more tricky to consider the binary orbits. Of course, we have also effects because if you have a binary orbit, then there is microlensing from one of the components, like so in the other one. But these effects I'm not aware of, that they were calculated, so I'm not really sure. Yeah.
Any other questions? Yeah.
It is slightly connected to Artemia's question. You mentioned that you are using Alpha Centauri.
Yeah.
Are you taking into account the relative orbit of A and B?
They're considered as a single system.
And it's just A and B. You are forgetting Proxima Centauri.
Okay. Yeah. This is just rough estimation to have a grasp of the orders of magnitude due to microlensing. Yeah.
Any more questions? Okay, then let's thank the speaker again.
Thank you.
So if everything goes well now, it's going to be the last talk of the schedule by Manuel Perger on exoplanet science. And stop share. Manuel, are you there? No? Okay. No, okay. Okay. Okay, then Sarah now? Okay. Sarah, are you there?
Yes.
Okay, can you
I'm
go
here.
now?
Yeah.
Okay. Thank you very much.
Okay,
So,
I'm going to share my screen. Let me. Can you see
Yeah,
my screen? Yeah? Okay.
You can see it. Yeah, can you go to full screen
yes.
just in case?
Now?
Perfect.
Okay.
Sara Rodriguez Berlanas is going to talk about the massive stars in Gaia NIR.
Okay, thank you, Nathan. Well, so hi everyone. I'm Sara Rodriguez Berlanas from the IIC and the ULL. And today I would like to take you into the hidden and dusty realm of massive stars with Gaia NIR. Well, massive stars and their birth environments play a key role in the evolution of galaxies. Through their strong radiation, winds, and final supernova explosions, they regulate star formation, drive chemical enrichment, and shape the structure and dynamics of clusters, associations, and even the spiral arms. However, despite their importance, our current census of massive stars is still highly incomplete. The main problem is that massive stars are born deeply embedded in dust, so many of the regions where they form are heavily extinguished. As a result, optical Gaia and are you hearing me? Sorry. Well, I continue. Okay.
Yes, Sarah, we can hear you.
Okay. Okay, so a result, optical Gaia is intrinsically incomplete at extinctions above 5 to 10 magnitudes in the Big Bang. And this means that we are missing precise astrometry for a high fraction of the youngest massive star population. So to fully access these environments, we need the near infrared. So we need Gaia NIR. But why is near astrometry essential for us? Well, as you all know, the key advantage of the near infrared is that extinction is much lower. Roughly, the K-band extinction is only about 1/10 of the optical extinction, so the near infrared can penetrate regions that are completely opaque in the optical. This allows us to observe stars deeply embedded in dust, including massive young stars in H2 regions, dense star-forming complexes, and young massive clusters. Moreover, with near astrometry, we can also reach structural components of the Milky Way that are otherwise inaccessible. For example, the inner spiral arms, the galactic bar, and the inner disk. And these all are key regions for understanding the formation, dynamics, and evolution of massive stars. And of course, Gaia NIR is complementary to Gaia. It uses the same astrometric principles, so we can keep a coherent reference frame, but it extends coverage into heavily obscure regions. This means that we can directly compare population in dust-free regions with those in high extinction environments, obtaining a full 3D census of massive stars across the galaxy. So to illustrate this, we can look at some examples of regions as seen in the optical and in the near infrared. On the right, you can see the pillars of operations in the Eagle Nebula, as seen by Hubble in the optical and in the near infrared by the James Webb. This is the same image David saw yesterday, in which we see that many of the stars and structure hidden behind dust that were invisible in the optical emerge now through the dust. We see a similar effect in the Carina Nebula on the right. The infrared view from the James Webb penetrates the dusty regions, revealing jets and outflows from young stars previously hidden by dust. And this is what Gaia NIR can bring to us, because it can reveal massive stars and clusters that have been hidden from optical surveys, providing accurate stellar positions, parallaxes, and proper motions. Well, particularly important is to set constraints in the early evolutionary stages of massive stars, before the uncertainties introduced in later phases due to, for example, rotation, pulsations, binarity, internal mixing, winds, or mass loss, propagate and multiply its effect in the subsequent stages. Therefore, infrared coverage is needed for detecting and characterizing their faintest, youngest, and more obscure early type population. We can say that without the near-infrared, our view of the galaxy's massive stellar content remains incomplete, affecting theories of star formation and evolution. But one of the most key aspects of the combination of Gaia NIR with Gaia is the improvement on the accuracy of proper motions. By extending the baseline in the time to roughly 20 years, we can highly improve proper motion measurements, as we saw yesterday, and also obtain improved parallaxes needed to reach larger distances. So the difference is striking, particularly for embedded and distant regions. And I must note that proper motions are the key to understanding massive stellar dynamics. With Gaia alone, the temporal baseline limits our position in faint or strongly obscure regions. But by adding Gaia NIR, the longer baseline allows us to measure even small motions with a high accuracy. This improvement has a direct impact on a number of scientific cases related to massive stars. For example, we would be able to trace the expansion of OB associations, measure the internal kinematics of young clusters, detect substructures such as filaments or streams, and distinguish cluster members from field contaminants in very extinguished regions. And many studies based on Gaia, such as those you can see there, will be greatly improved by adding data of the hidden population in these regions. In particular, Gaia NIR opens new possibilities for understanding OB associations and massive clusters. By providing astrometry in the near-infrared, we can finally achieve a complete census of membership. This is where several near-infrared spectroscopic projects, many led by Spanish researchers, become directly complementary. These studies highlight the impact of near-infrared spectroscopy in heavily obscure regions. They reveal hidden massive star populations and massive clusters beyond the reach of optical surveys and allow us to derive accurate stellar parameters, radial velocities, and abundances for these populations. So Gaia NIR will allow us to combine much more precise positions, distances, and proper motions with these near spectroscopic studies, providing constraints on stellar masses, ages, and, for example, the estimates of the initial mass function. On top of that, with full 3D velocity fields, including radial velocities from these surveys, we can measure expansion, collapse, and early dispersal of clusters, giving us direct insight into cluster formation and evolution. And what about Gaia NIR photometry? Well, it will have a strong impact in the characterization of these stars and also in the selection of massive obscure candidates, as it will provide additional information to include in classical selection methods based on color and color magnitude diagrams. Moving on to star-forming regions, Gaia NIR will allow us to go beyond individual stars and study the interaction between massive stars and their natal cloud. By combining precise near astrometry with gas kinematics from ALMA or even the James Webb, we can follow the combined motions of stars and the gas. This is essential to understanding feedback processes. Massive stars inject energy and momentum into their surroundings via radiation, winds, and the supernova. With Gaia NIR, we can measure how these feedback processes shape H2 regions, bubbles, and the molecular clouds. And moreover, it provides a unique opportunity to test theories of triggered versus spontaneous star formation. By mapping 3D motions of embedded stars relative to the gas, we can identify patterns of motion consistent with one scenario or the other. Well, Gaia NIR also opens a window onto massive stars, runaways, and star dynamics. We could be able to identify massive runaway stars in dusty regions, and with precise 3D motions, we could disentangle the origin of the ejections, linking these stars back to their clusters or original binary systems. I would like to note here that in the origin of massive runaways is still a relevant open question in stellar astrophysics. The most likely ejection scenarios are the dynamical interaction in star clusters, for example, close binary encounters, or a core collapse supernova explosion disrupting a binary system. This has direct consequences for understanding supernova progenitors and compact object populations, including neutron stars and black holes, giving us a more complete picture of the life and the death of massive stars in the galaxy. And here again, I saw some works on runaway stars, led also by the Spanish community, based on Gaia data that we think that could be strongly improved and complemented with Gaia NIR data. But Gaia NIR doesn't work alone. For example, the James Webb provides detailed physical characterizations of stars, including those deeply embedded in dust. However, it lacks global astrometry, which Gaia NIR supplies. ALMA maps the gas kinematics in star-forming regions. So by combining these gas motions with the stellar proper motions and parallaxes from Gaia NIR, we can study the dynamic interplay between stars and their natal cloud or material. Spectroscopic surveys such as WIF and FORMOS will deliver radial velocities, stellar parameters, and chemical abundances, which complement Gaia NIR's 3D positions and proper motions, giving a full 6D view of the stars. And for example, the Vera Rubin Observatory adds a time domain and deep photometric coverage, helping us to detect variability, eclipsing binaries, and transient phenomena. So in summary, Gaia NIR acts as the astrometric backbone, linking all these datasets into a unified, precise 3D map of stellar populations and their dynamics, from embedded massive stars to distant clusters across the Milky Way. So the big science questions that Gaia NIR can answer or can bring us closer to answer related to massive stars could be how do massive stars form and disperse their natal environments. With Gaia NIR, we can trace the motions of embedded stars along with the surrounding gas. Second, how do massive stars evolve in their earliest phases? Gaia NIR will uncover the youngest massive stars and open a new window onto their formation and early evolution. Third, what is the true 3D structure and dynamics of the spiral arms? Well, by mapping position and proper motions of massive stars across the galaxy in young clusters, Gaia NIR can reveal the structure and kinematics of the disk and the spiral arms in detail. Fourth is the IMF constant in different environments. Well, let's see what happens when we take into account the hidden population of massive stars. And finally, how does feedback regulate star formation efficiency? Well, Gaia NIR, in combination with gas observations, will enable a quantitative view of star feedback, tracing how winds, radiation, and supernovae form OO stars, say, star formation in clusters and OB associations. So together, these questions show how Gaia NIR would revolutionize our understanding of massive star formation, cluster evolution, and the dynamical structure of the Milky Way. And to conclude, I put here three main take-home messages. The first one is that massive stars and star-forming regions are key to the evolution of the galaxy, but Gaia alone only gives us a partial view. And I want to highlight here that Gaia has completely revolutionized the field of massive stars over the past years, delivering unprecedented astrometry and enabling major breakthroughs. However, the youngest and most embedded massive star populations remain largely inaccessible at optical wavelengths, due to severe and high dust extinction, leaving crucial regions of the galaxy unexplored. Second, near-infrared astrometry is essential to penetrate the dust and access the hidden regions where these stars form and evolve in their earliest stages and phases. And finally, Gaia NIR will complement Gaia, but also spectroscopic surveys, transforming our understanding of stellar dynamics and unlocking new science on massive stars, their clusters, and birth environments. And well, that's all. Thank you.
Okay, we have time for a couple of quick questions. Anyone? No, all very clear. Yeah, I can formulate a question. And, I mean, what I think when I see the geoscience cases is that we want to observe stars which are much fainter than the massive stars in the close vicinity. So we probably need a huge dynamic range to observe these clusters. But I think there's a question for you. There's a question for the designers probably. Yeah. Okay. There are no questions. Let's thank Sarah again.
Okay, thank you.
Now we have Santiago Torres, who's going to talk about white dwarfs in Gaia NIR. Not sure how we see your presentation. Huh? Where is it? Here.
Okay, thank you very much for letting me hear the opportunity to talk about my favorite topic, white dwarfs. Sorry for this. And I will start in the worst way, doing some apologize or disclaimer, or better, showing what are the assumptions to this talk. It's not pretend to be a review, it's just to discuss some topics, so forgive me, I omit some references. The calculus are not new calculations, not exactly calculations, are all just rough estimates. In some of them, we adopt a very conservative magnitude limits, 20 magnitude limits, and we adopt the key band as our reference for the estimates. So, but, well, anyway, what we pretend is to emphasize the Gaia visible mission, what have bring to us, and then what can bring this new Gaia NIR mission. And this is an illustrative example that all of us agree here, what has been Gaia for us. In astrophysics, there's a new era, it's a before and after Gaia, and specifically for white dwarf, the people who study white dwarf, you can see here, or maybe you cannot, a few white dwarfs there with good parallaxes, and this is in Hipparco, and now we have a very clean diagram. And this is the key feature that the key tool that we use in understanding the white dwarf evolution, the HR diagram. Because remember, just a few ideas of that as an opposite to the main sequence diagram, here stars are born around this area and then start a process of cooling, and then we are measuring. This diagonal is a measure of the cooling age, And also, we have the mass distribution. The low masses are over here, and then the more massive in this direction. The mass of the white dwarf is proportional to the mass of the progenitor, and this in turn is proportional to the mass of the main sequence. Then when we join all together, what we have here is a map of the ages of the evolution. And then this brings a lot of information of the star formation rate, the history of the galaxy is in print here. But not only that, the physics behind the evolution of the white dwarf is also in print here. The process of cooling, the emission of neutrinos or exotic particles, action, everything that can involve some physics is bring in this diagram. So it's very important for us, what has been bring by Gaia, and thanks to the proper motions and good parallaxes. But just as a summary, new data bring also new questions, and this is the way that science progress, and here we have a few examples of unexpected issues on the diagram. Maybe you have heard about that, the two cooling tracks that we can identify in the HR diagram that are related to hydrogen and helium atmospheres. We have also this Q branch that is related to the process of crystallization. This is really visualized in this diagram. But there are other aspects that, well, all of them is still under debate, but there are others that are not so well studied so far. For example, this ultramassive stream here, very massive stars, some of them magnetics. This faint blue branch, this is very curious. I will talk in a minute later because it's related to a deficit in the infrared, and also this faint rest excess that in principle the cooling track will be moved above here, but it seems that some opacities are lacked there. And so, well, all of these features are important here, and for that we need a clean HR diagram, but clean diagrams are not so at the beginning. If we study, this is an example of layer 2, the raw data from Gaia, we can see that we have a lot of sources there, but contamination, blending effects, spurious sources, crowd sources, and then we need a process of cleaning here. Also very important for what we are talk later is this separation here between the hydrogen atmospheres and the helium atmospheres. When they cool enough, they are around 4,000–5,000 kelvins. That's a separation of the two, and this is an effect of the collision-induced absorption of the molecule of hydrogen that starts to absorb the red and infrared, and then it turns to the blue. But this only happens to the hydrogen atmosphere, not to the helium ones. And this is very important. We are going to see that in a moment for the infrared effects. Okay, but well, even if we talk about a complete sample around the 100 parsecs, the fact is that if we move to magnitudes 15 or below that, the completeness starts to decrease and is lower than 0.5%, than 0.5. And this is due to this contamination, many of them the contamination due to the galactic disk, and this is something that probably Gaia NIR will improve. Talking about the limits of Gaia, Gaia provides a low resolution spectra that is okay. We can work with that, many things, but if we really need to be more precise, to identify, like in this example, metal lines or magnetic fields or even companions, binaries, and so on, is imprescindible to move to a higher spectra. Okay, so now reaching, what is the difference in the atmosphere? This figure that has been talking Manuel Carrasco yesterday, this is the key important fact. When we move to very low temperatures, hydrogen, as I said, due to this effect of collision-induced absorption, start to suppress the infrared fluxes here, and then the behavior is different for a helium or for a hydrogen-rich atmosphere. Okay, if we look in more detail that, here we can compare this is a cooling track, the visual in the y-axis and the key magnitude on the x-axis. How for hydrogen is this behavior? Is cooling down, but when the hydrogen reach the collision-induced absorption, then it moves to a horizontal plane, more or less. But even in this case, if we assume a 20 magnitude, that is very conservative, as a limit, for hydrogen, a visual 20 magnitude in a 100 parsecs will limit the sample to 15 absolute magnitude. This will imply that we can observe a white dwarf up to this temperature. If we move to the limit of 20, that correspond to 15 also in 100 parsec, we reduce this temperature to 4,300. It seems not so much, but this implies that the temperature to reach, the age to reach this temperature in the visual is 9 gigayears, but limiting to the Gaia NIR, this means that we can observe even white dwarf older, around 11 gigayears, because remember that white dwarf follows the third, well, as anything, follows the third law of thermodynamics, and the cooling here take a lot of time. So this small amount is even very important. But in this case, it's more dramatic for helium, because helium has this not infrared effect. They start cooling, and then in this case, a limiting magnitude of 20, that correspond to 15, it will say that we, in principle, will observe all helium white dwarfs in this case. No? That it can, the models stop here, but we don't know what will happen in this region. So we'll be absolutely complete up to 100 parsecs. No? And in this case, we will observe practically all helium white dwarfs possible. Okay, if we look in more detail for the completeness, just this comparative with a very conservative 20 magnitude, the completeness in blue is the Gaia visible. If we recalculate, it's just a rough estimate, but recalculating and taking into account the extinction is very low now in the case of the key magnitude, we will have that the completeness will move to 100 parsec to a complete sample around 130, it's not too much, but we practically double the number of non-white dwarfs. Nowadays it's around 300,000 white dwarfs, but, well, sorry, this will improve to practically the double number of white dwarfs. But if we take a more optimistic or more ambitious limiting magnitude of 23, that perhaps is not also too much, in this case, the completeness can reach 500 parsecs, and 500 parsec means a lot because it's 5 times in distance, but in volume is 125. And the numbers here becomes very crazy because we will have of the order of 6 or 9 millions of white dwarfs and a complete sample of 1 million white dwarfs. And even if this 500 you see, maybe you can think that for galaxy terms is very close, but you need to take into account that the orbits, you need to integrate the orbits, and these orbits have been, belong to objects that have been moving around all the galaxy. So this sample will be representative of all the galaxy. Okay, so with this improvement, we can achieve, for instance, in a better estimates of the luminosity function. We can move here, we can push and be more precise here on the cutoff, that this is very important for determining the H's of the thin Ds, the thick Ds, the halo. Also, we will be able to be more precise identification of white dwarfs belonging to the different galactic populations. And this is a summary of the different competitors or complementary facilities, depend on what you can consider, no? Depending. Nowadays, there are many that are close to the red or to the infrared, in fact. Some of them also cover all the sky. That is a very important characteristic, no? To be a complete sample. But I think no one of them has the possibilities of Gaia to be precise and to obtain a good parallaxes, proper motions, to obtain a precise HR diagram. But so they are complementary because many of the information of the different filters can bring more information about the specific characteristics of the white dwarfs. Okay, so I will move to talk also about a pair of scientific cases that are very interested, are related to the infrared on white dwarfs, and one of these is the search of white dwarf with infrared excess. Around 6–9% of white dwarfs, these figures correspond to a work that we have done and is really impressed in a few days, in short, will be on archive. We have found that for this 100 sample that we make as a reference, around 6–9% of the white dwarfs show an infrared excess. We can see here that how this is the Gaia spectra when in the G-pass filters, how when we move to the red infrared, we start to have here an infrared excess. And this infrared excess is very important. There are many people working on that because are related to an accretion to a disk. It can be a gas disk or a dust disk. In this case here we are representing a dust disk. That the emission is around 1,500 kelvins, and we start to observe this disk practically in the red infrared. No? So this is very important to characterize. Why they are so important? Because these disks provide information about the material of the extrasolar system. Typically, there are some asteroids or minor objects that collide to the white dwarf, and these metals are captured by the atmosphere. And then, we're analyzing these metals, we can have an idea of what are the content of material of the extrasolar systems. And so the identification of this on the infrared is one of the hot topics, no, in the study of the white dwarfs. As I said before, one of the unexpected features of the HR diagram with Gaia was this faint blue branch that is also called the infrared faint ultra-cool branch, because here what happened is on the contrary, there's a deficit on the infrared. In red we have a typical hydrogen atmosphere, and it seems that there's an infrared deficit, and this happens by another effect similar to the collision-induced absorption that I have been mentioned before, but in this case of the hydrogen molecule and the helium molecule. So if we have hydrogen and helium there, we can have this effect, but this object is still to be under study because some of them present very old ages, high kinematics, so they're very curious to find a good, precise knowledge of this sample. And also a very interesting feature that is what happens if we have this HR diagram, here on the left is on the visible, if we translate to the infrared, or the red infrared. White dwarfs can be used for measuring the distance to globular cluster and also to fit in the age, no? Because it's an equivalent to the main sequence turn-off there. There's a turn-off of the white dwarf, that this is useful for measuring the ages and the globular cluster distances. But what happens when we do it on the infrared? There's two important things that we can observe here. The first one is that this blue and this turn-off happens to brighter magnitudes that in the case of the visible, and also there's a larger separation, so we can be more precise in the obtain of the age estimates here. This is another thing that we can implement here with the near infrared emission. Maybe the issues of this technique will be that globular clusters are 2–3 kiloparsecs, are far enough, or maybe open clusters are limited in the number of white dwarfs, but it's a very interesting thing to analyze the HR diagram with the infrared mission. So for ending, and just to say that a similar mission like Gaia in the near infrared has a stronger point of an astrometry and photometry, will be very useful for the determination of the luminosity function, H's, star formation rates, a lot of things that we can do with white dwarfs, also for better estimates of completeness of the of material of the bright disk and dusty disk. And just, well, to mention that this era of big data will absolutely necessary to bring machine learning in techniques and also the artificial intelligence in many things that we can or we can dedicate to another things as humans. No? Okay, so thank you very much.
There any questions?
Santi, sorry for my ignorance. Halo white dwarf, long-lived, very, very long-lived. The variation of the gravitational constant, only 1,000 white dwarf in Gaia. How many white dwarf in the halo? And is it still a matter of very interesting concern, this variation of the gravitational constant along the age of the universe? Is it still a key science?
Yes, with these rough estimates, we may reach of the order of, how much is this? 18,000 white dwarfs, only of the halo, that this is a very statistical significant. For these topics, like the G variable or the emission of actions, the problem that always happens here is that there's a degeneracy between different things that can bring the same effect. No? We need to know very well, for example, the star formation rate to constrain there later the effects of a possible G effect. No? And so playing with these two things, but it is possible, it's perfectly possible to that. No? It's one of the topics that from time to time we take a look at that. If it is, you have here an image of the effects of the gravitational variation or not, or axions or other exotic topics, dark matter, if it is captured by white dwarfs, can also change the cooling of the white dwarf, maybe. So, but for that we need a precise, for example, star formation rate, a precise sample to avoid any bias or any other effect.
You put some vague statement about the multiplicity of white dwarfs with brown dwarfs. So you don't have a number for that? And is that something that we could get from Gaia NIR infrared with bigger samples?
Yes, this is one of the topics that we want to study here, because I talk only about disk, but this infrared emission could be also by other superstellar companions as brown dwarfs. And this is something that we are trying to estimate now. We have a few brown dwarf, white dwarf combination, and probably here we will have increased the number and to obtain a better samples and constrain possible, well, the IMF or the brown dwarf desert. All of these topics that are under discussion is perfectly possible.
Anyone else? Okay, then let's thank the speaker.
Okay, thank you.
And now is Manuel Berger, if you're there. Yeah.
Yes,
okay.
hello.
Can you share,
Good morning.
please?
Yes. Can you see?
We can see the whole, yeah, okay, perfect.
Yeah, perfect.
Okay, then He's going to talk about exoplanet science, as you can see. Please go ahead.
Okay. Thank you very much. Good morning. Unfortunately, I couldn't be there. Trains were cancelled, so I would have loved it. And I'm going to talk about exoplanet science, the possible influence of this Gaia NIR we want to send to space. I'm working in Barcelona. Here's a small overview of the team we have under the leadership of Ignacio Rivas and Guillermo Anglada. We actually work on all topics of exoplanet science, ranging from the pure detection of planets to the characterization of atmospheres, which is done these days, especially with new instruments like the James Webb Space Telescope. So we are covering probably all lines of exoplanet science these days. So I'm going to introduce a bit very generic what is actually an exoplanet. I put here the official definition or working definition of the International Astronomical Union. On the bottom left, there is a small summary. So exoplanets are objects of small masses. They should be sufficiently self-gravitating, have self-gravity to be round, and they should orbit another larger mass object. So this kicks out all those free-floating planets, actually. And it should have cleared out the orbit. So this is the argument where 2006 Pluto was kicked out of this definition, actually. The formation mechanism is not included in this definition. So just how we detect exoplanets, here's this nice example we always use. An exoplanet is, of course, only a few hundred Kelvin of temperature, and quite close to it, there is this star, which is a billion times or whatever brighter than this planet. So we have, of course, the problem that direct detection of such a planet is quite difficult. So the analogy is here always that we have this lighthouse 1,500 kilometers away. So this would be already Italy or Lyon from Sevilla. And we would detect there a firefly, which is close to this lighthouse. So this is very challenging, and only few detections have really been made in this direct manner. This is, of course, already a bit different in the infrared, where the ratio is a bit better for the planets. So this is a very nice image from the exoplanet book of Perryman. We can see here practically all the methods we use to detect exoplanets, the different branches in different colors, and they're going down then to the masses of exoplanets we can actually detect. And at the bottom, you can see then the numbers of planets we have actually detected with each method. You can see here easily that the two most important methods are the radial velocities, where we have already discovered around 1,000 planets. This is this lila line. And on the right side, the orange lines is by far the most successful method, is using transits with the space-based instruments like Kepler or TESS, for example, where we already detected 4,000 planets. So the newest number just looked up yesterday is that we have now officially 6,080 planets detected. You can also see here in the green branch that the astrometric method was not yet very successful. This is, of course, because of the reasons I just said. The precisions it's hard. The light of the star is really not helping. And as you will see, and Gaia NIR infrared can help there a lot, is that we have a baseline of observations which is not large enough to get really to those gas giants. Gaia could also, astrometry could also really detect and help to detect. I'm just going to introduce those methods a bit. I begin with the transit method. This is the most obvious one, of course. Here, the planets cross the stellar surface in front. We just do images and then see the light of the star dropping periodically here in one of those transits you can see at the bottom. The depth of this transit then is, of course, proportional to the ratio of the radius of the star and the planet. And we can thereby calculate, of course, the period, the distance of the planet to the star, and the inclination, which is, of course, edge on, and the radius of the planet. This is also the method where we can actually characterize later on the planet a bit more in detail, since the light of the star crosses the atmosphere of the planet during this transit. So this is the method we are now exploring, especially with the James Webb Telescope, and which is the method which will be most explored in the next decade, I suppose. So we are really now going after the atmospheres of the planets. With these methods, we are close, maybe not yet there, to really detect an Earth twin, so a Earth-like planet which orbits a Sun-like star. Biases here with these methods are that we have, of course, a better detection of small periods and of large radii. The second method I want to present here is the radial velocity method. So here, of course, we measure the movement of the star induced by the planet. So this is always some kind of misconception, of course. Not only the planet moves around the star, but the system moves around the center of gravity. So we can then measure the radial velocity of the star induced by the planet by the Doppler shifts of their spectral lines, which you can see here in this illustration. We can thereby then also measure the period, the distance, and the minimum mass of the planet, because, of course, the measurement depends a lot on the inclination of the planetary orbit. So you can imagine that if the planetary orbit is very inclined, that the effect of a massive planet would be the same than a less massive planet in a less inclined orbit. The same is true that we are close to be able to detect a Earth twin. We are now at around 30 centimeters per second, which is for me always a very amazing number. This is by far less than we can walk, and we can measure actually the movement of a star at an incredible distance as well. The biases are the same as for the transits. The larger the planet and the smaller the period, the better we can detect those planets actually. The same effect we measure, of course, with the astrometry. Here we see a small illustration made by ESA. Here we can also get the period, the distances. We can get the inclinations even for multiple systems. So this is a very nice feature here. And we can also get the planetary mass. We are, with the precisions, also quite near, depending, of course, on the brightness of the stars. Earth twin would induce some 2 micro arc seconds. Here, very importantly, with astrometry, we have this different bias. No, we, of course, can detect much more easily large radius planets, but differently, we can really access here planets which have a larger period, and Gaia near infrared would really help due to this longer baseline to add here to add or to help to explore this parameter range. Yeah, as you know, we have those 2 important missions already sent to space. This was Hipparcos from 89 to 93 with precisions to 1,000 microarcseconds. We observed here 1 million stars. And as you all know, of course, the Gaia mission launched 2013. We are now expecting the fourth data release. Yeah, we have observed here 1 billion stars with positions and motions, and I think this is a really very successful mission, and the infrared mission would only add to the precisions and to the data we could later use for the exoplanet sciences as well. I have here this nice comparison. So what could we detect, or could we detect a solar system? I show here at the bottom the wobble in astrometry or on the sky in microarcseconds for a stellar system at 10 parsec distance. I also show the periods of each of the planets, and I show the impact on radial velocities and the semi-amplitude of the radial velocities, this K. And I mark the numbers in red if they are still below our precision, and in yellow if this is on the limit, and in green if we can make it. And you can see that, of course, Jupiter, Saturn is, for all the methods, are the easiest planets. But we can see here that especially for astrometric and for Gaia near-infrared mission, we can really extend this possibility to go beyond Saturn, Uranus, Neptune, and really be able to detect those far-out gas giants, which have quite large periods still. What have we done with astrometry so far? We have detected 14 planets, most of them in the last 5-6 years. They were all of Jupiter mass. And we have now created a lot of candidate lists, actually, with a DR3 Gaia data release. There are around 300 planets as candidates. And we have this paper where there are 10,000 of candidates listed. So we really have to check each of them with additional data if we can find here actually real planets. No, we need additional data for those. I put here some of the observations we have done so far, and the images and the articles. You can see here how nicely we can actually, with astrometry, detect exoplanets and the movement of the star going around in one direction, and having induced this cycle from due to the planet. So those are our famous observations here, mostly also accompanied with additional observations from Hubble or from radio velocities. So what are the urgent questions we have actually in the exoplanet science? How is the diversity of planets and their systems? We still lack here exactly what Gaia near-infrared could really help us with. Those are long period gas giants. This will help to get really a better understanding of the distribution of planets around stars. We also have this huge problem called the radius valley, where exactly the planets in between rocky ones and in between gas dominated ones seem to show a dearth, and we are trying to understand, probably this is related to the snow line. Do we have many close-in planets actually? So we want to study the parameters like the multiplicity, the eccentricity, the habitability of planets. So all exploration of whatever parameter space can help us by very much with this statistics to get better parameters and to understand this diversity here. What we all want to know, of course, the formation of planets. So we have a few ideas. The most common one might be the one you see here in this illustration. Dust grains accrete into planetesimals. They form the planetary embryos and form then planets. And larger planets then might migrate inwards or clean actually the space out of any other smaller objects here. So we could also, Gaia NIR infrared could also explore here the larger planet realm. Yes, as I said before, urgent questions as well. How abundant are actually the Earth-like planets? So as I said at the beginning, we are now about to really go after the atmospheres. So we want to know, Earth-like planets with atmospheres. We know already from statistics that we should have around 90% of each star has a planet, and around 15% of each star has habitable Earth. So this is, I think, large numbers, and we can really go forward here as well. So we have, statistically, around 20 billion potentially habitable planets in the Milky Way. Gaia NIR infrared also could help us a lot in the classification of the host stars. No? This is really important. M stars are the most stars in the galaxy are M dwarfs, and we actually have focused our research in the last 20 years or 15 years on those stars, and would be really good to have always better classifications of them. Further, of course, with a near-infrared instrument, we could always go for the star-forming regions and take thereby young planets. There is just in the last years an effort going into the analysis of young planets. This would also help us a lot in understanding actually the formation processes. And here on the right side, I run this illustration as well. This is a point we are working on extensively now in Barcelona also. This is the understanding of stellar activity. This is practically stellar magnetic effects locally on the stellar surfaces, inducing phenomena like dark spots or faculae, which then emit in rather the infrared. So here we have effects which are different in the optical and in the infrared. And so this can really be learned a lot how those influences are. You see again here on these two lines is of concentration. On the left side, you see the one at sort of wavelength. Effect is different. So we can here also explore the chromatic effect.
You are well above your time. Could you come to the conclusions quickly?
Yes, sorry. Just here, I have again this illustration that you can go to larger distances. And okay, I see this slide. Then here we have synergies we can have with already existing missions like Plato. So, like I said, mostly we can access a new parameter space, get occurrence rates, and can explore it. So I close here with some of what I just said. So thank you so much. Are there any questions?
Okay, time for a very quick question. José.
Hola Manuel, seguro que reconoces la voz.
Claro.
No, just a very easy question, but it is for you crazy because we don't know. How many planets do you think that Gaia NIR would be able to find? We do not know the answer. I'm looking right now at David Hobbes. So, what is what you think that it could do, and what is what you want it to be?
The number I want should be as large as possible. I think we have this possibility, especially with the low baseline, that we check on there some interesting planets we haven't really get with other methods. So let's say some number for 100. What do you say, Jose?
We couldn't hear you.
Yeah, there was some connection. How many did you say?
I said, after a long sentences, I said 100. What do you say?
We lost you again. How many? It's just the number, just the number.
100, 100.
100, okay, thank you.
Okay. Okay, let's thank the speaker again. Okay, thank you. And now it's time for Miriam Cortés.
Hi, can you hear me? Hello?
Hello.
Okay.
Can you share, please?
Yeah, yes. Okay, can you see my screen?
Yeah, everything's fine.
Okay, thank you very much.
Okay, we're going to finish the session with opportunities for low mass stars. Please, whenever you want.
Okay, thank you very much for inviting me. I'm going to talk to you about low mass stars in the Gaia NIR era. So first of all, let me talk about low mass stars and brown dwarfs, why they are, what they are, and why are they so important. So when we talk about low mass stars, we're referring to stars cooler than our sun, less massive than our sun, and fainter than it. And when I say cooler, I mean stars with temperatures below 12,000 Kelvin, masses below 0.5 solar masses, and they are really faint. The lower the mass of the star, the more faint they are. And they are very interesting objects because when I say low mass stars, I also say brown dwarfs because there is this connection between the stellar regime, that it's stars that fusion hydrogen in their cores, with brown dwarfs that do not. So they represent a transition between stellar and substellar objects, and these substellar objects are also in between in terms of mass of stars and planets. So this is the really interesting sample that also is the most abundant object in our galaxy. We can say that more than 80% of the objects in the Milky Way belong to this low mass regime, M, L, T, and Y stars. So they are also interesting because they have very long lifetimes. They live as long as the age of the universe. So they are perfect tracers of the structure, the kinematics, the evolution, in terms also of metallicity of our galaxy. In terms of science cases, I must say, Manuel Berger also said before that M dwarfs are the prime target for exoplanet surveys. Actually, if you take the exoplanet catalog as for today, you can see that 10% of the planets or exoplanets confirmed or candidates in this catalog are orbiting around M dwarfs. So these are very interesting scientific objects as well. And as I said, they are faint, so they are observationally challenging. When I talk about the low mass range and I say they are faint objects, I can place them here in the HR diagram. This is an HR diagram taken from Gaia DR2 collaboration. You see perfectly the main sequence, and the bottom right There is the sample of ultra-cool dwarfs taken from work of Smart and collaborators in 2017. And here I'm saying ultra-cool dwarfs, taking stars that correspond to the late M types, Ls and Ts. We make this separation. And as you can see, they populate this bottom low region of the HR diagram, where we have less objects. So we are still completing this range of the HR diagram. And I must complete this information. Here I show these spectra as an example of where the emission is in for F, J, and K stars, meaning solar stars, compared to a mid-M dwarf. So you can see that these M dwarfs and lower mass stars emit the bulk emission is towards the infrared. So we are able to detect them in the optical, yes, but we are missing lots of them, or we are missing the information since they emit in the infrared. Now, the most of the emission is in the infrared. So here we are missing objects and missing information about them. In this sense, of course, Gaia has been an excellent resource for identifying and characterizing all types of objects. Here I show you, on the left, you can see this HR diagram that corresponds to the Gaia catalog of nearby stars at 100 parsecs, built with EDR3. And it's been able to build a very complete and homogeneous catalog of all the objects in our solar neighborhood. I will tell you to pay attention to these orangish dots that are here. They correspond to stars in the solar neighborhood, objects in the solar neighborhood with poor solutions, and you can see they are all concentrated towards the faintest targets. And then this greenish blue main sequence and white dwarf sequence that are those more than 300,000 objects with good solutions. This means good parallaxes, good proper motion, accurate proper motions, and so on. And if you attend to this region here that are M dwarfs, this region is well populated. But then if we go towards the lower mass stars, lower than the M dwarfs, meaning L, T, and Y dwarfs, we see that there are some stars, but there is a poorer characterization of these objects here. As stated by the authors, they say that at least 92% of stars of stellar type M9 are included in this catalog, meaning we are almost complete, but it starts to fail on characterizing these kind of objects. Then you see here in the chart to the right the distribution of M and late type dwarfs compared to other stars, A, F, J, K, white dwarfs, etc., in blue. And as we said before, these low mass stars are representative of more than 80% or larger percentage of the objects in our neighborhood. So you would say, okay, these objects are faint in the optical and are brighter in the infrared. What happens with current infrared surveys? We can talk about all sky surveys like 2MASS and WISE, which are provide us homogeneous photometry and astrometry of all the sky, but their astrometric precision is poor compared with Gaia. Their limiting magnitudes are around, as you can see here, around 16 magnitudes in the J band or 17 in the W1 band, yes. There are also other surveys, like for example, I'm talking here about VVV, the Vista Variables survey in the Via Láctea, and VVX, its extension, which has better astrometric precision, goes deeper in these infrared bands, but is limited to the central region of the bar and the bulge. It's towards the center, it's perfect because it avoids extinction and all this handles these problematics when we go towards the center, but is not an all sky survey. To show you the coverage of them, here I showed you the transmission curves on the left in blue of Gaia. Then you have the 3 bands of 2MAS and VVV, and then the WISE bands. So this region is where we are interested when we are talking about these low mass stars. Of course, what would we do? We cross-match Gaia with these surveys, with 2MAS and with WISE to complement. And we can improve the completeness of our catalogs because it allows us to identify nearby low mass stars. I talked before about a small sample of SMART and collaborators 2017. They started to build the Gaia Ultra Cool Dwarf sample. Here I just list a few works going in that direction, where they cross-match Gaia with infrared surveys using different methodologies, and you can see that they increase this Gaia Ultra Cool Dwarf sample by hundreds here, hundreds there, and up today I think that this catalog contains more than 8,000 UCDs, populating, as you can see, this fainter and redder region of this CMD diagram. But still, this is an heterogeneous catalog built from different methodologies using Gaia, using WISE, using UKIT, using other infrared surveys, but still it's incomplete. And you can see this, this incompleteness when we go to the lowest end, when we talk about, we start here from M7 stars and going through L and T. In this histogram, this is taken from Sarro and collaborators 2023. You have 2 colors, but well, the gray one represents this, the distribution of objects in the Gaia Ultra Cool Dwarf sample, and the green ones is a sample of ultra cool dwarfs built by a different methodology by Sarro and collaborators. So what you can see is that Gaia is losing sensitivity when we go to these fainter objects as expected. And I'm here I'm not talking anything about extinction and crowdness that we have in specific regions, but it's something that affects also the completeness of this Gaia, Gaia Ultra Cool Dwarf sample. So what do we expect from Gaia NIR, or how Gaia NIR would improve this? Let me make some easy numbers here to show you this. So let's consider typical colors in G minus J band magnitudes from M7, L5, and T5 dwarfs. And we can get, considering the actual limiting magnitude in Gaia, the G band at 20.4 magnitudes. And we can see that, of course, the J magnitude expected for these stars is brighter for the faintest objects, and we are limited to the closest objects. This limiting magnitude in the optical is imposing the detection of the faintest targets closer to us. So we have a great bias here when we want to know our neighborhood at larger distances. And I'm not talking about 1,000 parsecs, but just here at 20, 50 parsecs, we are not being complete in this mass range. If we make the exercise considering a limited magnitude in the Gaia NIR N band at 20.4 magnitudes, we can reach farther distances for these objects. In particular, you can see that for the T-type dwarfs, we would be able to confidently detect them up to 100 parsecs, meaning we would be able to build a complete sample, to have a complete census of all stars and brown dwarfs at 100 parsecs from us. If you picture an HR diagram, here I show you an HR diagram built from the 10 parsec sample in the Gaia era from Rayleigh and collaborators 2021. There are like 600 objects, 400 of them with spectral types, which are colored here. And what we could expect from a Gaia NIR survey and this HR diagram up to 100 parsecs would be something, I expect nicer than this, but something similar. I'm only focusing on the M regime, but we would expect something much more populated in this range that let us know really how many objects we have here, because all the studies we are carrying out on population studies, we are biased because we don't really know how many objects there are. And also all our calibration models are based on an incomplete sample, and this is something that is needed. So complementing the Gaia astrometry in the near infrared with the Gaia astrometry in the optical, apart from this long astrometric baseline and the astrometric here yesterday, I think I've heard something about reaching the nano arc second accuracy. It's fantastic. So we could be able to really complete a census with all these mass ranges, improve the kinematics, constrain better the initial mass function. It will provide benchmarks for stellar evolution, stellar formation, planet formation. And I'm aware that there are lots of challenges. Some of them have already been discussed here and will be long discussed here. But I'm really confident about the impact of this, the improvement that the Gaia NIR will provide us in several topics, as has been discussed previous in exoplanet, the high mass range, and from the galactic structure to the exoplanets regime. I'm really confident that it will be as good as Gaia has been for us till now. So I bear in mind that these challenges are key to success, and I repeat that we have passed this with Gaia and the optical, and with Gaia and the near infrared, I'm really confident will be something even better. So thank you all for your attention. I'll finish here in case you have any questions.
Okay, thank you very much. And do we have any questions now? Ale?
Hi, Miriam. Alessandro De Roglite here. I have the feeling from what you said that basically, sort of connecting your presentation to Santi Torres' presentation, that Gaia NIR may have an impact on low mass stars as like Gaia had on white dwarfs. I think I missed it. How you showed that in T dwarfs we are currently limited to something like 7 parsecs, was it? So how many L dwarfs are within these 7 parsecs?
You're talking about this?
Yes.
I think I don't completely hear. Your question is?
Sorry, my question is, so within these 7 parsecs, how many T dwarfs are there? And how many T dwarfs would you expect up to 130 parsecs?
Okay, so these are the numbers. Sorry, there is a question. Okay. Okay, so these are the numbers I get just considering the magnitude, the G magnitude in Gaia and the typical colors of the stars. In this 10 parsec catalog, I think there are few T dwarfs, at less than T parsecs, but more than 7. These are just some example numbers and something to show you how far we can reach. So if we have a few, how many T dwarfs we have here? A dozen of a couple dozens of T dwarfs, tops.
Wow.
Yeah, less than 20 we have in 10 parsecs. So you can extrapolate. I mean, we will reach, I can't give you a specific number, but hundreds of them.
Awesome.
For sure.
Thanks.
Any more questions? Then we will finish on time. Let's thank all the speakers for the session now. Any announcements? No? Okay, yes, remember that we are back at 3 for next session, for the open table with the industry. And have a good lunch.
start the roundtable on the industry. Thank you all for coming and staying awake at this time. It's a great pleasure for me to chair this occasion. We have here with us Cristina Ortega from AVS, David Hobbs, of course, Luis Saturnino from ACETEC, Gaisca Murga from IDOM, and Mariano Sanchez from CNR. And online, I think that we have Santiago Serrano from Satlantis. Hello. And Xavi Luri from the Gaia group of Barcelona. And besides, at some time, I apologize in advance because if you are in the middle of some presentation or something, I will have to interrupt you because we will have Cecilia Hernandez from here, from the Space Agency of Spain, in the airport. So just taking the right time to make a quick presentation from her side. Okay. So my plan for today was the following. It's just this initial introduction from my side, welcoming you and presenting this overall agenda. Then we move to David on explaining the main needs, or reminding the main needs from the industry for Gaia NIR. All of this is again focused on Gaia NIR, on the technological and know-how that may be missing or still challenging from the industry, especially from the Spanish industry. Then Cecilia will explain her point of view. Xavier Luri as the PI from a long time ago, and with all these essential contributions to Gaia, with a lot of expertise gained at several fronts, that will be very useful to get his point of view for Gaia NIR as well. And afterwards, we will move to a brief round of presentations from each of the industries that we have here, including, by the way, myself, because I'm here also as DAPCOM, as the spin-off that we have from the UB and the UPC. So just, I will ask you please to try to stay at 5 minutes each. So just focusing on your expertise, your know-how, what you think you can contribute to Gaia NIR and so on. And after this, roughly half an hour for you to explain your point of view, including online Santi. We will move to a few questions, around half an hour more with 2 minutes each for 3 questions or so. And finally, some 10, 15 minutes from the audience in case you have some questions or your point of view as well. Okay? So I pass the word to David. Yeah. Thank you.
Hi, thanks for inviting me here to this discussion. So I have no slides prepared, so I'm kind of winging this, but what I want to do was to remind you a little bit about what we need. And this story really begins, or a large part of this story begins about 30,000 years ago, when photons were emitted from the surface of a star near the galactic center. And those photons now are traveling towards us, and in a decade or so, perhaps 2 decades, Gaia NIR will be ready to receive those photons. And those photons will come in through our optical system. So for industry, their role begins basically here. We have to have an optical system that's designed to receive these photons through a primary mirror. The light has to be bounced through the optical system and onto the focal plane where we have our detector technology sitting. And inside the detectors, these APD detectors, the light will be converted into electrons, and those electrons have to be read out of the detectors. And we should remember, if we're looking at the galactic center, we gave some numbers earlier, that we could be seeing 10 million stars per square degree, or if we go several magnitudes deeper, that could be up to 60 million stars per square degree. And this is a huge number of detections at the same time. And those electrons then have to be integrated as they move along the focal plane. And the focal plane has to be able to read out these, so we need readout electronics for the detectors. And the detectors need to be cooled passively as well. So they generate a lot of heat when they're reading out all of these stars, and that has to be dissipated into space passively without any active coolant, which is also a big challenge. And all of this electronics then has to gather all of this information together in a computer. These onboard computers will have to rely on storage, but they have to prepare the science results and then transmit them to ground through some sort of high-gain antenna. And I believe ESA is working on new high-gain antennas to transmit the data. But the data rates involved here are amazing, and we would need, as Jordi said in his talk, about compression algorithms and all sorts of very clever ways to do this, because we simply will have so much data that we want to get back to ground. So this represents a massive challenge in space, and where industry can help us to design a spacecraft that's suitable for this. And the data then has to be collected on ground, and it has to be processed also by the scientists who are also sitting here in the audience. And we have to engage, of course, all of the young scientists now, because most of us will retire before this mission actually operates. So it's the young people in the audience that we really have to get to do the work. And that's also going to be very exciting. And I said in my talk earlier that we've already started training young people to do this challenge. So this is the challenge we have. There's many opportunities for industry to get involved in this process. And we haven't even thought about the data processing centers yet, but that will probably follow something along the lines of the Gaia data processing. So there's many opportunities and challenges involved in this, and it's kind of very interesting work as well, and fulfilling, I think, for everybody involved in this endeavor. So I think I'll stop there, and it'd be nice to hear then what Spanish industry wants to contribute. So who's next?
Thank you very much, David. Good. So maybe Xavi, are you ready to say a few words?
Hello, can you hear me?
Xavier?
Hello, can you hear me?
Yes. No. Yeah.
Yeah. Hello. Thanks, Jordi. First of all, I have not been able to attend in person in Sevilla. Sorry about that. That's a personal problem. But Jordi has invited me to contribute as, and I quote, IP veterano, veteran IP. And now he has introduced me to being able to talk about all types. So yes, I have to accept it that I'm the old generation. And as David was saying, the young generation there will have to take the task of making Gaia NIR a reality. But actually, since I'm really old generation, let me look back. 30 years ago, we were in a similar situation with Gaia, and we were doing two things, building a consortium and getting the industry engaged. On the first half, I think that we're in a much better position. At the time, we inherited from Hipparchus, and now Gaia inherit from the Gaia experience. At all levels, I think that will be very beneficial. And in particular, in Spain, I think we are in a position to build a much bigger consortium. Looking at the meeting today, there's a lot of people sitting there from many research teams, and the Gaia network, the Spanish Gaia network, I think is a good seed to build a very strong Spanish consortium that can contribute to a very strong European consortium. And on the second part, the industry. At the time, at least in Spain, we were moderately successful in engaging with the industry. And we even had some contracts involving universities on the research groups and the industry, and a reasonable involvement of the Spanish industry. 25 years later, I think the Spanish industry is in a much better position. It's much stronger, with many more capabilities, and more important, with a much stronger commitment from the Spanish government on space science. And I think that we can do a much bigger contribution to Gaia. Again, together with our European partners, our European industry. So I'm really happy to see this meeting as a seed of something bigger. And I encourage not only the scientific community that from the presentations we have had those days, really interested in Gaia, but encourage the industry present here, and I think the roundtable is important, to take a leading role in Gaia, and especially to work with us scientists, institutes, universities, hand to hand, to have a successful and relevant contribution to the Gaia NIR mission. So I think we can do big things, and I'll leave it here. And again, thank you for letting me do this short speech, and thank you all for the big interest in Gaia NIR. I think we have started very well for this nice mission.
Thank you very much, Chari. All right, so I think that we can now move to the first set of presentations. Maybe you can start. I guess that we can use the same microphones that we have here. I presume.
The chronometer, so yes. Hello. Yeah.
And your slides should be here, I think. Nope. Yeah, this one. And here you have. Okay.
But,
oh.
But wait, because this is not the first slide.
Okay.
So we'll go to the first one. There we are.
Y te comparto la... unmute. Oh, no. We need to mute, sorry. And share, where is share? Come on. Now. And share the full screen. And is it okay now?
Yes.
Yep, okay. Good. Thank you. So,
Okay, so good afternoon, everyone. Thank you, Jordi, for the introduction, and all the community for the opportunity to be here today. I think we know, all my colleagues in the industry, we all agree that it's important to support these kind of initiatives since the very beginning. And for those that don't know AVS, I will try to be super quick with the time I have. But I wanted to give you an overview of what we do. So this is our facility where we are doing the space activity. And first I want to start with the mission, or a sentence that has been with us since the founding of AVS. We say that we do limitless deep tech because we do technology for science, but our lemma has always been boosting scientific knowledge. So you must understand that these kind of initiatives are very important for us because our aim is precisely to help the scientists or to develop the technology that the scientists need to advance on their science. We are located in Spain, but also in France, in UK, and in US. So eventually this could be beneficial, no? for the distribution of the technology when it comes to time. And we have been delivering critical equipment for the last 20 years. We have counted in total 1,300 complete turnkey developments. And now we are prepared, so we've been growing, and now we are prepared with 1,000 square meter facilities, in clean rooms, etc., and 8,000 in total, and we are about 200 people already. And the activity that we do is, well, these are our facilities in Vitoria, is divided in these three main areas. This is not like a classical way of dividing the science, but it's our way. And we are developing technology in accelerators, in fusion, and in space. And I just wanted to give you some very quick examples of participations that we are doing in accelerators. This is the Atlas instrument in CERN, or in neutrons, where we are doing complete target stations, which are very complex instruments, also to say, in synchrotrons, or also in lasers. No? So you see the dimension of the kind of responsibility we are already ready to take over. Also, we just deliver a full telescope that will be installed in the Canary Islands. And I like to use this example to let you know that we've been moving from developing subsystem to a full capability of system development, which is the example of this telescope. No? We also have a lot of participation in ITER, that you may know, that's in the fusion area. And of course in space, where, for example, we were able to bring contributions to 2 instruments to the surface of Mars on board the Perseverance rover. And that gave us, let's say, well, the stamp on the capability to do space instrumentation too. So now I will give you a few examples in the couple of minutes that I have left of what could be relevant for Gaia NIR mission. On one hand, we are doing the cryostat, that is part of the new Athena mission to host the ex-IFU detector. And I think this kind of knowledge that we are gathering with the cryostat and all this, well, you see in the picture, there's quite a complex systems with many interfaces with many of the subsystems of the main instrument. So this could be applicable. Also, we are participating in LISA, in charge of the industrialization of the radiation monitor, the coils that are magnetic sensors, and also the thermal control, which is also something that could be applicable, as we will see later on for Gaia NIR. We have done for the space optical instruments, like this single photon detector, but also cryogenic instruments for ground. Indeed, we have different contributions, for example, with the Miradas with the University of Florida, which is a set of complex also mechanisms that work in cryogenic temperatures. And last but not least, our capabilities in thermal control. This is an example of one big contract we have with the European Commission that also sum the potential applications that we could apply to Gaia NIR. Then I don't want to, my last seconds to let you know, for those that don't know, that we are the primes, one of the 2 primes of the Arrakis satellites. You see this is one F-class mission, part of the scientific program at ESA. And this is a 600-kilogram satellite, okay, that will bring one Spanish payload. Well, it's also a very important contribution. So for the Gaia NIR technology needs, that summarizing in a very simple way, we'll have structures, bipods, mirrors, thermal control, cryogenic radiators, cryogenic mechanisms. We think, or we are prepared to contribute to whether the development or to use the already existing knowledge we have. Thank you so much for the minutes.
Thank you.
Almost in time.
Next one, Luis for ISTEC.
Hello, everybody. I'm Luis Saturnino. I'm a program manager in ISTEC. We are a company based in Barcelona, 10 years old. It was an anniversary last week. And we dedicate to design and integrate payloads in satellites to deploy a full constellation, mainly it's multispectral, but mainly in the long-wave IR. This is the capabilities of our satellite, the Hydra 2 precursor, that it was launched in January 11, like 2 weeks ago with the SpaceX, successfully launched it, and now it's in the commissioning stage. So with this satellite and growing constellation, we'll be able to monitor the land surface and sea surface of the Earth for the Earth observation in order to collect data, mainly temperatures, and though we can develop several use cases for different industries with commercial purposes. So this is our pipeline of satellites to deploy the full constellation. It will be, the pictures on the right are the satellite on ground during the AIT process, and the upper picture is in the pod with Exolaunch for the SpaceX Falcon 9 launcher. So until 2029, we will be launching, hopefully, 25 satellites that will be covering the entire surface in an average of 3 hours revisit time. For that, we have already our own AIT facilities for the optomechanical components. And nowadays, in 1 or 2 months, it will be fully complete, our on-ground CalVal facilities to do the calibration and validation campaigns of our payloads in-house. So it will be including also black body, TVAC, and so on. With these capabilities, some of the use cases that we can unfold is these pictures are related to sea ice monitoring. With the thermal bands, we are able to distinguish between the different layers of ice. So nowadays that the Arctic is going to be kind of a topic for everyone. It could be helping navigation through the Arctic ice. And it's also one of the use cases for the Copernicus contributor missions that we are part of. Another use case is vessel detection, like this. With the thermal footprint, we are able to detect vessels. Either they are activated with the AI system or not. And another use case of many of them, it could be it's wildfires. We are able to deploy information for wildfires, not only for the monitoring of the wildfire itself, but also for the prevention and the post-fire activities. So with that, you have my contact details there. Anything you need, continue. Thank you.
Cecilia, hello. Are you ready to give your brief talk? Cecilia, are you ready? Maybe we can have one more talk afterwards. For those of you that don't know, Cecilia Hernandez is the head of the industry section of the Spanish Space Agency. So she will provide us her point of view of the Space Agency on Gaia NIR and on the industrial activities. If you're not ready yet, maybe we can move to one more company, and afterwards we move to Cecilia. Yeah? Let's wait. Otherwise, we can move to Idom. Yeah? Let's do one more, Marcel. Yeah? Okay.
Well, good afternoon, everyone, and thank you very much to the organization for inviting us to this forum. My name is Gaisca Murga. I'm the head of astronomy and space at IDOM, and I will try to briefly tell you what we are doing at IDOM. We basically develop high-performance optical and mechatronic systems for build-to-spec systems for science and there is should I do anything? Later. Okay. Okay. So we are working basically in science and technology. This covers fusion, particle physics, fission, experimental reactors, and so on. And I'm the responsible for astronomy and space in this unit. Our main clients in these areas are ESA, Thales, Alenia Space, Open Cosmos, Atlantis, ISDEFE, and so on and so forth. And in astronomy, which is a business in which we've been working in for 25 years, we've been working with, I think, all the institutes and that I believe I know. We have currently active collaboration with some of them. We are working now with the Institute of Astrophysics of the Canary Islands, with the Technical University of Catalonia, with the UPC, with the University of Vigo and so on. This kind of collaboration with the university and with academia and some institutes are very important for us because they make possible some of the systems that I can tell you of. In astronomy, in ground-based astronomy, we've been working in several small, large, and very large telescopes. Now our most relevant projects are on the ELT, on the Extremely Large Telescope, for which we are doing the two prefocal stations, which are the systems that steer the science beam to the different instruments on each of the platforms. And at the same time, they are able to do the acquisition guiding and wavefront sensing. Basically, we are able to detect how well or bad the telescope is pointing, and we are able to send the commands to the mirrors that correct it, and we are able to measure the wavefront error from the stars that we are receiving in order to be able to detect and compensate the seeing which is introduced by the atmosphere. And then we are doing another very relevant system, which is the ELT-M1 local coherencer, which is a system that basically detects which are the small steps between the segments that compose the primary mirror to an accuracy of 150 nanometers and inform the telescope about these events or these small steps so that they can be corrected. This is done by the way, by a optical metrology system that has been developed and patented by IDOM in collaboration with the UPC. In space, we are active in optical communications. We are collaborating with Thales Alenia Space on the Spanish GEO-QKD mission, for which we are doing the Space Telescope Pointing System. It's a pointing system, an accurate mechanism working in GEO orbit, which is able to steer a telescope with an aperture of about half a meter. And then we are also doing the ground receiver almost completely, including pointing, acquisition and tracking systems, wavefront sensing systems, and adaptive optic systems in order to condition the light as it comes. We are working also in Earth observation. We developed in the past the optical bench and the cells for a space camera of 170 millimeters. And we are currently developing for ESA a combined scanning camera concept, which will allow reducing the amount of mechanisms needed typically in these kind of cameras in space. We are also, I'm sure I cannot show you any pictures because of confidentiality issues, but we are also developing a high-resolution multi-channel optical payload for EO, and we will be soon starting the production of 6 flight models of it. And then I believe in Gaia NIR, probably it's too early to talk about it, but we are also doing a lot of optical ground support equipment. We do it for our projects as it is needed, and we also do it for our clients when requested. In this sense, we developed in the past a dynamic optical relay system, which is able to project a beam accurately onto a EO IR detector, which is the device under test, at high speed and with high accuracy and high optical quality. We have developed also simulators for the ELT, for EO cameras and so on, and also for the interferometers that we developed for the local. And basically, the areas in which we believe we can add on to Gaia NIR are from the optical units. This includes from the mirror itself, the cells, and the position mechanisms that are included. We can help on the structures, on the focal plane systems, and so on. Here into the talk by, I think it was Josh yesterday, he was mentioning about the main challenges, and I believe that many of the things that we do are quite aligned to the challenges that are identified. I think the monitoring the basic angle is something that can be done by using metrology systems like the ones we developed. We are very familiar with microclanks on this kind of high accuracy systems. Probably we have noticed them. Probably the impact on our systems is nothing to do with the impacts on an instrument as accurate as Gaia NIR. But these kind of things is, and also stray light problems and so on, is something in which we believe we can add. Thank you very much.
Thank you. Cecilia, are you there? Would you be ready to? Yeah, hey, hi, hello.
Well, it's good to see that you can hear me because I cannot hear you so well.
Okay, sorry. Thank you so much, first of all, for connecting in this
No, I'm here.
difficult moment. Can you hear us?
Yes. Now it's
Okay.
better.
All right. Thank you. Thank you so much, Cecilia. The floor is yours, or the microphone is yours,
Yes,
if you want to
thank
give
you.
us a few minutes of your point of view.
Yes, but the question is that now I am trying to share
Oh, yeah.
my presentation.
Mm-hmm.
I think I do not know. Can you see it?
I think it's yep, yeah, perfect.
Perfect.
Not in full screen yet, but
Yeah,
it's
I
fine.
try full screen and I see.
Yep.
Do you see full screen?
Yes. Now it's all right. Thank you.
Perfect. Well, first of all, let me apologize because I thought that there wasn't a pure Spanish event. And my presentation is the result of translating from English to Spanish, all the concepts of what has happened during the ministerial conference in November in Bremen. Okay, well, let me start with what happened that day in this conference. The first thing is that there were a high level of subscription in general and related to the level of resources that is the source to fund scientific program. For the first time in many years, the level of resources is above the expected inflation. So in this very moment, we can say that for the first time in many years, the scientific program has more money than we could dream, let's say, a couple of years ago. This is something that I am very proud of that, because as you know, or if not, I would say I am chairing the scientific program committee, and we started with our expectation, and the first reaction was that you are dreaming. It will not happen, but it happened that we have got a level of resources well above the inflation. The problem is that in the meantime, we have realized that we have some missions where NASA has strong participation, and as you know, the budget of NASA has been dramatically reduced.
Cecilia, we lost you. Are you still there?
Yes.
Oh. Maybe it's on our side.
No, I think we cannot hear her also.
It seems that it's something on our side. I don't know what happens on the sound here of the room. Apologies, just 1 second. We are checking. Can you try again, Cecilia? No, it sounds from somewhere else. I don't know what's happened. Yeah, we hear that, but very, very faint. I think it's something on the audio control room. Can you try? Yes. Now it was. It's fixed.
Okay.
Yeah, sorry about that.
It is okay now. Well, I'm going to close the video because sometimes it works worse.
Okay.
Okay. The question is that for this time, the commitments for this Israel have been well above last ministerial meeting that was in 2022. The budget has been committed, approved by our minister, is 31% over what we committed in CM22. And if we include quite above expected, is we still have 27% more than we committed in 2022. Something that is that the subscription programs for resilience and dual use has increased. The level of subscriptions has been really high, and at the same time, the coordination with the European Commission have been stronger than ever. I think that these are the most important facts of this ministerial conference.
Yep.
I have problems. No, it doesn't. I have problems with the.
Changing the slide, you mean, or?
No, I cannot change the slide.
Oh,
Oh,
maybe.
no,
Yeah,
no.
no. Okay.
No, I can't. I can't.
Mhm.
It's a intergovernmental, well, that is something important in what we say that for the first time we had more, or there were some emphasis in resilience and dual use. For the first time,
Is ella? Okay. Cecilia, from time to time, it seems that we lose you a bit, like on your microphone side or so.
But I am here. There's nothing. I try to listen to it. Well, for the
We-
first time, political solution activities recognize security and defense. Never again, never before. The First World War is something related to ISA, because ISA.
Yeah. Cecilia, sorry, apologies. It seems that your microphone is deactivating from time to time.
But I yes. Do you hear me?
We can barely hear you. Maybe it's if you're using a Bluetooth microphone or something like that. Maybe it's
No,
giving
I'm
some.
not using.
Oh yeah, no.
No, it's okay.
Yeah, no, it's fine. It's fine. Yeah.
Well,
Sorry.
I will try not to touch anything. Well, this is something that appears for the first time in a political resolution, the word security and defense. And that's very important because it's something that is very in line with the geopolitical situation. Just to remind you, what are the programs and activities of ISA? When we're speaking about budget, there is a budget that is the level of resources for mandatory activities, that is basically the scientific program and basic activities, that are activities that ISA needs to fulfill just to survive. Then there is something that is not fully mandatory, but near mandatory. That is the contribution to the spaceport in Kourou. And this is something that is associated to GDP of countries and also to the participation of these countries in what is called the optional programs in launchers. The rest are optional programs, and it means that countries contribute in line with their capabilities or priorities. Okay? Now we are going to see exactly what are the results of CM25. The subscription, the level of commitment is above 22 million euro, and it's above what we dreamed 1 year ago. This is something that I have to say. And as you can see, the scientific program, yes, the scientific program represents 17% of this subscription, with 3,700 87. Then you have basic activities. That's somehow very important for science also, because you in basic activities supports infrastructure, and all the infrastructure supporting scientific programs. Since then, ISAC, that is based in Spain, is supported by these basic activities. And also when you need to do studies to prepare feature missions, and there is a very challenging technology is also covered through these basic activities. There are other programs that are, well, that you see that are mandatory, that are optional programs, but have that high level of contribution. The first one would be space transportation. Here you can find the family of areas that are European launchers, but also a new generation of launchers for small and medium satellites that is growing up now in Europe, will be supported through the European Space Agency. Then you have also a program that is very much supported with Earth observation, as a strong cyber course. The exploration program, I would say the exploration program that is below the expected contribution, but because as we mentioned at the beginning, there are problems, projects that require missions, where we had cooperation with NASA. In this case, the dependence of Europe is much stronger. And in this case, it was very difficult for countries to commit under a safe programmatic horizon. Well, this is something that needs to be reshaped in the coming years, because Europe needs to be independent or more autonomous than she is right now. You can see more or less how this budget has been distributed. What happened for Spain? If it was a successful ministry in terms of budget, for Spain was amazing successfully. We invested more than ever. If we compare with the previous contribution, 50% our contribution per year. In 2025, our contribution has been 300 million per year, and in the period 2026 2030, our year ISA will be 455 million. So it's a historic increase of the Spanish participation. It has been reflected the position that Spain has now. Now Spain is in the fourth position of ISA contributors for the first time in history. When we made this contribution, it's because we had the will of leading or playing leading roles, at least co-leading in science, sustainability, resilience, navigation, and communication. If we look at the historic investment of Spain in ESA, we can see that from 2017, we have multiplied by 3 our contribution. This is what is reflected in this slide, and for us it's a matter of proud. This is the first time that the Spanish Space Agency is leading the contribution to a ministerial conference, and we have got an increase, a substantial increase on the budget, even the circumstances that we are living right now. If you see here the comparison of contributions in ministerial CM 22 and CM 25, you can see that Spain used to represent 5.5% of the contribution. Spain represents 8.44%. Spain was in the fifth, and now Spain is in the fourth. We see here the evolution of member state contribution, the 10th contributor. You can see how this increase in its contribution comes from some countries. Look at Germany, increase its budget quite a lot. They used to be the 20%, now they are 20%. You can see France and Italy, in percentage, have decreased. They have increased let's say the figure that in percentage, they have the relative position have increased a little bit, but the big change has been in United Kingdom. That has decreased and now is just undecided. In the past, Spain was, let's say, here with Belgium, Belgium, sometimes Spain above, sometimes Belgium. Belgium was above Spain in CM 22, and now we have both our position and not only our position related to the slightly above Belgium, but we are even above United Kingdom in terms of contribution. So it has a lot of implications in everything. People in are working, of course, the rights of fair return, opportunities for Spanish industry, and so on. How is the Spanish contribution distributed? This 1,871 million euros is distributed in the way that you can see. I will highlight it's 270 million euros in products. You know, it's only related with science, the national way of contributing to instrument. We have added 49 million euros. But I have to clarify that this money that is involved is new money. Because the very truth is that as we had money for products from the we still have money in this very moment for the next year. We have 60 million euros to spend. I'll let you remind you that in 2022 we had 30 million euros. So it's a good increase of budget. Okay, then where we have our, let's say, highest contribution been in launchers and mainly in Earth observation. Also, we have contributed substantially in communications and navigation, that are programs that are very much related to what will happen in the future with the European Commission. As I mentioned at the beginning, there is a strongest cooperation than ever with the European Commission. Then I will make a
Cecilia, apologies. Do you have many more slides? Because I'm afraid that we are running a bit out of time.
Because this general overview, I can explain the question, for instance, to science. What are we going to do with this money in science? Mainly to finalize the cosmic vision. You know, now we have SMEI that will be launched in a couple of months. Plato, Ariel, comet interceptor, Envision, also LISA.
Cecilia, we lost you completely. We cannot hear you. I'm afraid that we have too many audio problems. Can you hear me? Yeah, sorry. I'm afraid that your microphone is disconnecting too much, too often, and we can hardly follow you. I'm sorry about that, but maybe you could try to summarize the few slides that you may still have. If we can hear you paying a lot of attention, because it sounds really, really faint on our side. Could you try to summarize the remainder of your talk in a minute, perhaps? No, I'm sorry, we cannot hear you. I think that there's something on your microphone. Apologies about that. No, we can barely hear you. I'm sorry, but I think that we will have to finish the presentation now.
Okay, sorry.
So sorry about that, and thank you so much for your time, Cecilia. That was instructive. Thank you. I think that we have your slides, or you can provide the slides at a later point so that we can also check them again. And now I think that we can, since we are sharing the screen, we could jump to Santi, still online. Santi, are you around? Hello, and thank you again, Cecilia. Thank you so much.
You're welcome. I do not know if you hear me.
Yeah, now we can hear you again. Thank you again, Cecilia.
Okay, thank you. Thank you very much.
Okay. Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay.
And see you.
It remains.
Yeah. If you can try to stay under the 5 minutes.
I will make my best.
Okay, thank you. Okay.
Okay.
Yep.
So thank you, everyone. I am Santiago Serrano, a Science and Technology Director for the Arrakis program in Atlantis, also researcher at IEC. But today I'm going to speak about the space technology for Earth observation and scientific missions from Atlantis. So Atlantis is an Earth observation technology company with its headquarters in Bilbao. Also, we have subsidiaries in the UK, France, and the US. And the core technology is that we can provide entire missions to the customer, adapting to what the mission is. So from definition and design, payload, and so on, and particularly providing high performance payloads from UV to long wavelength infrared. And what you can see on the left is two of the payloads that we have in Atlantis, the small one that fits also in very small satellites and CubeSats, and the middle one. And on the right, you can see one of the images from our satellites. This is from another one, in particular from the small camera that delivers a resolution of about 2 meters. And you can see that this is in the visible and this is in the infrared. So we are also observing from the same payload in different wavelengths, providing imaging, video, and polarimetric capabilities. So far we have flown around, we have flown 7 missions with 100% of success rate, all looking down towards the Earth and focused on either agriculture, environmental protection, defense, security, infrastructure monitoring, oil and gas. We have also a Copernicus contributing mission to detect methane emissions that contribute to the global warming and coastal monitoring. But in particular, this and maybe even more related to Gaia and to Gaia NIR is our contribution to the science program from ESA. This is the F2, the fast class mission called Arrakis. So Arrakis is a new mission that we are building and in the study phase yet, that will deliver unprecedented views of low surface brightness down to magnitudes almost beyond magnitude 31. This is a very fast focus mission. So contrary to large missions, we have about 7 years from selection to launch. So this has been all running all the time. We are towards adoption on June this year, and we are at the moment also preparing PDR. Apologies, I was not being able to go to Sevilla. We are delivering the full data pack of PDR tomorrow, and those who have been in this kind of scientific missions with ESA probably know what this is. But this is extremely exciting and challenging, where Satlantis is the industrial prime for the scientific instrument. This is going to be with the expected launch in 2030, but still a very challenging project with all the optomechanics, electronics, and with a partnership and consortium with other 8 countries and about 20 other institutions. This is how the images from Arrakis as we simulated will look like. And this is already one of the images that we took. We are doing something unconventional. We built one of these space cameras to one of the observatories to test it, to verify the optical performance that is full diffraction limited. So also very interesting. And what we care here is what kind of relevant development could be for Gaia NIR. So this payload has 4 channels, 2 in the visible, 2 in the near infrared. We observe simultaneously for about 50 hours of total integration time per galaxy. And with that, we are using one of the detectors that is mostly used in science missions as the Hawaii sensor from Teledyne Imaging Systems. This is the same that is going in Euclid, in Hubble, in James Webb, and in many other scientific missions. It's an extraordinary detector where we are also building, providing the optics, understanding the sensor, the front-end electronics, and also in collaboration with other 2 institutions, IEC and IFAE, building all the characterization setups to understand, characterize, and calibrate these sensors. So in addition to the optical designs that Satlantis is doing, all this activity, we believe, is going to be extremely relevant. So I think that's going to be it. I hope I was mostly in time, and I leave you with a few of the star images that we are taking with the ISM camera in the Hawaii Observatory. Thank you very much.
Wonderful. Thank you. I think you were right on time. Thank you so much, Santi. Okay, so if you can stop sharing the screen, I will start again and we conclude with CNIR. Mariano? And I think that we can... CNIR, epa. Ah, sí, estaba en el navegador, es cierto. ¿Era este? Sí. Vale, y lo teníamos por aquí.
A un sitio más abajo.
¿Más abajo?
Creo que en estos puntos.
Este. Presentar, mira, vale. Sí, me deja. Ahora no deja. Ahora, epa. Vale. Ok.
So, good afternoon, everybody. My name is Mariano Sánchez. I'm director of the Space Department at CNIR. CNIR is a company that dates back from the 50s, so we are actually this year celebrating the 70th anniversary. So you can imagine that we've had a long track of activities in space and particularly in science. Here you can see just a quick view of some of the most important examples of our participation, starting in the 90s with the SOHO and running to activities like Herschel Plan, Gaia, Solar Orbiter, JUICE, or more recently ELISA and Envision. And what are our main areas of expertise that we provide to these science missions? We can split up into 3 main elements. So they are the first one, the electromechanical systems, both for flight and for ground. And the important thing here is that we don't develop just the mechanical elements, but also the electronics associated to these mechanical elements. And we've got examples like, for example, deployment mechanisms, booms, for example, the JUICE, or a scanner, a big scanner for MTG, or more recently, we are developing for LISA the alignment mechanism for the 3 lasers of the mission. In the area of communications, we can develop the full communication system, starting from the antenna to the RF front end and to the modem. And here we are, for example, particularly for science, we have developed several high-gain antennas. So recently we are developing the antenna for LISA, for the high-gain antenna, and also the antenna pointing mechanism for a mission like Vigil, which, as you know, goes to L5. And the last block of activity is the navigation, in which we develop full attitude and control systems. And here we've got important examples, like, for example, Euclid. You know that Euclid is perhaps the more accurate and the more demanding mission in terms of pointing stability. So we've developed the attitude and control system for this mission. But we have also worked in Gaia. So we have developed several elements of Gaia. In particular, we have developed the sun shield. You know, we need the sun shield to protect the observations. And this is a big sun shield, so it was to be deployable. And there were some requirements that was necessary to be taken into account in order to end up with something really feasible. And we have just listed here the most important requirements in terms of envelope size, the thermal stability, also the structural stiffness, and some of the interfaces. And also, of course, as you can imagine, always the overall requirements of mass. But we have also worked in the alignment mechanism for the secondary mirror, which is also an important element in order to get the proper observations. This alignment mechanism is not just a single shot project. We started with Gaia, but also we have developed this type of alignment mechanism also for Euclid and for Ariel, different type of requirements. So we run from 5 to 3 degrees of freedom, and we've been moving to different environmental conditions like the temperature, in which, for example, for Ariel, we are going down to 40 kelvins, which is just cold electronics there. And this is just a lesson learned from Gaia that should be interesting to be taken into consideration. We're looking at Gaia NIR, the next step. So essentially, some element mostly related to, for example, through the straight light. Most of you know that there was some problems with the straight light due to the fibers of the deployable material. And also, we will have, even though we can take most of the design and solution as they were, we need to take into consideration elements like obsolescence of the electronics, and to introduce probably some non-dependence conditions that are now play a role. So let me finish with while I'm trying to describe what we could do for Gaia NIR, just a video in which we were showing the deployment, the test and the verification of the deployment mechanism. And what can we do for Gaia NIR? But I mean, first of all, to continue what we did for Gaia, I mean, we can still working in this deployable sun shield. We can also keep working in the alignment mechanism of the mirrors. But also, I've learned yesterday that there is a challenge with respect to the data rate we got to get from Gaia NIR. And as you could see, we've got a lot of experience in high gain antennas, so we can cover the full communication chain, and this is something also which is important for us. And within the third element of our backbone of activities, we can also contribute to all the control, attitude control subsystem that should be necessary for this particular mission. So that's all for me. I think it is.
so I think that I'm the last one, and I will try to be very quick. Famous last words. I should have, yep, this one. I'm a bit ashamed of talking about this small spin-off after these great companies. It's really amazing the work that you're doing. We are quite more modest. We are a technological spin-off created from the UB and the UPC 13 years ago. Now, February, it will be 13 years ago. The main motivation was the exploitation, the commercial exploitation of data compression technology, this FAPEC compression technology, but also given that the founders, all of us had a very strong background on Gaia and data processing for Gaia, we also had this second division on software and data processing and so on. We incubated in the ISABIC in Barcelona. We were one of the first 3 companies incubated there, and afterwards moved to my city. Was much more comfortable, but we have 2 main offices in Barcelona and Vic, basically, and collaborating a lot with the IEC, ICCUB, and University of Barcelona. As I said, we basically have 2 main divisions on high-performance data compression with our FAPEC technology, and massive data handling and processing. On data compression, we were really happy when we managed to put in orbit our technology for the first time with the Spire global constellation for Earth observation based on GNSS, radio frequency data, and so on. It's now still being used in hundreds of satellites or so. Amazing, mind-blowing, in my opinion. And also we have this data visualization software for hyperspectral imagery and some maritime water column files, which is, we basically moved from space to the oceans. It was some quite unexpected move, but very productive and interesting. We are, since a couple of years ago, applying commercially our data compression technology to vessels, to sonars of the sea bottom and the water column, as you can see here in these pictures taken from our software. But yeah, anyway, this is the brief and quite intense short story of DAPCOM during these last years. You can see that we have had several projects already. Many of them, most of them on Gaia data processing, but also on other aspects, like some small satellite from ESA, some weather forecast and monitoring pipeline for the Institute of Astrophysics in Canary Islands, optical timing of runners, peculiar things, and data compression as well. So this is our main expertise. It's mainly on software development and data processing, and these are the main aspects where we think that we could contribute to Gaia NIR. Basically, software development with our quite strong expertise on Gaia, development of pipelines, tailored pipelines for these very specific scientific missions, and deploying them in high-performance computing, and also developing, very important, some of the algorithms that will be needed for this kind of missions. And with that I conclude, and we jump to the roundtable in itself. So, I took notes of a few things of the presentations that you did. Those were really amazing, and it's maybe I was thinking that it's a bit frustrating to some point that we are limited to the geo return, because from what you have explained here, I would suspect that you could basically build the entire mission, so to speak. So that, I guess that this is where things like Arrakis comes into place. It's nice to see missions like that fully led by Spain, and with a huge participation from Spain. But in this case, it's a large mission, so I guess that we have to split the cake between different countries. But anyway, I took note of a few interesting points like non-dependence that you mentioned, I think. It's a very interesting point to avoid, despite some of you have offices in the US, which is extremely interesting from the research and development that is being done there. I think that it's good, and with current times especially, to avoid dependence from that. Anyway, I wanted to mention a couple more of things that I took note of. I see that you have capacities in structures, thermal control, radiation control as well. There are some projects that are more perhaps on a low Earth orbit or perhaps just stationary. It's good to remind that we are going basically into deep space. L2 is deep space, so we have to be careful about the radiation hardening in electronics especially. Something that I found very interesting, have you considered optical communications for Gaia NIR?
Yes, this would be very useful actually. The problem is that you have to have a steerable optical communication, and if that can be done, it would solve the data rate problem basically.
Yeah, but for stability and noise on board and everything, we cannot have any continuously moving mechanical parts.
Yeah, we would prefer to avoid moving parts basically. So you need some sort of mechanism where you can steer an optical beam basically. I don't think it's impossible to do, but I'm not sure it's been developed yet.
Well, the studies and CDF and everything will tell us. Okay. Satlantis mentioned that you have some near-infrared detectors and so on. I presume that some things that may be lacking still are the TDI mode.
Yeah, so the biggest problem we've had really with the Gaia NIR mission is finding detectors that can integrate light at high frequency, basically. So if you have detectors like that, of course, it's very useful, but most detectors operate in a kind of a slow readout mode, and that's why the APD detectors that Leonardo have were suitable. But that's just one aspect of the mission, so if they can supply the detectors, we still need readout electronics and lots of other things as well that have to be accompanied.
And perhaps cryogenics and structures and what else did you say? The metrology that we will also need on board, some basic angle monitor spread all over the focal plane as you showed. Yes. So yeah, really exciting. Anyway, we are running a bit short of time. I was thinking of doing you 3 specific questions and maybe going through the several companies, but perhaps we can just try to shorten that and get 2 or 3 answers from some of you. The first question that I was thinking of is actually these current challenges that it's a long way until the adoption, hopefully, of the mission and development and so on, so we still have time. So until then, which main challenges on technology and know-how do you envisage perhaps in your companies or overall in the Spanish industry? Maybe you want to start?
Well, maybe now that we are participating in Athena, I have our own experience on no matter how much experience you have in cryogenics, which in our case is quite extensive, not only on space but also on Earth, that and also with the ESA scientific program that foresees the need of development, early development on some technologies, we've seen that sometimes those developments that has been done in preparation for missions, when it comes the time to apply them, they are not available unless, I mean, it blew my mind because we were trying to find some conclusions on some studies on materials that were done on another country by another company, and it's kind of they are not available. So we need to restart and do our own tests. So I think this is not a technological challenge, but more, let's say, administrative or coordination or a challenge. But apparently, it's some work to do on that side. It's very recent for me, and so maybe it's good to take into account. Yeah.
Second opinion, maybe some other.
Sorry.
Thank you. So for us, for ISTED, we are not yet working for science missions, but we do the optomechanical systems, also select the FPA, we integrate with TDI, but not with the cryocooling for MCT sensors, but the proximity electronics also, and we make the end-to-end from the optomechanical to the data. Possibly in Spain, we are lacking of some FPA developers we have in Europe, but maybe the most relevant one is still in USA, unfortunately, or the most relevant. So improving in that sense of the detector, improving the technologies, and investing in R&D in that sense, it makes sense, at least to me, because it's the main component that I consider for Earth observation or detectors in deep space, probably.
Maybe I could just add about cryocoolants. We generally try to avoid any kind of cryogenic cooling system. So we basically use heat sinks to get rid of the heat. But that's a problem because a lot of heat sinks weigh a lot and that costs a lot of money to launch then. So maybe we have to consider cryocoolants also, but they also weigh a lot. So I think the heat sink option is probably better for us.
Mm-hmm. Just to add a little bit on a different topic that I mentioned during my presentation is as far as I understood, you as scientists want to maximize the return of the mission in terms of the data you are able to digest and to use and so on. And as far as I understood yesterday, the bottleneck today is the transmission chain. So we need to, I think one of the main challenges is try to work out on a solution that would allow us to increase this data rate and to end up with a high-gain antenna that should be able to do it. And just very much related to the cryogenics, you mentioned the cryocoolers and so on. It's fine for me if you introduce a cryocooler or whatever, but I think it's important to take into account that you are introducing kind of a source of vibration and so on. But depending on the stability requirement you've got, it could be affecting the overall performance of your observation and would require an additional vibration isolation system. Yeah. So it's something to be taken into account,
But we also have the similar problem with the fuel tanks, though.
Yeah,
the
sure.
fuel sloshes around also. But now that Jordi stimulated me talking about optical communication, there is a simple way to avoid a rotating or a moving component, and that's simply to fire multiple laser beams, because you always know which one is pointing towards the Earth, and you can solve that problem. So I think optical communications might be the best solution, actually. It solves the data problem.
Well, it depends a lot of also the duration of the pass. Because at the end you've got a very narrow beam, and this beam should be passing through your ground station, yes, and should be compatible the time you've got in. So it's not just a straightforward.
But the beam will spread out though over 1. What is it? 1.8. How many million kilometers is it? L2. 1.5 million, so the beam actually spreads out quite wide, so yeah. I think this could be a solution.
And so the power you need, because if it's a spread, you need to be very powerful in order to get...
With the design it will be even more, I think.
Yeah. Yes. No, it's around 1.5 million euros, something like between the satellites, I guess. Yeah.
Yeah, now that you mention, well, it's true that it's preferable to avoid the moving parts, of course, but in case they are needed, it's true that there are a lot of advancement on vibration cancellation yes, so, and this is, so we are participating in several activities, and this is even being incorporated in small satellites and in LEO missions, so on, so probably in some years, it could be something like much more accessible or less heavy. So this is also like a hope, or at least an open window that in case it's necessary, I think we should also look at that technologies.
Yeah, I think regarding the challenge that you mentioned about the detectors, I think it's an institute nearby which is very relevant for that. It's the Institute on Microelectronics in Seville. It's in La Isla de la Cartuja. I don't know if you know them. They are able to do really specific development for applications. For example, they are now developing infrared detectors for defense, and they have developed single photon APDs for astronomy. They use them in interferometers, and they are really, really fast. They are talking about picosecond of reading, and they have experience in Spain. I can.
Yeah, maybe we should. You should introduce me to them.
I have little more to add about detectors, but I think regarding the rest of the challenges that were mentioned, I think investing in technology, on developing the tools or the systems or the technology that we will be needing in the future is definitely interesting. And as Christina was saying at the very beginning, it's really interesting to involve industry from the very beginning in order to be able to evaluate what is feasible right now, and if not, what can be done in the remaining time.
Santi, would you like to add anything else?
Well, thank you. I kind of agree of most of the challenges that you have. Can you hear me?
We still cannot hear you. I don't know if audio
Hello?
control. Yeah, no, yes.
Okay, no, I mean, I agree on most of the challenges that you have been sharing. Also on rad-hard electronics as well, we are fighting to get the proper radiation electronic level. And in particular, I think the NIR detectors is going to be a challenge, not only on building and making sure it works, but only on the calibration. We usually have very limited calibration capabilities on board, and therefore understanding well these sensors where sometimes they have effects like persistence and so on, it will be critical. We are fighting a lot now, again, with the calibration sites as we have in IEC and IFAE. To understand these sensors is critical before launch, and is going to be especially critical for Gaia NIR, I would say.
Yep, thank you. I fully agreed. Yeah, now that you also mentioned radiation hardening and so on, it's in the case of Gaia, and let's see if we can manage to get something similar for Gaia NIR. I think that we were quite good there, because I presume that quite a few packets were lost because of some other issues. But radiation-induced prone particle events, problems in the data and so on, from my IDT hat point of view, I think that I remember like 2 or 3 bit flips in the full mission. So it was really an amazing piece of work. I don't know if any of you are behind that success, but that's really acknowledgeable. It's very good. So going quickly to the next question, it was actually related to the schedule that we mentioned now. If you want to mention anything about the schedule steps, the considerations that the industry may need to properly prepare. Actually, I think that I will link that to the next question, and we solve that into one single one. Because I wanted to ask about the schedule that you may need, that the industry may need to properly prepare, the steps that you would need, and any improvements from the administration. I don't know if we have anyone from the administration connected or here in presence that you would really welcome to facilitate the participation of industry and the just to participate in major missions like Gaia NIR.
Yeah, well, I think we have all suffered, no, from the from experience. Okay, yes, that's more positive. Yeah, from the difference between the times of the administration and then the times of the development or the implementation of or the need of the missions and the schedule of the missions. So, of course, we know this is not easy to solve, but I really think there's a challenge there, because so far, I'm sure it's the same for all the companies, but it's very challenging and very difficult to maintain all the resources and until the finance comes, and so we need to do like malabarismos, I don't know the word in English, but financial games. So yes, I think this is one of the challenges. And of course, I mean, we are open to discuss with the Spanish Space Agency about ideas. But yes, for sure, this is something that for the future could help a lot, you know, to support the science.
Maybe also, Is this working?
Yeah.
Sí. Maybe also from the administration, it used to be supporting the R&D programs, but investments are not used to be that supported. It's always try to be spread but along different projects and different years. So for these missions that are not that recurrent, bigger support on infrastructure, it could be an asset for Spain.
Okay, I mean, just thank you. So just a couple of words about the schedule in this. I mean, now today we are still in a very preliminary step of the mission. So now it's in your hands, it's in the scientific community to provide the evidences that is interesting enough to be adopted. And what we can do from an industry point of view is just to give you all the support you might need. I mean, we are in CNR, we are very much used to work closely with the scientific community from the very beginning, giving you our industrial perspective in order to give you or to end up with a more realistic solution, you know. And then afterwards, during the industrial phase, I mean, we'll have to wait for ESA to release the corresponding ITTs and also on. Regarding the administrative staff, it is something that, I mean, overall speaking, the scientific program has proven to be very successful in Europe. I mean, you can have a look in contrast to for example, to the exploration mission, to the exploration program, which is not very successful because, you know, we are at the point it's pretty much related to the non-dependence that I mentioned before. I mean, science and Earth observation has been programs that are driven by Europe, while exploration has been somehow trailing by other countries, and the result is that we are always, we are not independent. But having said that, the problem that we have here in the industry is that perhaps we are doing things pretty well, that sometimes enters into conflict with the available resources we have with respect to the geographical return. You know that Spain today has over-returned in the scientific program. So we've got we have certain problems to increase our participation in missions. That's a problem we have, and this is something that we can't do anything but expecting that at a given point in time the agency will just resume the zero of this oversubscription they have. So the only thing we can do is just to keep working like we are doing now and try to hope that we are in a better situation.
Well, regarding the schedule, one must admit that the schedule of the program gives a little bit of vertigo. We are more used to fast-track projects than to this. But the good point is that there is time in order to get prepared. And in this sense, I believe that we have time and opportunities for scientists and engineers work together. And I believe that whenever scientists and engineers work together, we're able to doing marvelous things. And regarding the administration, well, I mean, we know the rules of the game and so on, and I think there is room in order to do things. So I think we should do it.
Maybe I could just comment on the timeline. I mean, even though it's a very long time away, I mean, ESA are already conducting technology studies that are related not just to Gaia NIR, but to detectors in general and readout electronics. So there's a possibility of getting involved via these technology studies at this point. So I think that would be a big opening for people to come into the system and be in place then to benefit from the contracts later on.
Yeah, agreed.
Santi, any comment?
Can you hear me?
Yep.
Yeah, I mean, Atlantis is a fast company. We are in a fast mission. And even though 7 years of launch looks a lot far away, we are always running. And I imagine that even for a long or large mission, we will have to rush and we'll have to organize quickly. But in terms of what can be improved, I would say that Also giving thanks to our agency and to the Spanish Space Agency for all the support. I think there are tools that might need to be improved, like the time where you submit a product and you end up starting with it. In some other countries are implemented that it can be requested at any time, and with a calendar that usually cannot wait 6 months or 1 year. This is the typical thing that I would say would improve, particularly the schedule and the implementation for a company to start in.
Yep. Thank you. I think that we may open the round to possible questions from the audience. I don't know if anyone wants to ask anything to our colleagues. Don't be shy. Yeah, down there. Any other microphones, maybe?
¿Quién ha levantado la mano?
Yeah.
Hi. I know that you've been talking about that is very long time for the launch and everything and the instrument that you're going to use. Usually in astronomy, we have the plans for, okay, we're going to launch this telescope and with technology of an iPhone 1. Even though right now we have iPhone 15, for example. Have you, I know that is kind of tricky, but which is the plan in 20 years to set, we are using computers with Intel 9 instead of using Intel 20 in 20 years, for example? This is a question from my side.
Maybe I can comment something there. First of all, I don't think that we will ever use Intel-like or high-power consumption in satellite. It looks more like ARM-based processors or something like that. Sometimes I heard of intentions to use GPUs on board satellite. That would be, of course, a game changer, but I'm not really sure about that for power consumption.
Maybe I will explain myself. The point is that, that even though GPUs, CPUs, whatever technology that we have right now, in 20 years it's going to be more advanced. This is how we are going to contrast saying that why we are using that.
Maybe a little comment here as well, that the computers have to be space qualified and radiation hardened, and that usually means then that they lag about 10 years in technology, unfortunately, because that takes a long time. But maybe that can be improved, of course, so it's possible.
Yeah, I fully agree. That's the main point, that probably you can consider the technology that you have right now and add these 10 years to properly qualify that for space, and those may be the ones that are built into the satellite that will be launched 10 years later, this kind of thing. So that explains that, basically. Anyone else, or another question? Comments, opinions? No? Yep.
What should we do? The scientists, for you, what is what you need from us?
I think we need you to tell ESA exactly which are the developments so they can put the activities, because we will be ready to respond to those ITT. And that give us the clues to know where to put our efforts, our strategy to help us very much to follow you and to help you progressing.
I was about to say that what we need to do is to sit together and talk. And start putting challenges on top of the table, tell us what is, which are your concerns, and we can try to find solutions together.
Yeah, just from what Frederick Safa was saying in his talk yesterday, is he seemed to indicate that basically we will do a study late next year, probably 2027, and that CDF study then will finalize the parameters for the mission. And once we have that, then they can put out tenders for technical studies of how to achieve this. And they already have a good idea of the kind of numbers we're thinking about. but we need to refine them and fix them then to make requirements.
Yeah, I wanted to comment also, going a little bit into the details. I mean, we here in CNR, we work a lot in the products program, so in which we develop certain elements for your experiments. And it's quite often that when we intended to start the activity, the requirements are not frozen yet. So this is quite important for us in order to be able to trigger the activity. Otherwise, we are stopped by ESA, because ESA say, you need to give us commitment on this development, but I cannot give you any commitment because I don't have the requirements frozen, the specifications. So it is something that I think we need to, perhaps, I don't know if we work together, but try to speed it up in order to have it as soon as possible consolidated in order to trigger the development activities.
In some cases, I will not say which ones. I have seen first the implementation and then the requirements definition. Then you are sure to fulfill them. But anyway, if anyone else has any other comment or question, just wanted to try to make a bit of a summary. Some things that also wanted to highlight. I don't know who of you mentioned that. That in these very long projects, I think it was you, that it's also very good to make sure that the know-how, the heritage and the legacy of studies that were, it was you, that perhaps even politics enter into the game or privacy requirements or whatever. So it's a very long run, so we should make sure that knowledge, for example, from Gaia is not lost when we are approaching Gaia NIR. We have to consider the high data rate, the optical communications perhaps, cryogenics, these noise vibration considerations, those are also very useful. Keeping up in sync the development and funding pace and make sure that we can keep up the teams and all the developments that are needed in between the funding steps that there are. So keeping up the momentum. These are very long projects, I insist. And yeah, we basically need to make sure that there are clear evidences of interest on the scientific, on the technological and industrial, and on the administration point of view. And with this, I guess that we can manage to make Gaia NIR successful. So I think that's it. Thank you. Thank you very much. Thank you.
No, ahora sí. Remember, we're taking the picture now. So the people in Zoom, please open the cameras if you want to appear in the picture. And the rest of you, please stand up and come down here because we're going to face the chairs. Okay?
Fazemos a foto, era?
Sim. Hola. Yeah, everybody, yeah? So companies, industry, scientists, all together in the picture.
Oye, y yo también. Imaginaos que soy un datos de Gaia comprimido.
Okay, take a seat. Okay, let's start the last session of the day. ¿Le cambio el título? Es más cortito. Okay, the first speaker of the session is René Dufart from the Instituto de Astrofísica de Andalucía, and the talk is about the solar system objects, Gaia in the solar system. And, well, you have 15 minutes. I will... Bueno, son 15 más 5, me levantaré a los 15.
Okay, thank you very much. This ¿Le doy? ¿Aquí?
No, we are sharing now. Tienes que compartir la screen. Vale.
Okay. Okay. This talk was given by Álvaro Escandal and me, but Álvaro couldn't come, so I will give all the talk. The idea of this talk is to present results on the Gaia. Yes, Gaia observed also objects in the solar system, and the main idea of the talk is to present how can Gaia NIR use this data to obtain data on the objects, on the solar system. No. ¿Estas? Oh, no. Empezamos otra vez. Vale. Okay. So for stars, for the normal, this is the focal plane of Gaia. For asteroids, this is a very different observation. And for stars, you can detect the stars in the left part of the CCD and follow the star along all the CCD. For asteroids, during the transit of the object in the focal plane, the asteroid moves. So you need to define how to observe this by software. So this is two different tracks, two different asteroids along the long scan direction, and you can follow and do the photometry and the astrometry of these objects for the transits. For every asteroid, more or less, during the world mission, the observations were around 60 to 100 times each asteroid. And Gaia observed around 150, 160,000 objects, asteroids in the solar system. So the main structure of the data processor is you identify the source in the focal plane, and then cross-match the source with the ephemeris and make a transit list. You can identify which object is that is doing the transit. Then you have the ingestion and the identification of the object, and the first result is the astrometric reduction of the object. You can obtain very precise astrometry of the object that helps to improve the orbit of these 100,000, 150,000 objects in the solar system. Then, in the G-band filtering, you can do the photometry. After the photometric processing, we can obtain the G magnitude of this object. And after the validation, all this data is going to the archive. Also, we can obtain some spectra of the object. that they have the same way as with the stars, with the RP and the BP spectra, but here the spectra is reflectance spectra. We need a post-processing of the spectra. I will show some details. And after this processing and the validation, we got the output to the archive. So in summary, we obtain data of more or less NIAs, near Earth objects, around 1,000 or 2,000 objects. The main bulk of information is in main bell objects, around 2 and 4 astronomical units. Then we have Trojans here, and only a bunch of trans-Neptunian objects. And this is the asteroid published by Gaia NIR 3. So we have here a semi-major axis plus eccentricity and semi-major axis plus the inclination, and you can see the density here. The plots in the below in the back is the G magnitude, the limiting magnitude of the objects, that is around 20, 21 in G magnitude, that correspond to around 16 in H magnitude, which is the absolute magnitude. I will tell you later what is this, but this is the first physical parameter that we can obtain from the photometry. H magnitude, the absolute magnitude, is related with the albedo and with the size of the object. So started with astrometry. If you follow the photocenter of the objects on the main apparition of the body, you can compare with the predicted orbit, and if you find that the astrometry have something like this, some variation in a sinusoidal orbit, you can make the interpretation that you have a satellite in that object, and then you launch a call for observing this asteroid, and you confirm that you are discovering only with astrometry that this object is binary. That is the case of this asteroid Arecibo. So this is the first result only doing astrometry, and when we enter in the photometry field, we need to remember that we are observing objects that are more or less potato-like objects that are rotating around 8 hours of rotation. We do not know this axis reference, the long versus short axis, we don't know. We don't know the rotation pole of the object. We don't know the period of the object. And you observe this one time, only one point of this curve, and then after hours you observe another point, and then after days maybe you observe another point, and then you need to reconstruct this rotational curve. And the idea is to reconstruct this shape of the object and maybe the orientation of the rotational pole. In NIR 3, the information is only the photometry, but in NIR 4, we will have the information on rotational curves and sizes and shapes of the objects. Also, we need to remember that another variable here is that the objects are moving, and they are moving close to you, and the phase angle is changing. Phase angle is the angle between the illumination, the observer, and the object. And so with this in mind, we can start to obtain results with only Gaia data. If we plot G magnitude over phase angle, we can obtain this straight line that gives us some information about the surface, the kind of surface that the asteroid has. So if we plot with all the photometry that we have on this asteroid, Eurybates, which is a Trojan asteroid, we can obtain this slope, which in this case is 0.05, and the H magnitude, which in this case is around 10. So from the absolute magnitude, we can obtain the diameter, assuming some albedo, and from the slope parameter that usually was assumed to be 0.15, which is really different with the one that we are finding only with data from Gaia. So very homogeneous data. And this is part of our work. So from this kind of plot, magnitude over phase, we can obtain this kind of information, slope parameter and age magnitude for 150,000 objects. And this is the plot of G magnitude corrected for the distance to the object versus phase angle. You can first see here that the objects always are observed 10 degrees far from the sun. This is a characteristic of Gaia observation. This is not good for us, so we need to put here more information from ground, from telescope on ground, to fulfill this gap here between 0 and 10. I'm showing here only the first 100 asteroids, but we have similar plots until the asteroid number 100,000. And this is the distribution of the slope parameter. So I told you that the slope parameter for all asteroids were assumed to be 0.15, which is here. And the after Gaia, we can see that this is really a different distribution of the slope parameter. So this is telling us that something is different in the surface, maybe more dusty, maybe more combination of dust and ices. And transforming this information with to H magnitude, we can see here that we can go until H magnitude around 16, which is giving us something about the diameter in the main belt is around something like 10 kilometers. Spectroscopy. With the blue and red spectra, we can obtain also the spectra of the object. This is reflectance spectra, so is the light of the sun reflected in the surface of the object. So the spectra obtained by Gaia need to be reduced, need to be divided by the solar analog solar star. And we can obtain this kind of spectra, this blue part and then the red part. And for each object, there is a mean of several observations. You can see in the red part here, one of these is one spectra, and then the mean of this give me this red spectra. We note some problems, mainly in the blue part, very noisy here, very noisy also in the point where both spectra match together, and very noisy also in the reddish part. So after some processing, after making the mean of all the spectra here, we can obtain, using a bias, a bin bias, a bin, to obtain like something like a low spectra of all the objects. That give us some information, not too much, but give us some information about if this object is made by silicates or made by ice or made by more carbonaceous surfaces. So, some example from spectrophotometry of Trojan asteroid. You can see spectra here and very flat spectra, no information. Maybe only the slope can give us some information, but what kind of mixture of ice and silicates we have in the surface of these objects. So what can Gaia NIR, what can we do with this? We do not expect a significant photometry improvement, but we do expect a spectroscopic improvement. This is the summary of the talk. So, for spectroscopy, near-infrared spectroscopy, we have today around 1,000 objects for spectroscopy in the near-infrared obtained by ground-based telescopes, showing that the objects in the surface of the object is made by silicate, ices, or a combination of these, which give more or less nothing. It's a flat spectrum. And we can only glimpse at the large scale distribution because the spectral range, the visible, is really not a good range to obtain the mineralogy of the object. But if we go to the near infrared, we can obtain this kind of spectra. In the blue, there is this object with this very flat. This is a ground telescope obtained. So we have these gaps here because we have the three main filters. And we have Eris here, which is an icy surface with a lot of absorption bands that we can identify if we have methane or nitrogen or water on the surface of these objects. The green points is the bin assuming the same bin as we obtain in the visible spectra of Gaia. So if we assume that we can obtain the same kind of spectra in the infrared range and assuming the same bin, we can see that yes, we can have a really nice low spectra in the near infrared, and we can go from 1,000 objects to 150,000. So today in photometry, more or less, we have 170,000 magnitudes in the near infrared. Most of them are in Y filter, and in JHK we have less information. And we expect that Euclid will provide around 150,000 spectra of asteroids, but avoiding the ecliptic plane, because Euclid will not observe that. So the idea is to see after these surveys what will Gaia NIR will improve in this. So assuming the same depth that Gaia, in magnitude depth, that Gaia will go, so up to G around 19, we may expect to reach J around 18, which means absolute magnitude around 16 for a main belt asteroid, which is 3 magnitudes deeper of the current largest survey today. Thank you.
Okay. We have time for questions. Is there any question in the room? Okay, Michael. Sorry.
If the Gaia NIR spectra go down to something like 2 microns or so, would this be sufficient to become sensitive to thermal emissions from asteroids?
No, thermal emissions start at 3-4 microns in main belt asteroids. If we are talking in trans-Neptunian object, it's really more far away.
Okay, Alessandro. I understand that since the light of the asteroids is reflected from the sun, they're much brighter in the optical rather than infrared.
Right.
So I wonder, what is the role of Gaia NIR, especially after, because this is going to happen after the end of the LSST survey.
Right.
So I wonder if LSST is probably is it going to observe everything that can be observed with Gaia NIR?
Yeah, in photometry.
Right. Okay. Okay.
So
that's why you said spectroscopy.
Yeah. The improvement that we think is only in spectroscopy. In photometry after LST, after Euclid, I think nothing can be added. I'm thinking in 20 years. Yeah. But in spectroscopy, yes.
Right. Okay, thank you. Let's thank René again. Okay, the next speaker will be Sagar Malhotra from the University of Barcelona. So he will be talking about improving the census of unresolved binaries. 5 minutes and I stand up. Okay,
Okay, hi, good afternoon. I'm Sagar Malhotra, PhD student at the University of Barcelona, working under the supervision of Friedrich Anders and Alfred Castro-Genard. So today I'll be discussing about how not only Gaia NIR astrometry, but also Gaia NIR photometry can help us improve the census of unresolved binaries. So yeah, so why study the unresolved binaries? Well, about 50% of the solar type stars in the galactic field are found to be in multiple systems. This has been reported multiple times in the literature, and stellar encounters can lead to the disintegration of binaries and exchange of companions. And this effect becomes particularly important for dense regions, for example, open clusters or globular clusters. And studying the mass ratio distribution in those clusters can help us understand the star formation and their dynamical evolution. So what is the nature of mass ratio distribution? Well, it has been studied quite a lot, but there's still not consensus. People have found that it is monotonically decreasing or increasing, and a recent study by Cordoni and others on a sample of 78 open clusters found that it is more or less flat for most of the clusters. Okay, so what is the state of art? The good thing about using open clusters is that we can have a very good distinction between the single and binary stars. So people have tried to construct a ridge line to enhance this distinction. They have used probabilistic generative modeling or mixture models, and some have also used the baseline. It is a Bayesian approach to compare the observations with the theoretical isochrons. And with this method particularly, you can get individual mass ratios. The thing about this method is that it can be time consuming. Okay, so in our case, the motivation is still the same, that we use this particular displacement of a particular unresolved binary system from the single star main sequence, which is shown here in the black, to get the individual mass ratio. And we can use the photometry to study all those systems at once. As you can see in here, for mass ratios greater than 0.8, the locus becomes parallel to the single star sequence. So there is some sort of a degeneracy in mass and the Q, in the sense that the same observations can be described by either a high primary stellar mass and a low mass ratio, or the other way around. So we need very good description of the single star sequences. And there can be cases in the literature where the cluster parameters found by the studies are not the optimal fits. So we do need to have the improvement in the cluster parameters as well. So first of all, setting up the problem, we would like to infer the primary stellar masses and the mass ratios. We use the observables, which are the multi-band photometry coming from Gaia, 2 mass and Weiss, and the Gaia parallax. And we would like to infer the astrophysical parameters, which are the primary stellar mass, the metallicity, age, the mass ratio, the distance, and the line of sight extinction. So our main idea is that using the infrared photometry and applying the cluster parameter priors can help us break some sort of degeneracy in these parameters. And we use simulation-based inference, which avoids the need for an explicit likelihood. And when trained on a simulated training dataset, we can use it to infer posterior distributions. And one thing to note here is that both Gaia NIR photometry and the astrometry will lead to an improved quality of the observables, specifically the NIR photometry, which will be available for more number of stars, and improved parallax. And this will inherently lead to a better estimation of mass ratio and other parameters. Okay, so this is an example of what you would typically get when you use SBI on a simulated star. And here we have the posterior distributions for the 6 model parameters, and they are quite poorly constrained, and they are also affected by the degeneracies. So one way to break these degeneracies is by using cluster parameter priors. And we develop a new iterative method for inferring cluster parameters. So yeah, I hope it works. Okay. So in here, you see that with each iteration, we are applying an automated method of selecting stars based on their evolutionary phases. And specifically for age, we are only selecting the main sequence ton of stars. One thing to note here is that the initial guess is heavily influenced by the presence of blue stragglers. This is a case of a real cluster M67, and we are using the membership lists from Hunt and Rifford catalog. But our method is able to remove these blue stragglers in the selection of the main sequence ton of stars and improve the estimate with each iteration. And we have kept the metallicity fixed throughout the iterations because there are some known issues in estimation of the metallicity using only photometry. Okay, so once we have our cluster parameters, we can see if we are able to improve the posterior distributions. This is the same example which I showed earlier, but only for masses and the mass ratios. And what if we apply the cluster priors? So now the posterior distributions are very well constrained, and the model parameters are quite robust in this case. I also discussed about incorporating infrared photometry. So in here, this is another simulated star, which is a solar type star, and the simulated mass ratio was about 0.3, which is shown here in the orange dashed line. And if we use only Gaia photometry as observable, we would get that it is more likely to be a single star, and the mass ratio would be close to 0, even though we are able to get good primary mass estimate. And what if we include the 2-mass and vice photometry? So in this case, even though the masses are still the same, now the probability of it being a binary is much higher, and the mass ratio is very well estimated. So with these two pieces together, we can say that incorporating the near and mid-infrared photometry can significantly enhance the detectability of low mass ratio binaries. So this was the case for individual stars, but if we do this for cluster members and on a cluster level. So on the top, you have the comparison of the primary masses and the mass ratios when we don't apply any cluster priors, and at the bottom when we do. Of course, there is a significant improvement in the two estimates, and on top of that, we also decrease the uncertainty by an order of magnitude or so. Also, one thing to note here is that due to large errors in observations, especially for faint stars, and this is particularly for the parallax, there can be some false classifications. So we do need some sort of a threshold on the mass ratio, above which we can reliably detect unresolved binaries. And for this particular simulated cluster, we have it as 0.23. And contamination rate for such a threshold is less than 5% for bright stars. And in here comes the Gaia NIR astrometry, because as was also discussed by David Hobbs in his presentation, that the parallax would be improved significantly, especially for the faint stars. So with the Gaia NIR astrometry, we would be able to provide robust estimates even for the faint stars. But if we apply for this whole machinery to a real sample of open clusters, so we did some quality cuts, and finally we have 130 open clusters with decent quality colorimetric diagrams in multiband photometry. And our method is able to predict good enough cluster parameters for about 42 of them. And the median mass ratio threshold for cluster members with only Gaia NIR and with only Gaia photometry is 0.48. Well, it has been a lot of time since I have been saying Gaia NIR, okay. And when we use both 2-mass and vice photometry as well, we drop it to 0.27. Yeah, and this will of course be a similar improvement for Gaia NIR, but for a large number of stars, about 2.5 billion of them by the end of mission. Okay. And just an example for two specific clusters for NGC 2360 and M67. So we have the colorimetric diagrams colored by the primary masses and their corresponding uncertainties on the top, and the mass ratios are the same. So we do recover very well the binary sequence and the uncertainties. One thing to note here would be that the uncertainties, even though they are quite precise for most of the main sequence stars, they are increased for the stars near the main sequence turnoff. And this is quite actually reassuring, because the equal mass binary sequence and the single star sequence are very hard to distinguish in this region. So I'll like to conclude with another 2 slides. So we also looked at the binary fraction and trend with cluster parameters. And just to keep things homogeneous, we have a mass ratio threshold of 0.6, comparing with the cluster age, distance, and metallicity. And on the left, you have the corresponding Kendall coefficient matrix. So what we see that the binary fraction tends to increase with the cluster age. This doesn't mean that there are new binaries being formed. It just means that because binaries are more likely to sync to the cluster center, and there will be no mass stars in the cluster halo, they would just be more likely to be disrupted. So this decreases the number of single stars. So that's why it increases the binary fraction with the cluster age. With distance, I'll say it's expected because there'll be more number of stars which remain unresolved at higher distances. And for the metallicity, even though this has been reported in the literature, we still find that in the correlation coefficient, it is still correlated with the distance. So it may reflect some sample selection effects. And another trend which we looked at was the variation of this binary fraction with respect to the primary stellar mass. And we stacked all the results for the 42 open clusters, and we see that for all the detected binaries shown here in red, it very well follows the RNO 2011 fit. And one important thing about this fit is that it was done on the field stars. So what we can say is that for masses greater than 0.6 solar mass, the multiplicity in open clusters agrees well with that in the field, especially for the close binaries, and an excess is observed for low masses. The excess is probably because of the low mass isochrone systematics, which is very well reported, and this can inflate the unresolved binary fractions in that regime. But alternative explanations can also be that maybe low mass stars in open clusters are likely to be paired with high mass ratio systems, or there is a preferential loss of low mass single stars. Okay, so just to conclude, we have developed a fast method to obtain the joint mass and the Q posteriors for cluster members while simultaneously fitting for cluster parameters. The binary fraction with respect to the primary stellar mass mirrors that in the galactic field, especially for masses greater than 0.6 solar mass, and it may be biased for systematics for lower masses. Okay. And just to conclude how Gaia NIR will improve even for this particular science case, it will bring huge improvements, including that IR photometry will significantly improve the detection of low mass ratio systems which are otherwise not detected by Gaia-only photometry. And precise parallaxes will enable robust mass ratio estimates, especially for the faint stars. And we never know, there might as well be, well, I don't know if anyone has discussed this, there might be new detections of open clusters near the galactic center. And there might be improvements. Of course, there will be improvements in the stellar evolution models in the low mass regime. So yeah, but next, personally, we are now working on how presence of an unresolved companion will affect the characterization of field stars. And well, the initial results do seem promising. Okay, thanks, that's it, thank you.
Okay, are there questions for Sagar? There.
Thank you. So in your results, you are showing that you will be able with Gaia NIR to get better concern about the binary fraction, but will you also be able to get better measurement with the relation of the binary masses and the periodicity of the binaries around these primary stars, using the long baseline between Gaia and Gaia infrared?
You mean about the astrometry?
Yeah.
Using the astrometry. Yeah, of course. Like there might be some systems where the Rouvet will be inflated in that case if we have the joint solutions, of course.
So you will be able to reconstruct the periodicity, right, of the orbit or not?
Yeah, of course. But the thing is, there was a paper by Alfred, so 2024. This Rouvet, at least for Gaia DR3, it is only like a good estimator until say 200 parsecs, and maybe for some systems until 1 kiloparsec. I really don't know how it will improve for Gaia NIR when we have like 20 years of difference. It of course will improve, but this is just a case if you have very far away open clusters, instead of using this astrometry, you can also use this method to get good estimates on the mass ratio. But of course, I completely agree about that.
No more questions? Okay, let's thank Sagar again. Cuando me levante faltarán 5 minutos.
Hello everyone, going to present a science case for massive young clusters. There's quite a lot of interest in these sort of clusters here in the Spanish community. Mostly the same groups that are doing massive stars, but with Gaia NIR, this is a case that can go well beyond the massive star community. So I'm going to start by defining what I mean when I talk about massive cluster. That depends on environment. It's not the same in a starburst galaxy as in the Milky Way. In the Milky Way, in about 10 years ago, there was this symposium in one of the IU meetings, and it was decided that we're going to call massive something that was above about 10,000 solar masses. But I would like to give a more, say, physical definition, and I mean with a massive young cluster is a cluster that allows you to set an experiment in itself. And what I mean here is with a 10,000 solar mass cluster, you have about 20,000 stars of a given age and metallicity. So you have numbers, you have statistics. There are experiments that you can do with those stars if you can observe them. Now we are observing the massive stars mostly, but with Gaia NIR we can reach much, much further down the main sequence. So this is what you call a massive cluster generally. This is a young cluster in the LMC with about 20,000 solar masses and a nice collection of red supergiants. And we have things like that in the Milky Way that are reachable, even though until about 25 years ago, people thought that these things didn't exist in the Milky Way. But some of them were hidden by extinction, and some of them were simply not recognized. Just to give you an example, this cluster has been studied for a long time as a normal cluster with mass estimates of about 1,000 solar masses. But with Gaia, we have found that its true mass is much, much higher. And this is something which is at a relatively nearby distance and with little extinction. We combined the Gaia data with the spectra for more than 140 cluster members. And this cluster has a present-day mass of about 8,000 solar masses, which implies an initial mass well above 10,000. When I mean you can do experiments with it, what can you do? For example, just looking at the massive part, you have about 50 B2 stars here of different luminosity classes, and they all have the same age and composition, so you can look for other things within the spectral type, for example, with 50. Here you have different diagrams that we apply with different stellar models to certify that there's a population of blue supergiants that cannot be explained with single star evolutionary tracks. And there's a population of them. There's not a single star. So that means that supergiants probably are formed in a different way. Are there any other clusters like this in the galaxy? Well, not many that we know of. This is one. Here is more complex. You see, we're getting to extinctions close to 8 magnitudes, but you can still do this in the optical. This is a slightly more massive. It's perhaps a bit younger. This is interesting because it has a very bright CFIT here. This is a direct confirmation that stars between 11 and 12 solar masses can be CFIT variables and be very bright, which is also interesting. These are the two that we know that are visible in the optical. There may be many more. In fact, this is an infrared image of a region close to the end of the galactic bar. And here there are collections of red supergiants that we have identified that quite possibly are massive clusters. And I say quite possibly because we only see the red supergiants. We don't see the rest of the cluster. And this is not because we don't see the stars. It's because looking towards the bar, the background is so dense that we don't know which stars are members of the cluster and which ones aren't. But with Gaia NIR, of course, we can solve this. In fact, if you look at the distribution of these sort of clusters that we know in the galaxy, you can see in green you have objects that were known in the 20th century. In yellow, they have been found this century. In purple, you have objects that are visible in some way in the optical. In red, you have objects that you need to go to the infrared. And you can see that we are probing a small region of the galaxy. There must be many, many more. We can be quite sure that there are many more. This, for example, is M11, which is a very well-known cluster, which is only less than 2 kiloparsecs away. And now it has around 10,000 solar masses. It must be the descendant of one of our objects and is in the neighborhood. So there must be many. So these clusters are very interesting. as laboratories, you can use them as proxies of the starburst conditions that you have when most of the stars were formed at cosmic noon. You can probe the IMF under extreme conditions. You can see if protoplanetary disks can survive when you have all the ultraviolet emission from hundreds of OB stars. You can see what are the most massive stars, and as I say, there are many, many other things that you can do if you can go down the main sequence. Just to give you an example, this is what Gaia has done. This is a field in which apparently there's absolutely nothing, but if you do proper motions, you find a number of objects, and if you isolate those objects, you have a very nice cluster there. It's a cluster that we found some time ago, that was also found in Barcelona. It's a cluster of about 75 million years old. It's a bit older than our young clusters. It has a distance of only 2.3 kiloparsecs, and it has a mass of about 10,000 solar masses, and it's just there. This is close to the Scutum star cloud. M11 is here, and this cluster is here. This is about 2 degrees, so this is telling you that these things must be common. And these are the clusters that were known before Gaia in this area with the catalog of Cantat Gaudin. These are the clusters that are known with Gaia DR3 in this area, and you can see there are many more. We have gone over some areas of high extinction. You reach about 3 kiloparsecs in this direction, but for example, you can see there's absolutely nothing in the star cloud, and this is not because of extinction, but exactly because there's no extinction, and it's too crowded for Gaia here. So if you look at the distribution of young clusters, these are from Hunt and Reffert, you can see here the spiral arms by rate, and you can see the fit is not very good. But the interesting thing here is that the arm that you cannot see is this arm that is here. This is the Scutum arm, and for Gaia, this is a blank. And this is a blank because it's dense with molecular clouds, and Gaia cannot go there. So if you go towards inside the galaxy in any direction at 3 to 3.5 kiloparsecs, it's blank for Gaia. You don't see anything. Almost. You see a little bit. You need to have something really bright to see. Something like this, for example, the most massive young open cluster in the Milky Way, Vestron 1, which has about 100,000 solar masses and lots of very, very bright stars that shine through the dust. Then you can use Gaia to say that this thing is not as distant and massive as people thought, but that's because you are not using Gaia correctly. In fact, if you just apply code and tell it to find a cluster there, it will give you this population, which is a population, but if you look at it, it's not a sort of population that you find in a cluster. And in fact, the point is that the cluster is behind the Scutum arm, and if you look in this direction and ask to see a kinematically coherent population, it's going to find the population of giant stars in that arm, and it's going to ignore the cluster, which is here. You have thousands of stars here, you have the cluster here, and you need very good proper motions to solve this. But if you help a bit and tell Gaia where the cluster is, then we can do a lot of tests, statistical tests, and be sure that we have identified the cluster and give pretty accurate parameters for it. This is in the optical with Gaia, and you get something very nice, but there are many issues about completeness, about the huge zero-point offsets that many of these objects have, which are scary, comparable to the parallax. And now, if you go into the infrared, you can take a spectra, things, get accurate parameters for hundreds of stars, which is what Raúl Castellanos, which is a student at CAP, has just done. Now we have accurate parameters for this cluster. It's about 6 million years old. And this means that all the most massive stars have evolved away from the main sequence, and many of them have exploded as supernovae. If we want to know which is the most massive star, we need to go to a younger cluster. This was done in the Arches cluster that was mentioned this morning in the talk about the galactic center. Arches cluster is close to the galactic center, and there's this claim that it doesn't contain any star more massive than about 150 solar masses, and that this is the upper limit for stars at solar metallicity. This is not clear. There are claims of a more massive star in the LMC, close to 300. The point is that when you go to these very, very high extinctions, you start having a lot of problems that have been mentioned this morning. You talk about the galactic center, and this results in estimates of cluster parameters that change continuously from paper to paper, age, mass, extinction, everything changes from paper to paper by a large amount, and we need a lot of help from Gaia NIR to look at that. Another example is another very massive cluster, which is very young. There was a long-term argument about the distance between 3 and 8 kiloparsecs, and Gaia has settled for about 4.5, and we are sure about this. And so we know here we have another cluster with a claimed mass of about 30,000 solar masses. So there are many of them that we can see. This is another one. I'm going to skip over this. Going to just come to my conclusions, which is that I'm pretty sure that there must be dozens of very massive clusters. If they are not young, we are not going to be able to see them probably against the background. If they are young, they're going to have many bright stars from which we can get the proper motions of the cluster and then identify the rest of the cluster. And we already know about a few that have red supergiants, and we want to complement this. But of course, we're going to have all these laboratories that allow us, with Gaia NIR, to reach down the main sequence, down to solar-type stars, and perform a lot of experiments under controlled conditions. Thank you very much.
Thank you, Ignacio. I forgot to introduce him, Ignacio Negel from the University of Alicante. There are any questions for him?
Ignacio, you have told us about the missing mass in massive clusters, but, and what Gaia NIR could do for finding these missing stars. But what about the missing open clusters that we have not seen? What is your predictions for the future? How many completely new open clusters do you think that Gaia NIR would be able to discover?
Depends on what you call a cluster, because many of the things
you make your own.
Yeah, many of the things that Gaia have found are small groups in the solar neighborhood that we are not going to see at 8 kiloparsecs in the optical, in the infrared, or in the gamma rays. But if you mean true clusters, I think there must be many hundreds in the inner galaxy.
That we have not seen yet.
That we have not seen yet. I believe there are many hundreds and probably many thousands in the inner galaxy. Yeah. Maybe they dissolve very fast, but young ones, there must be hundreds, I think. Yeah.
It's not a question, but just to add on that, there'll be sometime this week or next week a paper about cluster selection function. So maybe that can help answering. No, not Gaia NIR, of course, but sorry, not a question.
Any other question? Well, if not, thank you again, Ignacio. Now, Nuria Miret.
¿No?
Ah, perfecto.
Sí, y el poso...
Un poco eso. Okay, so Nuria Miret from the University of Barcelona is talking about the transforming our view of star and planet formation.
Vale, perfecto.
So, good afternoon, everyone. I will talk about how Gaia NIR can transform our view of star and planet formation, and this talk is going to be complementary to several that we have heard today, this morning on Sarah and Miriam, and now about Ignacio. And I think this only strengthens the case on how Gaia NIR is going to really revolutionize our view of star and planet formation. And before starting this presentation, I would like to acknowledge my collaborators, because to present this talk today, we have gathered together all our works, and so I will try to present an overview of several science cases that impact this topic. Therefore, I will not have time to go into the details. I will just try to get a first impression, and I'm happy to discuss this further in the questions or later on. So essentially, this is the big picture we are trying to answer. So how we go from one molecular cloud into a family of young newborn stars. And to answer this question, Gaia has been key to analyze the properties of very young stars and several parameters such as the initial mass function, the spatial distribution, dynamics, ages, etc. So Gaia has been very important in characterizing these properties that tell us about the initial conditions of the cloud, where the star formation began and how propagated it through the cloud. But this is still an incomplete picture, and Gaia NIR can improve here a lot. First of all, because it will allow us to see through these molecular clouds and therefore see earlier stages of star formation than what Gaia can see. And also because since we are going into the infrared, we are going to be sensitive to much cooler objects and therefore all these planetary mass objects that Gaia is missing. So my talk will show now several science cases taking into account these key advantages of Gaia NIR. So first of all, Gaia has provided a revolution of our understanding of OB associations, and particularly in the solar neighborhood for Scorpio Centaurus, only at 120 parsecs from the sun, we can now resolve very well the substructure of these regions, and we see very clearly different subclusters very well aligned in 3D positions, and that also show some age, velocity, and mass gradients that overall all this information allow us to understand that star formation began at the core of Scosene and propagated outskirts through these cluster chains to the outer regions of this OB association. Now, the limits of Gaia are still that we cannot see the stars that are still embedded at the outskirts of this OB association. The stars are missing, and only we have the resolution to see all this substructure for the closest OB associations. Orion at 400 parsecs is already much more challenging because we have these fingers of God due to the parallax uncertainties, and if we try to go to farther and farther regions, this only gets more complicated. So in this case, Gaia NIR will allow us to see on one side all these populations still embedded at the outskirts of these cluster chains, and also will allow us to transport this resolution that we have at only 100 parsecs to other regions, and therefore allow us to test whether the star formation scenario that we have seen in Scosene is the norm in the galaxy, or whether it depends a lot on the environmental conditions. Then another science case, so Gaia has showed us that all young clusters, or most young clusters, are expanding. This is possible now thanks to the excellent kinematics that we have on Gaia that allow us to integrate individual stellar orbits back in time. What you are seeing here are individual members of the Beta Victoris moving group, and you see that the stars were most concentrated in a point where the association was born, and this provides us a dynamical traceback age that is complementary to isochronal ages and give us a lot of information about the dynamical state of the cluster. So here the limitations are that first, we don't know what's going on about the dynamics of still embedded clusters, and also that we need a really high precision in the velocities, below 1 kilometer per second, in order to do these precise orbital tracebacks. Good news here are that we have a lot of spectroscopic surveys available or coming that will produce very precise radial velocities comparable to the tangential velocities that we can obtain with Gaia or Gaia NIR in the future. And Gaia NIR will also tell us all about the dynamics of the still embedded clouds, and understanding these dynamics is important to understand these early expansion motions of the cluster and also how the parent molecular cloud vanishes after the formation of stars and what is the impact of this parental cloud evaporation on the expansion of the star cluster. Then, moving now on the ultra-cool dwarfs. So Gaia was not designed to observe ultra-cool dwarfs because these objects are extremely cool and they shine more in their infrared, not so much in the optical, but still it was able to detect a few thousands of these ultra-cool dwarfs. And we have been able to determine luminosity functions, estimate the kinematics binary system, and several other properties of these objects. But obviously the limitations are the completeness at the faint and cool end. Also, the signal-to-noise and resolution of the spectra are obviously not great because, as I just said, the mission was not designed for this purpose. And also, the evolutionary models that we have on the optical are not as good as the ones we have on the infrared. Then, going on the infrared provides us better sensitivities, and we have better evolutionary models to understand what is the metallicity of the stars, or what is the atmospheric composition and other stellar parameters. And in particular, as Miriam mentioned this morning, Gaia has been great at detecting M-L dwarfs, but we have only been able to detect very few T dwarf and non-Y dwarf, while Gaia NIR should completely change the picture here. Then also one of the key questions, or one of the big questions regarding all these ultra-cool dwarfs is how do they form? Do they form similar to low-mass stars, or do they form in planetary systems that they later abandon? So to answer this question, we need to detect large homogeneous samples of brown dwarf and free-floating planets to characterize their properties in terms of the mass function, multiplicity, disk properties, metallicity, kinematics. All these together will tell us which is the dominant mechanism and how this maybe depends also on the mass of the objects. And here again, Gaia NIR will completely change the picture. On one side, it will allow us to detect the so-called proto-brown dwarfs. This is the equivalent stage of proto-stars, and understanding how are proto-brown dwarfs at these earlier stages is really important to see how they resemble or not the proto-stars and understand whether they form in a similar channel or not. And also characterizing the multiplicity and these fractions with the astrometry, photometry, and spectra from Gaia NIR will be crucial to see statistically which of these two mechanisms dominates. Now, I would like to give some numbers or some predictions of how Gaia NIR could change our view of these ultra-cool dwarfs. So, with Gaia, we have been able to detect astrometry of brown dwarfs. So, we have been able to detect at a distance of 100 parsecs, more or less, we have been able to detect objects as cool as 20 times the mass of our Jupiter. So this is excellent, but we cannot reach planetary mass objects only with Gaia currently. We need complementary infrared instruments to detect planetary masses. Now, the limitation of these infrared surveys is that they don't homogeneously cover the whole sky. They have very patchy coverages that, where the completeness depends on the 2D position and also on the filter that you use. And this eventually makes it extremely complicated to translate the completeness into the magnitude distribution and the mass function. Also, we don't have parallaxes for all these objects, which makes them harder to confirm as members of these young populations. We can only have proper motions in the most advantageous cases where we have observations separated by a long baseline. And also, we need to spectroscopically confirm the cool nature of these objects, and this is really observationally expensive. Again, Gaia NIR will completely change this because we are going to get simultaneously the astrometry and the spectroscopy for planetary mass objects. So here what I have done is assuming a magnitude limit of about 19 magnitudes in the J band. So in a case like this, at 120 meters and assuming an age of about 3 to 10 million years, this would mean that Gaia NIR could observe objects of only a few Jupiter masses, and therefore getting way into the planetary domain. So this is for very nearby regions, but Gaia NIR will also allow us to see and detect brown dwarf at much farther distances than what we can do now with Gaia. As I was saying, Gaia in these nearby regions can detect 20 Jupiter mass objects, while Gaia NIR will be able to detect also these 20 Jupiter mass objects, but at much larger regions of about 1 kiloparsec. Here at the right, you are seeing a plot that Victor prepared for this presentation, where again, he assumed a magnitude limit of 19 in the J band, and you can see how the limit changes as a function of extinction and distance. This has been done assuming 2 million years. We could also extrapolate this at other ages and to see so what would be the completeness and coverage of Gaia NIR in particular regions. And with this, I finish with my conclusions, and I just wanted to strengthen again that Gaia NIR will completely change the picture for these young stars and planets because we will be able to see through molecular clouds and therefore having access at these earliest stages of formation, and also because we will be able to detect cooler and cooler objects. Thank you very much.
Thank you, Nuria. Any questions for her? Questions?
Everyone is too tired.
Okay. Well, let's go. Thank again, Nuria, for her talk. The next speaker is Isabel Santos, showing cosmological simulations for Gaia NIR studies of the local group. Cuando falten 5 minutos me levanto. 15. 10 más 5.
Ah, 10 más 5. Okay. Hi everyone, my name is Isabel Santos and I'm a postdoc at the Institute for Computational Cosmology, and I'm a theorist, so I'm not going to talk directly about Gaia data, but about how we can use cosmological simulations to, in combination with Gaia NIR, derive studies of beyond the Milky Way in the local group. So we've heard during these couple of days that Gaia has revolutionized our view of the Milky Way, but not only of the Milky Way, but also the substructure around it, like the LMC and the SMC we've heard this morning, and also dwarf galaxies, satellites within 400 kiloparsecs of the Milky Way, and globular clusters. This is a view from within the Milky Way, but if we were to look from outside the Milky Way, we would see something like this. And this is a cartoon, but it shows that we currently know of around 60 confirmed Milky Way satellite galaxies. Many of these are what we call ultrafaint, so luminosities below 10 to the 5 solar luminosities. And these have been detected mainly by deep imaging surveys, but some have also been detected by Gaia, for example, Antlia 2 and Crater 2. I will come back to this idea later. This is still a limited view of our immediate environment because the Milky Way is actually part of the local group, which is a binary system together with the Andromeda M31 galaxy.
and with also dwarf galaxies surrounding this system. We have both dwarf galaxies that are isolated and dwarf galaxies that are bound to these two halos, which we call satellites. And in general, we define the local group as a spherical region with a radius of around 3 megaparsecs, and the distance between Andromeda and the Milky Way is around 770 kiloparsec. So this is the universe that we observe, but in our standard model of cosmology, the lambda cold dark matter model, it is predicted that the universe is actually dark matter dominated with a particular type of dark matter. We think it's cold, which is just a way of summarizing its particle mass. And this theory says that underlying these galaxies, there's a network of halos that follow some very robust characteristics, which can be summarized in these 4 points: that there are more small halos than large ones, that there's self-similar substructure around halos, that halos have universal cuspy, very dense in the center, density profiles, and then corollary of these predictions is that galaxy formation becomes increasingly inefficient in low-mass halos. Dark matter is still one of the most pressing and most fundamental questions in modern cosmology, and so we hope that data from Gaia NIR could help us answer this very important question. We heard this morning from Giuseppina Battaglia's talk that we expect the accuracy of proper motions to get so good that we'll be able to have very accurate orbits of dwarf galaxies at 1-2 megaparsecs from the Milky Way, with the same accuracy that we now have for the closest satellite galaxies. So in combination with this, in the light of this vast data, cosmological simulations become an evident tool that we would need in order to interpret this data. Why are they important? Well, observations give us snapshots of the universe, but simulations can provide full evolutionary histories. Simulations allow us to link kinematics to specific formation pathways. We can also link dynamics to the underlying dark matter distribution and star formation histories. And finally, the main idea is to place individual galaxies into the broad cosmological context. So there are many collaborations with different efforts of local group simulations. I will go through a few, but the main characteristic of these simulations is that they are zoom-in regions of a local group analog, which means that they select pairs of halos of a large volume parent dark matter only cosmological box, and then resimulate that smaller region at high resolution and many times with hydrodynamics. How a local group is defined, well, that depends on the different simulation, but in general, these definitions are based particularly on the masses of the halos, so that they match the data that we have for the Milky Way and Andromeda, the distance between the halo pair, that they are isolated from more massive neighbors, and they also sometimes include a constraint for the slope of the Hubble flow. This example that I'm showing here is from the Apostle project. This simulation has been run with the Eagle galaxy formation model at high resolution, 10 to the 4 solar masses in baryonic mass. And what we're seeing here is the evolution of, is a video of the stars, of the stellar component. And this high resolution, as you can see, allows us to distinguish tidal features around the massive galaxies, but also the small ones. There are streams, there are plumes, umbrellas, etc. This is another example of another simulation. This is from the Hestia project. This that we're seeing here is the gas density. It has been run with the Auriga model, which is a different model to what I showed before, and it's also a high resolution. A specific characteristic of this simulation instead is that it has constrained initial conditions, which means that the parent box, the large volume from which the local group was selected, didn't have random initial conditions. It wasn't a random universe, it was a constrained universe that reproduces the large-scale structure that we actually observe. So for example, it would have the Fornax cluster and the Perseus cluster at the right position in the sky, right distance, and right masses. And of course, those objects, which are very far away, 50, 100 megaparsec away, are not included in the zoom, but it is argued that they would generate a tidal field that could affect the dynamics of the small-scale structure. So these are simulations that are state-of-the-art today, but we're talking about Gaia NIR, which will come around 2040 or so. So we would expect that by then the technology has advanced a lot. It is said that computing power doubles every 1.5 years. And so what type of simulations would we want to have for then? Of course, the answer is always the same. We want higher resolution. We want to be able to resolve all these tiniest galaxies that form. We want to resolve tidal features like stellar halos, streams, etc. We want a large volume, and we want this to be within the correct environment. And so I'd like to talk about a project that I'm co-leading with the Sibelius collaboration to start the first efforts towards a simulation with these characteristics. So this would be constrained simulation. Sibelius is also a collaboration that produces constrained initial conditions. But this time we're aiming for a local universe, a zoom-in region that has 35 megaparsec radius. So we're talking about a volume 1,000 times larger than what is state-of-the-art today, and at high resolution as well. For now, 10 to the 5 solar masses, but given the increasing computational power that we expect, and probably by then GPUs will be the main type of hardware that we will be using, we would probably be able to run the simulation at 100 solar masses resolution using at the same computing time of, we estimate this should take some 15 million CPU hours. So this project is to run in CDM and in warm dark matter sterile neutrino flavors, but also to have hydrodynamical counterparts run with the new Colibri state-of-the-art hydrodynamical model. This model can resolve the multi-phase interstellar medium in large cosmological boxes, so it allows gas particles to cool all the way down to 10 Kelvin in a big box. So what kind of science can we do with these types of simulations? I'm going to give just some examples of work that I've been involved with and other work. One thing we can look at and study is the mass profile of the Milky Way and also the mass profile of the local group. So in this paper I'm highlighting here, we looked for LMC analogs in local group simulations and how they relate to the mass profile of their host Milky Way, gravitational potential. And what we found is that the LMC shows a 3D velocity that is very close to the escape velocity of the halo at that pericentric radius. So when we compare to data, then we can rule out different mass models, Milky Way mass models that are used in the literature, using the LMC, for example, and also using proper motions or 3D velocities of other tracer satellites, especially further out. Another question that we can answer is that of satellites of satellites. So lambda CDM predicts hierarchical structure formation. So there's substructure around substructure around substructure. And so we expect the LMC to have had its own satellites. We used local group simulations to study the dynamics of satellites at the LMC and therefore be able to give probabilities of association with the LMC to our observed Milky Way satellites. Another study that one can do is to study what's the fate of the local group. So the traditional picture that we've always been told is that the Milky Way and Andromeda will merge at some point in the future. But actually, local group simulations have shown that this is quite uncertain still. So when this work here by Tilsawala shows the probability of mergers between the Milky Way and Andromeda depending on which halo members you take into account. So if you only take into account the Milky Way and Andromeda, and you run your simulation, then there's a 44% probability of the merger happening. But once we include the orbits of the other more massive members of the local group, which are the LMC satellite of the Milky Way or M33 satellite of Andromeda, the results change. And they also change from DR2 to DR3. So we expect that with increased accuracy of our proper motions and orbits, we will be able to constrain further or better the fate of our local group. Something that's relevant to the work I do, constraining the nature of dark matter, would relate to this idea. So one way of constraining dark matter is counting satellites, counting substructure. And as I mentioned earlier, Gaia detected a few satellites. One of them is Antlia 2. These, and the other one is Crater 2, these are satellites that are quite unusual. They are very faint and very large compared to the other Milky Way satellites. And so there have been different work trying to understand these characteristics. So using velocity dispersion measurements for these two galaxies, you can estimate the central density, which I'm showing here in the bottom panel, and compare it to the pericenter of the halo. And so the densities that they find are quite low, below the density of the Milky Way host at that radius. So this suggests that they are suffering intense tides from the Milky Way halo. So then people have tried to model a galaxy in Lambda CDM that suffers tidal effects and see if they can reproduce the characteristics of Antlia 2, and the answer is no. So far, in a Lambda CDM universe where galaxies start with an NFW cuspy density profile, tidal stripping cannot explain the unusual size of galaxies like Antlia 2. So this Gaia is helping to detect objects that are very interesting from a cosmological point of view as well. And then finally, something that is relevant to the work I'm doing, maybe a long shot for Gaia NIR, but maybe worth mentioning. So our new high-resolution simulations of the Milky Way halo combined with modern subhalo evolution models in Lambda CDM predict that subhalos that are in cold dark matter can never fully disrupt. So this would mean that the Milky Way halo should be full of satellite galaxies, very tiny galaxies. And we predict that there should be some 60 or 80 more ultrafaints than we currently know. We also know that these should be very close to the galactic center. They had very early infall times and they're located very close to the center with small pericenters. And so I was thinking that maybe Gaia NIR, since it will be able to see through the galaxy, through the center, could be able to detect these stellar overdensities and maybe with astrometry isolate these tiny satellite galaxies, constraining the nature of dark matter. Other studies that one can do, I will just mention them, are one can use Gaia proper motions Gaia NIR proper motions to connect orbital evolution with morphologies and star formation histories. So in this paper, for example, we connected the orbit of M33 with the orbit of Tucana dwarf spheroidal. Tucana is an isolated dwarf galaxy, but it is quenched, and there's no explanation for this. So we suggest it's a backsplash galaxy, and it happens that with our simulations, we would predict it was ejected from the Milky Way at exactly the time that its data for its star formation history says it got quenched. And it could also explain, this interaction could also explain tidal features observed in M33. And then having proper motions of outer local group dwarfs at 1, 2, and 3 megaparsec could help us understand the Hubble flow, which is still an open question. The observed Hubble flow has a scatter and a slope that simulations do not reproduce. You can find a possible explanation in that paper, but it's still an open question. So my summary, Gaia NIR will revolutionize local group dynamics, but cosmological simulations will help guide the interpretation of this data by linking dynamics, formation histories, and putting everything in a cosmological context. And I'm happy to answer any questions. Thank you.
Thank you, Isabel. Any questions?
Hi, thanks for this very nice talk. I think this connecting Gaia NIR to cosmology has been something we've neglected, basically, and it's something we need to do much more on. So I think this is very useful. So we're thinking now about updating the science cases for making a proposal and so on. So I think we want to include this, but not only this talk, I should emphasize. All the talks that I've heard today, actually, there's many science cases that I think people would like to contribute, and we're going to look at if we can put this on a web page in some sort of tree of science cases, basically a bit inspired by Michael Perryman's science tree for Gaia. And there we should collect all of these science cases together. There's too many things for me to keep track of even. But this is very welcome and useful as a selling point. Thanks.
Sounds good, thanks.
Okay, all these presentations will be in the meeting. Yes. At least you will have the report of it. Marcel was first, I think. No? Okay.
Two questions. I'm completely unaware about cosmology. It's completely out of my comfort zone. So the first one is your resolution small enough so that we figure out when high-speed train is arriving in Teruel? The real question is, there's been a lot of drama over the last year and a half about the evolution, possible change in dark energy, DESI and all that thing. And we are in a dark energy dominated era, cosmological era, right? So how does dark energy, possible variation of dark energy enter your simulations? I guess that was my question.
Yeah, so the local group is a massive bound system that dominates the dynamics of all the objects that belong to it. So dark energy does not really affect, not even for the Hubble flow, the dynamics of its members. So should be fine.
Okay. Any other question? Then thanks, Isabel, again. And welcome Guillaume Thomas from the Instituto de Astrofísica de Canarias, who will be talking about studying the Milky Way stellar halo and its stellar stream with Gaia NIR.
Sorry, I can't stop sharing my screen. Oh, finally.
Vale, perfecto. All right. Well, so first of all, I would like to thank the organizer to give me the opportunity to speak of my favorite object and my favorite topic, which is of destroying dwarf galaxies and studying them. So in particular here, I'm going to focus on the Milky Way stellar halo and stellar streams, and I'm going to try to convince you how Gaia NIR infrared is going to help us to revolutionize our view of them. So let's introduce first our protagonist. When we're speaking of the stellar halo, we're speaking of the outermost component of a galaxy like the Milky Way. Typically in our cases, it's 20 times bigger than the size of the disk, just for you to get an idea. In terms of stellar masses, it's really negligible. You have basically 1% of the total stellar masses in the stellar halo. However, it's a really important component if you want to understand the nature of dark matter, if you want to probe the distribution of dark matter, but also if you want to understand how was formed a galaxy like the Milky Way. It can look a bit like really smooth, like the stellar halo is all this outer part that you can see outside this extinction, which thanks to Gaia, we can see the extinction. So everything that we are focusing in area where we don't have any extinction or really low. So my first thought when I saw this, and people mentioned Gaia NIR infrared, is what will be the improvement of Gaia NIR infrared to study stellar streams and stellar halo? Infrared, well, we don't need much more, but the extended wavelengths on the baseline between Gaia and Gaia NIR infrared is going to provide us better astrometry. Actually, by doing so, I also realized that actually the infrared component is going to be really useful for many things. So the stellar halo can look a bit like smooth, but actually you have many population inside, a lot of debris, dwarf galaxy, globular clusters, and a lot of streams that you can see here that are coming from the disruption of this object with time due to tidal effect. And actually, right now, we have been discovering more than 90 streams around the Milky Way. More than 80% of them are either be confirmed or even found thanks to Gaia alone right now. And it's really likely that we're going to discover way more of them in the near future with Gaia DR4, Gaia DR5, and Gaia NIR infrared is also going to help us to discover a lot of them, in particular in that region where you see that we are missing a lot of streams and we expect to get them. So if you just want first a good example of what infrared is going to provide us is detecting more streams. So what the stellar stream are really useful for? I'm sure that a lot of you have heard about stellar stream, but I'm not sure that you have seen the whole panel of what we can do with them. First of all, stellar stream are really excellent accelerometers. We hear just before with industry that they provide accelerometers. That's the best galactic accelerometers that you can do. With it, you can measure directly the distribution of the potential, the distribution of mass in the stellar halo at different distances, at different area. And so you can quantify not only the global distribution, like the density of dark matter around the Milky Way, but you can also get the shape of the dark matter halo with it. You have an example here with the Sagittarius streams that help us, for example, to understand that
globally, the Milky Way halo seems to be more prolate in the distances. Actually, we know more it's more triaxial. And stellar streams also are really useful to provide and to probe the distribution of mass around the Milky Way. You can see on this very nice diagram a lot of different tracers showing the mass of the Milky Way with distances. And within the first 100 kiloparsec, a lot of the studies are using stellar streams. For a good reason, this is the best tracers that we can do. Instead of getting just a snapshot at the given time, you get a view of stars distributing a long time. It's like if you want using a kind of images, if you want, or a movie instead of images. However, the Milky Way is not in equilibrium. We know this for a couple of years now, and unfortunately, the LMC is here. And the LMC, due to its presence, is attracting the Milky Way with differential forces at different distances, and so the Milky Way is moving from its original position, getting attracted by the LMC, but the different area of the halo is not attracting in the same, with the same strength, and so you are going to generate a dark matter wake that you can see here. You are going to produce a collective response, which is just due to this over-density of dark matter that are going to be present because they are not pulled away like the same time than the Milky Way. And the other part, which is this transient wake, which is typically the Chandrasekhar dynamical friction tail behind a big massive object. And this means that it's a bit complicated and it has a big effect, and stellar streams are really useful to quantify them. Here you have, for example, an images of the accretion of the Orphan-Chenab galaxies and the formation of the stellar stream. And you see here the black point is the LMC, and it doesn't pass inside the stream, it's passed really nearby, and you see that it's going to generate a perturbation. Normally what you expect, you're going to get the proper motion which should align with the streams. The stars should follow along the stream. However, you will see that when the LMC, this black point here, passes nearby a part of the streams, you're going to get an offset of the proper motions or of the velocity vector, which is not going to be aligned, generating a modification in this morphology, but also in the different velocity vector. Something similar that you can see also is in terms of another plan that we like is total energy against angular momentum diagram, because it's conserved quantity in an axis symmetric potential. And normally you should get something which is ellipsoid along a given axis, but you see that this perturbation means that you have a big change in total energy and angular momentum, and you have a lot of weird features that still to appear. And by studying the streams, we can try to quantify the different effects, the LMC, but also much more. Another way to see the perturbation or to see the impact that we can have is for most of the study, the LMC is neglected. However, we show, for example, thanks to Sagittarius morphology in that cases, that including the LMC bring the mass of the Milky Way lower than what you expect, typically by 10%. So typically what will provide Gaia NIR infrared for this is that its precise astrometry in its extended baseline is going to help us to get better proper motion, better parallaxes, and so we're going to be able to get better probe to be able to study at the same time the galactic potential and the perturbation. Stellar stream also really interesting not only to study the outer part of the Milky Way, but also the inner part for many things. First of all, it's because it can cross the inner part of the Milky Way, the inner center, and it can give you, provide you information about the 3D shape of the potential in the inner part of the Milky Way. Furthermore, they're also really sensible to perturbations such as galactic bar or the spiral arms. And you have an example here of the Hyades streams coming from the distribution of the open cluster Hyades with different pattern speed of the bar. And you can see that at some point you have the pattern speed that become really important, and you're going to get the streams that tend to be tilted, but also its own morphology can be disrupted. Just because the bar is not going to affect the same part of the stream at the same moment, sometimes you're going to extend the stream, sometimes you're going to shred it inside. And it's exactly what you can see here, that the pattern speed had a big impact. What it is meaning is that with this, you can study at the same time the pattern speed of the bar of the Milky Way, the pattern speed of the spiral arms, but you can also study the dynamical evolution. Here it's an example with 1 streams. Imagine now that you are using 50 streams, something like this. You are going to be able to study the dynamical evolution of the pattern speed of both the spiral arms and of the bar. And for that, well, it's exactly what you see. This here is the inclination of the streams with the pattern speed. And in that case, Gaia NIR infrared is going to help us a lot because it's infrared, so we are going to detect a lot of the stream like this. So far, the IADS, we are not even sure which stars belong to the streams. There is different candidate of the path of the streams, and we need radial velocities for this. But in particular, if we want to detect more streams, if we want to detect more of this object, we need to go in infrared and to go in a region where the extension is really important. Furthermore, stellar stream also really good to quantify the granularity of the halo, because as Isabel said really well before, in the lambda CDM or L warm dark matter model, we expect that the structures are formed hierarchically. And so you expect also that you will get a lot of dark matter subhalo that remain dark, just they don't have stars because they are not enough massive to keep the gas at the moment of reionization. And so you expect that you have a lot of tiny dark matter subhalo around our galaxy, which will orbit. And depending on the type of dark matter, you're going to get more or less of this dark matter subhalo. And so we can quantify this with stellar streams because these objects, when they cross the stellar streams, are going to let the features that we can observe. You have here a simulation of one stream of the Palomar 5 streams, upper part which is not perturbed, and in the lower part which is going to be perturbed by the passage of two dark matter subhalos inside it. The first one here, and the second one. What's happened is that the dark matter subhalo is going to cross the streams, is going to attract the stars really nearby, and then the stars are going to be attracted like this. The stellar halo is going to continue its path, and the stars are still going to continue to grow like this, creating this gap. The problem is that a lot of things can also create gap. The bars, palhams, geomolecular cloud, this tilting, well, a lot of things, even observational effect, internal dynamic effect, many things. However, this can also have a specific dynamical imprint. In terms of proper motion, radial velocity, you have typically a perturbation around 300 meters per second. So with Gaia NIR infrared, again by combining with Gaia, you're going to get very precise astrometry, and we're going to be able to detect this feature for streams up to 30, 40 kiloparsec, which means that we're going to be able to probe the granularity of the halo until these distances. They're also really good to probe gravitational framework, or different alternative gravitational framework. For example, here in the simulation I made of Palomar 5 again, in MOND we can see that the leading arm is shorter than the trailing arm, which is not what you expect in classical Newtonian dynamic. And it is exactly what we have in the observation. It's not a fit. This was a prediction, actually, of the observation. And Gaia NIR infrared is going to help us, again, with this. With extended proper motion, we're going to be able to quantify the dynamical differences that we have between MOND and Newton. It's not only the string is shorter, the dynamic is also a bit different. But for that, you need to be in a specific spot, between typically 8 to 30 kiloparsec from the Milky Way. And again, being infrared is going to help us because we're going to be able to go in another direction of the Milky Way, where we expect also this effect to be even more dominant. Well, so I speak a lot of stellar streams. Let's go now in the stellar halo, and in particular in older accretion. For old accretion more than 8 giga-years ago, we cannot see the stellar streams anymore. The object completely doesn't form any spatial structures. You see here for most of these accretions that are really old, we don't see any structures at all. However, they still form structures in integral of motions. It is this really famous plot from Amina Elmi that I think she made actually for Gaia, where you have the initial distribution in energy angular momentum diagram, and when you combine with the Gaia uncertainties, you expect that the stars stay more or less in the same direction. And we have already started with Gaia to study this object, but in the solar vicinity, because we need precise distances, so parallaxes, and we have this distribution that you can see here of integral of motion space with a lot of substructures, and these substructures are the debris left by galaxies that have been accreted in the past. However, there is a problem, is that in the solar vicinity, it's really hard to be able to know if one of these structures is coming from a galaxy, or a single galaxy, is that a merge of different galaxies, or it can also be due that different structures that you see are coming from the same accretion. Potentially, these two structures are linked together, for example. It is what you see in the simulation here, where each color represents a given progenitors. You can see that depending on the time in the solar vicinity, that's the same volume. Sometimes you're going to be able to identify some of the structures, but a given accretion can let different substructures. Sometimes you're not going to be able to differentiate galaxies. For example, here, you're not going to be able to differentiate the blue from the orange galaxy. And so Gaia NIR infrared is going, again, to help us a lot, because it's going to provide us better astrometry, better parallaxes. We're going to be able to do so until 40, 50 kiloparsec in that cases. And it is really interesting because it's going to give us better detection. The structures are going to be thinner, smaller, due to better precision. And we're going to be able to go more distant. And at further distances, you're not going to get this melting of different structures forming together. So we're really going to be able to disentangle these different structures. Furthermore, because it's going to be infrared, we're going to be able to go more in the center of the Milky Way. It is a really interesting area because it's where we expect to get the trace of the most important accretion. Due to dynamical friction, the most massive galaxy will be in the center, and so infrared data are going to help us to get this. And just to finish, because I think images might be better than a long story, just to show you visually how Gaia NIR infrared is going to help us in all of it, I use the simulation of the Sagittarius streams that you have here in gray. You have proper motion in right ascension, and distances measured by 1 over parallaxes, which we all know that it's not correct, but well, let's do it for simplicity. You have this data, that's the true representation of individual particles. When you combine it with Gaia error and with Gaia NIR infrared, you can clearly see that the big improvement just by eyes, right? For example, if I try to get the velocity dispersion along the streams, it's impossible right now. We are dominated by the error. We cannot do it for the furthest part of the streams, which is the most interesting because it's where we have the most information about the shape of the Milky Way, or where we can extract it. So with Gaia NIR infrared, we have uncertainties that will be so small that we're going to be able to study the dynamical dispersion along the streams in proper motion with all the stars. Same, we're going to be able to get better distances. I'm going to finish on this, where we can start also to get better tracer, not only for a few stars that we have right now, typical tracers, but for a lot of stars until 30, 40 kiloparsec. We can also go to see this in energy angular momentum diagram. Again, that's what you have. You see a lot the dynamical dispersion, the trace due to the LMC. That's what we have right now with Gaia DR3 at every distances. If we can observe all the stars, which is not necessarily the case, that's what we're going to get with Gaia NIR infrared. Now you can see that we can really quantify the perturbation, not only to detect them, but quantify the perturbation, not only from the LMC, but also from older accretion, like gas sausages, from the bar, from different features that we even don't know yet. So in conclusion, I think that Gaia NIR infrared is really going to revolutionize our field, not only because we will get better astrometric solution, but also the infrared data are going to provide us a lot of information. Combining Gaia with Gaia NIR infrared, we improve the astrometry, and also we can combine also with spectroscopic observation, as in coming, as a right now observing like WAVE for most DAISY, DAISY-5, whatever, but also with future telescopes like MSC or WST, which will arrive exactly at the moment that Gaia NIR infrared is going to be launched. And the Spanish community has, I think, in that cases, because we have in the Agencia Española de Espacio, we have to speak a bit of Spain, we have both the observational and theoretical background, I think, to lead this project on studying the stellar halo with Gaia and Gaia NIR infrared in the future. Thank you.
Okay, one quick question from the audience there at the bottom of the...
Nice talk, John. Thanks. I didn't understand how do you distinguish perturbations from stochastic variations of stellar densities?
Oh, well, that's exactly the point I have usually. It's really hard, and just by doing density, you cannot do it. That's why you really need to get access to the dynamic inside, because you need to study at the same time the morphology, distances, and the velocity perturbation to be able to know if it's which type of perturbers is going to perturb the streams, either by making gaps or by perturbing the global morphology. It's really complex to do, and right now we don't have enough precision in the astrometry to be able to do so. So the improvement of the astrometry, either for parallaxes or proper motion, is going to help us a lot to be able to differentiate between the different perturbers. The problem is that the perturbers go on one on top of another, and it's really hard to know which is a dominant effect in some cases.
Okay, thank you, Guillaume. Okay, with that we end this session. We resume tomorrow.